Hey guys, good evening and welcome back. Good evening and welcome back again to your Unacademy NEET English channel. I believe all of you are doing great. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know in the chats quickly. Let me know in the chats quickly if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly, my dear students. Good evening and welcome back. Good evening and welcome back. So what's up? How are you all doing? How are you all doing? All good? Yes, perfect, amazing. So guys, I had to delay this session by 1 hour, right? Otherwise, we start all the sessions exactly at 5 p.m., right? There were some technical issues which I was facing, so finally, they are all fine, and I believe I'm perfectly audible and perfectly visible to all of you, right? Perfect. So, before starting this particular session, let me know in the chats whether you are done with the mole concept completely or not. Say yes or no in the chats. I just want to know it. Say yes or no in the chats. Everybody. Are you done with the mole concept chapter already? Are you done with the mole concept chapter already? I just want to know that. Yes, JEE students can also watch this. Absolutely, yes. You guys can also watch the session. Perfect. I can see all the students are saying yes, they have completed the mole concept. That's great. So why did I take solution as the chapter number 2? Because you know, solution chapter, it's interlinked with the mole concept, right? It is interlinked with the mole concept. So today we shall be completing the whole chapter, the entire chapter solution, right? So today we shall be completing the entire solution chapter, my dear students. So let me quickly show you what all things basically we are going to cover in the today's session. So let me tell you, people, the complete chapter involves all the theory, all the types of the questions which can be asked from the chapter solution. Every single thing will be covered exactly from the basics, from the scratch, right? Whether you have studied this chapter before or you have not, does not matter. Every single thing I'll be discussing in detail, okay? Right from the basics. Whatever questions can be asked from this particular chapter, every single problem pattern I'll be showing you here, and all the PYQs which have been asked from the chapter solution, every single thing will be covered in detail, right? So all ready, people? All ready? I would want you guys to let me know in the chats with some fire emojis. Are you all ready? Someone is saying screen is not fully visible. Well, I can see it from here. It's completely visible, right? I think you need to change your settings. I think you're watching this video at 120, 160p, something like that, yeah? Perfect. The duration of this chapter, I believe this chapter will be getting completed in almost 9 hours. This chapter will take, I would say, 8 to 10 hours. 8 to 10 hours. Yeah. 8 to 10 hours it's going to take. PDF of the session I share on my Telegram, you know it, right? Which is Wassim Bhat Chemistry Official. Right? That's where I keep on sharing the PDF. Okay, and right after the chapter, I share the DPP as well. I'm pretty much sure you would have solved the DPP of the mole concept, which I already shared on my Telegram, right? And I believe you would be able to solve all the questions if you have watched the mole concept chapter in detail from the basics. Okay? So are you all ready then? Should we start? Are you all ready? And let me know if you guys are going to be with me till the end. Are you ready for that? Are you ready for that? Are you ready for that? Yeah? Perfect, guys. Perfect, 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 perfect. Perfect. So let's get going then. Let's get started with the session. My dear students, let me quickly show you the overview of the things which we are going to do in the today's session. We shall be starting with the concentration terms, right? Concentration terms is going to be our first topic, which involves all your concentration terms, molarity of dilution, molarity of mixing, molarity of reacting, non-reacting, every single thing, right? After that, we shall be talking about a term called as vapor pressure, which we would need everywhere in this particular chapter. And after vapor pressure, I'll be giving you the elementary idea of the boiling point, the elementary idea of the freezing point. Then we'll go to the Rault's law and its applications. After we are done with the Rault's law, right, we shall be discussing ideal, non-ideal solutions. After ideal, non-ideal solutions, colligative properties, one of the most important topic, right? And these colligative properties will be discussing relative lowering, elevation in boiling point, depression in freezing point, osmotic pressure, and at the end, one of the super important topics of the chapter, that is going to be your Vant factor. That is going to be your Vant factor, right? Someone is asking about the collision theory. Collision theory is not in this particular chapter. Collision theory is in the chapter chemical kinetics. Okay? Perfect. So this is going to be the session flow, people. So should we start then? All ready? Should we start? Should we start quickly in the chats? Everybody. 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 All ready then? All ready? Perfect, guys. So let's get going then. Let's get started with the first topic. That is going to be your concentration terms. Okay? Concentration terms, people. Well, before starting the concentration terms, I just want to give you some basic information, right? I just want to give you some basic information first. Then we'll enter into the first topic, that is your concentration terms. Understand, people, what exactly I'm going to say. Well, first of all, when you talk about a solution, my dear students, you must be familiar with the fact that a solution is basically made up of two components. Solution consists of two components, right? You should be knowing about that. One is going to be your solute, and one is going to be your solvent. Solution consists of two components exactly. One is going to be solute and one is going to be the solvent, right? How do we define solute in general and how do we define solvent in general? My dear students, remember one simple point. Solute is basically that component of the solution which is present in lesser amount. Solute is basically that component of the solution which is present in lesser amount. And when I talk about solvent, solvent is basically that amount which is generally present in larger amount, which is generally present in excess. This is your first point. Your solution consists of two components, solute and solvent. Solute is the one which is present in lesser amount. Solvent is the one which is present in larger amount, or you can say solvent is present in excess, right? Point number one. Point number two, my dear students. Point number two. Let me tell you the phase of solvent. The phase of solvent and the solution. The phase of solvent and the solution will be the same. What does that mean? That means if the solvent is in liquid state, the solution which we get at the end, that will be also in liquid phase, right? If solvent is in liquid phase, the solution which we get at the end, that will be also in liquid phase as well. So remember, whatever is going to be the phase of the solvent, same is going to be the phase of the solution. This is again one more point which I would want you guys to remember from now on, right? The phase of solvent and the solution will be always the same. Okay. From now onwards, solute you are going to represent either with number 2 or with letter B. Solute you are going to represent either with number 2 or letter B. Similarly, solvent from now onwards you are going to represent either with number 1 or letter A. Okay. Perfect. This is again one more thing. Solute you'll be representing with number 2 or letter B. Solvent you are going to represent with number 1 or letter A. This is again one important point which you will be remembering from now onwards. Similarly, my dear students, one more important thing. As I told you, solution consists of solute and solvent. Solution consists of solute and solvent. So remember one thing. Mass of solution is always equal to the mass of solute plus mass of solvent. This is again one point which I'll be frequently using here, right? Mass of solution is always equal to the mass of solute plus the mass of solvent, right? Similarly, my dear students, there are few terminologies which I'll be using frequently here. What are those terminologies? Have a look. I'm writing W, I'm writing N, I'm writing E, and I'm writing M over here. Let me tell you this W. W stands for mass of the substance in grams. W stands for the mass of the substance in grams. N stands for the number of moles of the substance. E stands for the equivalent mass of the substance. And M over here stands for molar mass of the substance. Well, these are the few terminologies which I'll be frequently using over here. W stands for mass of the substance in grams. N stands for number of moles of the substance. E stands for equivalent mass of the substance. M represents molar mass of the substance. Now, my dear students, tell me just one thing. For example, sometimes if I write W2, can you let me know what will be the meaning of this W2? Since W stands for mass, 2 stands for solute. That means W2 stands for the mass of solute. W2 stands for the mass of solute in grams. For example, sometimes if I write W1, W1 stands for the mass of solvent in grams. Let's say sometimes if I write M2, M stands for molar mass, 2 stands for solute. So what is M2? M2 means the molar mass of solute. For example, if I sometimes write N1, N stands for moles, 1 stands for solvent. Therefore, N1 means number of moles of solvent. Right? As simple as that. Perfect. Now people, let me tell you a few more important things. Understand. My dear students, when you talk about the solutions, we have got different types of solutions. I believe you would have already heard them as well. The first type of the solution you must have heard, that is your binary solution. Right? Binary solution. What is a binary solution exactly? Binary solution is the one which exactly contains how many components? It consists of two components. Binary solution is the one which consists of two components. Out of those components, one component will be for solute and one component will be the solvent. In total, there will be two components, one component of solute and one component of solvent. Any such solution which will be having two components in it, you'll be calling that solution as the binary solution. Number one. Number two. My dear students, first one is the binary solution. What is the second one? Can you let me know in the chats? Can you let me know in the chats? Based on the number of components in the solution, what will be the second type of the solution? Quick in the chats. Quick in the chats. Guys, this is something which I believe you should know, right? This is something which is complete basics. What is the second type of the solution? Absolutely. Second type of the solution is going to be the ternary solution. Well, if I talk about the ternary solution, it will be having how many components in total? It will be having three components. It will be having three components. Out of these three components, there will be two components of solute and there will be one component of solvent. Two components of solute and one component of solvent. Similarly, there is one more type of the solution. What do you call that as? Binary, ternary. Second is quaternary. What is a quaternary solution? Let me tell you, quaternary solution is the one which will be having exactly how many components? 4 components. Out of which 3 components will be for solute and 1 component will be for solvent. So in total 4 components, out of which 3 are the solute components and 1 is the solvent component, right? Similarly, guys, sometimes in this particular chapter, I'll be using the term aqueous solution. In this particular chapter, sometimes I'll use the term aqueous solution. What is an aqueous solution in particular? I would say aqueous solution is the one in which the solvent used is water. Any solution, any such solution wherein the solvent used is water, you'll be calling that particular solution as the aqueous solution, right? Perfect. So my dear students, this is something which you are going to remember from now onwards. Okay, these are some basic things, right? These are some basic things which you will be remembering from now onwards. Now, after all this stuff, let me exactly come to our actual topic. What is that? That is your concentration terms. This is our first topic in the today's session. Concentration terms. My dear students, this particular topic, concentration terms, it is almost used everywhere in your physical chemistry. You must be knowing about it, right? Yeah, this particular topic, concentration terms, it is used almost everywhere when it comes to your physical chemistry. Now we will try to understand. The first concentration term which we are going to discuss here, that is weight by weight percentage of solute. Weight by weight percentage of solute. So first thing, how do we define weight by weight percentage of solute? Before defining weight by weight percentage of solute, let me tell you, this weight by weight percentage of solute, I'm also calling as mass percentage of solute. Now, what this mass percentage of solute is all about? Simple, very basic terminology this is. My dear students, weight by weight percentage of solute is defined as, that mass of the solute in grams. That mass of the solute in grams, which is present in 100 grams of solution. That mass of solute in grams, which is present in 100 grams of solution. Imagine you have got a container, right? Imagine you have got a container. Imagine the container has got 100 grams of solution in it. Imagine that container has got 100 grams of solution in it. Now, my dear students, if there is solution in the container, that tells you what? That means there will be solute as well as solvent in the container, right? For example, What I'm trying to say is, imagine this is the container. Imagine this container contains 100 grams of a solution. Now there is a solution in the container, so it will be containing solute as well as solvent. For example, just to make you understand, let's assume in 100 grams of solution, there are 20 grams of solute present. Let's assume that. Let's assume in 100 grams of solution, there are 20 grams of solute present. As per definition, that mass of solute in grams, which is present in 100 grams of solution, what do you call that as? You call that as weight by weight percentage of solute. So as you can see, as I told you, 20 grams of solute are present in 100 grams of solution. 20 grams of solute are present in 100 grams of solution. So you can directly say weight by weight percentage of solute here is 20. As simple as that. Weight by weight percentage of solute here is 20. What does that mean? That means 20 grams of solute are present in 100 grams of solution. Right? Similarly, my dear students, imagine in 100 grams of solution, if there were 30 grams of solute. What does that mean? As per definition, that means weight by weight percentage of solute is 30. Right? Imagine in 100 grams of solution, there are 40 grams of solute. What does that mean? That means weight by weight percentage of solute is 40. Right? As simple as that. I believe this is something which is clear to you. Now people, how do you first of all calculate weight by weight percentage of solute? What is its formula? Let me give the formula directly. Weight by weight percentage of solute, which is what you call as mass percentage of solute. It is always equal to the mass of solute in grams divided by the mass of solution in grams multiply with 100. This is the simple result by means of which we can calculate. Weight by weight percentage of solute. Right? Similarly, my dear students, if I ask you, what do you think will be the formula for weight by weight percentage of solvent? You'll directly say weight by weight percentage of solvent will be nothing. It will be just mass of solvent in grams divided by mass of solution in grams multiplied by what? Multiplied by 100. Simple way of calculating weight by weight percentage of solvent as well. Okay? Simple way of calculating weight by weight percentage of solvent as well. Now, my dear students, for example, let's say this is the container which I'm taking. Just to make you understand. Let's say this is the container. For example, in this container, we have got 500 grams of solution. Assume that in 500 grams of solution, there are 10 grams of solute. Assume that in 500 grams of solution, there are 10 grams of solute. If I ask you to calculate weight by weight percentage of solute, here, what you'll be doing? Mass of solute in grams, which is 10 grams, divided by mass of solution in grams, which is 500, multiplied by what? Multiplied by 100. Right? Multiplied by 100. Perfect. Mass of solute in grams divided by mass of solution in grams multiplied by 100. This is going to give you what? This is going to give you weight by weight percentage of solute. As simple as that. Right? What does it mean? See, 0000 cancel, 5152. So weight by weight percentage of solute is 2. As per definition, what does it mean? It means that 2 grams of solute will be present in 100 grams of solution. As per the definition. Right? 2 grams of solute will be present in 100 grams of solution. I believe this is something which is clear to you. Okay. Now guys, there is one more thing which I would want you guys to remember. What is that? Remember, weight by weight percentage of solute plus weight by weight percentage of solvent, it is always equal to 100. Weight by weight percentage of solute plus weight by weight percentage of solvent, it is always equal to 100. I might use this result also sometimes. Okay. Now, one more important thing. My dear students, for example, sometimes if I write like this, if I write 20% weight by weight of NaCl aqueous. If I write a statement like this, for example, you should be in a position to decode this statement. You should be in a position to decode this particular statement. First of all, have a look. We have used the term here aqueous. Aqueous means the solvent used is water. If the solvent used is water, that means this NaCl becomes your solute. This NaCl becomes your solute, right? 20% weight by weight of solute. What does that mean as per the definition? As per the definition, it means that 20 grams of solute, which is my NaCl, 20 grams of solute are basically present in 100 grams of solution. Are basically present in 100 grams of solution. I hope you will be in a position to decode these sort of statements as well, right? Complete basics, right? And I would just want you guys to remember these results. That's all. This was our first concentration term. I won't be solving any questions till we are done with 3-4 concentration terms first. Till then, I'm not going to solve any question. I'm just going to give you the results, the definitions, and then we'll solve the questions in the combined mode. Okay? Perfect, guys. One more thing. I have written over here that 20 grams of NaCl are present in 100 grams of solution. 20 grams of NaCl, 20 grams of solute is present in 100 grams of solution. So what is this 20 grams? I'll say this 20 grams here is the mass of solute. What is this 100 grams? This is the mass of solution. This is the mass of solution. This is the mass of solute. If I ask you, what will be the mass of solvent? Mass of solvent will be simply mass of solution minus the mass of solute, which comes out to be how much? Which comes out to be 80 grams. Clear? As simple as that. Yeah? Amazing. Let's move on to one more concentration term. What is that? That is your weight by volume percentage of solute. My dear students, how do we define weight by volume percentage of solute? Just have a look. Just have a look. Let me write its definition. It is defined as the mass of solute in grams, the mass of solute in grams, which is present in 100 ml of solution. Which is present in 100 ml of solution. Mass of solute in grams. Mass of solute in grams, which is present in 100 ml of solution. Okay? So for example, if you will be having 100 ml of solution, let's assume in 100 ml of solution, there are 20 grams of solute present. Let's assume in 100 grams of solution, let's assume in 100 ml of solution, there are 20 grams of solute present. What does that mean? That means weight by volume percentage of solute is 20. Imagine in 100 ml of solution, there are 30 grams of solute present. You will say weight by volume percentage of solute is 30. Imagine in 100 ml of solution, there are 40 grams of solute present. What does that mean? Weight by volume percentage of solute is 40. So in short, my dear students, remember one simple thing. Weight by volume percentage of solute is nothing but that mass of solute in grams, which is present in 100 ml of solution. Right? Perfect. Right, people? Am I clear? Am I clear till here? That mass of solute in grams, which is present in 100 ml of solution. Perfect. What was here? It was the mass of solute which was present in 100 grams of solution. But here, in the second case, it is not 100 grams of solution. It is 100 ml of solution. Correct? Correct, people? Someone is saying, sir, you missed mass percentage. This is the mass percentage, right? This is the mass percentage. I did not miss it. I hope this is clear. All right. Now, my dear students, just try to make its result. What do you think will be the result for the calculation of weight by weight percentage of solute? I would say weight by volume percentage of solute will be equal to the mass of solute in grams divided by the volume of solution in ml multiplied by 100. This is the result with the help of which we can easily calculate weight by volume percentage of solute. In the similar way, if I sometimes ask you to calculate weight by volume percentage of solvent, it will be equal to mass of solvent in grams divided by the volume of solution in ml multiplied by what? Multiplied by 100. With this particular result, you can calculate weight by volume percentage of solvent as well, right? Now, my dear students, understand one simple thing. For example, if sometimes I write 20% weight by volume of NaOH aqueous solution. Well, you should be in a position to decode this statement over here, right? People, I mentioned weight by volume. It is not weight by weight. I mentioned weight by volume. Now, how you can decode this statement? It simply means 20 grams of your solute. 20 grams of your solute are present in. Now it's going to be 100 ml of solution. Because here I've used the term weight by volume. It is not weight by weight. Yes? Perfect. Simple and basic. For example, let me give you a scenario like this. Imagine this is the container. Let's assume, my dear students, in this container we have got 500 ml of solution. For example, if in 500 ml of solution, there are 50 grams of solute. Imagine if in 500 ml of solution, there are 50 grams of solute. If I ask you to calculate weight by volume percentage of solute, you should be in a position to do it. As per the formula, weight by volume percentage of solute is equal to mass of solute in grams. What is the mass of solute in grams? It is 50 divided by volume of solution in ml. What is the volume of solution in ml? It is 500 multiplied by what? Multiplied by 100. This is double zero cancels. The value comes out to be 50. So what is this 50 here? It is basically the weight by volume percentage of solute. It is basically weight by volume percentage of solute. As per definition, it means that 50 grams of solute are present in 100 ml of the solution. Yes? Right? Sorry, not 50. This is 5 and 5, 10. Right? This is 10. So it means that 10 grams of solute, 10 grams of solute are present in 100 ml of solution. I believe this particular stuff is clear to everyone. Yeah? I believe this particular stuff is clear to everyone. Now, my dear students, I just want you to remember one important result, which I'll frequently use in this chapter. What is that result? Just take a note of it. I'm not going to derive any result today. I'll be giving you the results and we'll see its application part, right? No derivation stuff, etc. needed, right? See guys, I'm writing weight by volume percentage of solute. Weight by volume percentage of solute. Do remember, weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of solution in grams per ml. This is one quick result which relates weight by weight of solute and weight by volume of a solute. Weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of solution. This is one quick result which I believe everybody is going to remember from now onwards. Yeah? I'll be frequently using this particular result in the questions. So remember this particular result. So my dear students, this was my second concentration term, that was weight by volume percentage of solute. Well, the third concentration term, which I believe you would have seen already, you would have studied also, volume by volume percentage of solute. Now tell me, how should I define volume by volume percentage of solute? Tell me in the chats. It is defined as the volume of solute in ml. It is defined as the volume of solute in ml present in 100 ml of solution. Present in 100 ml of solution. That volume of solute in ml, which is present in 100 ml of solution, that gives me the volume by volume percentage of solute. What does that mean? Imagine like this. Imagine you have taken 100 ml of solution. For example, in 100 ml of solution, there are 20 ml of solute. What does that mean? That means volume by volume percentage of solute is 20. If in 100 ml of solution, there are 30 ml of solute, That means volume by volume percentage of solute is 30. If in 100 ml of solution, there are 40 ml of solute, that simply means volume by volume percentage of solute is 40. That's all, right? So as per definition, volume by volume percentage of solute, it is defined as that volume of solute in ml, which is present in 100 ml of solution. Yeah? Right? So what do you think will be its result? If I ask you, volume by volume percentage of solute has to be equal to volume of solute in ml divided by the volume of solution in ml multiplied by what? Multiplied by 100. This is the formula with the help of which you guys are going to calculate the volume by volume percentage of solute. Right? Similarly, my dear students, if I ask you to calculate volume by volume percentage of solvent, how do you do it? Simple again. Volume of solvent in ml divided by volume of solution in ml multiplied by 100. This is going to give me volume by volume percentage of solvent. Right? Now, sometimes if I write like this, if I write 20% volume by volume of NaOH aqueous solution, NaOH aqueous solution, how you guys are going to decode this statement? How you guys are going to decode this particular statement? It's pretty much simple again, guys. Over here, the term is volume by volume. First, we decoded W by W. Second, we decoded W by V. Third, we are going to decode V by V. What does it mean? It simply means that, as per the definition, it means that 20 ml of solute, 20 ml of solute, which is my NaOH here, right, is present in 100 ml of solution. 20 ml of solute is present in 100 ml of solution. Right, people? As simple as that. As simple as that. Right? For example, imagine like this. Let's say this is the container which I have. For example, in this container, I have got 500 ml of solution. Assume that in 500 ml of solution, there are 50 ml solute. There are 50 ml solute. For example, if I ask you to calculate weight by weight percentage, volume by volume percentage of solute, how you guys are going to do it? Use the formula. Volume of solute in ml, that is 50 ml, divided by volume of solution in ml, that is 500 ml, multiplied by what? Multiplied by 100, 0000 cancel, the value comes out be 10. So what is this 10 here? If I ask you, what is this 10? What is this 10? This 10 is basically the volume by volume percentage of solute. As per definition, what does it mean? It means that, as per the definition, it means that 10 ml of solute, 10 ml of solute are present in 100 ml of the solution. I believe this is super clear to everyone, right? I believe this is super clear to everyone. Yeah? Perfect, people? Perfect? So this was your volume by volume percentage of solute, correct? And volume by volume percentage of solvent. Now, the fourth concentration term, my dear students, the fourth concentration term, what is that? That is going to be mole fraction, which we represent with chi. Mole fraction, which we represent with chi. How do we define the mole fraction? How do we define the mole fraction? How do we define the mole fraction? It's again simple. Mole fraction is defined as the ratio of moles of a component, to that of total moles present in the solution. What does it mean? Have a look. For example, people, imagine this is the container which you are taking, and in this container, assume that we have got a solution present. We have got solution in this container. If we have got solution in this container, what does that mean? That means the solution will contain solvent as well as solute. In this container, you will find solvent as well as solute, right? Now, my dear students, imagine that N1 represents number of moles of solvent in the solution. N2 represents number of moles of solute in the solution. N1 represents number of moles of solvent in the solution. N2 represents number of moles of solute in the solution. Right? Right, people? Now, if I define mole fraction of solute, as per the definition, it is going to be nothing but number of moles of solute divided by total moles present in the solution. Total moles present in the solution. This is the mole fraction of solute. Similarly, mole fraction of solvent is going to be number of moles of solvent divided by total moles present in the solution. As simple as that. As simple as that. As simple as that. Yeah? Shreya, just wait. I did not solve any questions yet. Just wait. Okay? When I solve the questions, every single thing will be super clear. Right? Just see what I'm doing right now. Follow me. Right? Eventually, step by step, you'll learn all the things. Okay? Now, people, there is one more term. There is one more term which might be used sometimes to just confuse you. Nothing else. What is that? Mole percentage. Sometimes they'll ask you to calculate mole percentage of either solute or solvent. Let me tell you, mole percentage is nothing but simply when you multiply mole fraction with 100, it becomes mole percentage, right? So, if I write mole percentage of solute is nothing but mole fraction of solute multiplied by 100. Similarly, if I ask you to calculate mole percentage of solvent, it is going to be equal to mole fraction of solvent multiplied by 100. Okay, sometimes they might give you the data in terms of mole percentage as well. Well, you should be knowing this particular stuff as well. Yeah. Now, people, tell me one thing. Mole fraction, what do you think will be the units of mole fraction? Mole fraction is basically the ratio of the same terms, the ratio of the same quantities. Moles in the numerator, moles in the denominator. So, remember something, this mole fraction, it is unitless. Mole fraction is unitless term. It is a unitless term, right? It is a unitless term. Remember this particular stuff as well. Okay? So this was my fourth terminology. That's what I'm calling as mole fraction. Okay? Now, let's try to solve certain basic questions first, right? From the terminologies which we have already covered. Okay? Try to understand, guys, what exactly I'm going to do. Have a look. This is the first question which I've already mentioned on the screen. Calculate the mole fraction of solute in 10% weight by weight of NaOH aqueous solution. So first of all, if I ask you, what is the meaning of this 10% weight by weight of NaOH aqueous? You should be in a position to decode this. What does it mean? What does it mean? It means that 10 grams of your solute, which is NaOH, are present in 100 grams of the solution. 100 grams of solution. This is something, what it means exactly, right? So 10 grams of solute are present in 100 grams of solution. So basically this 10 grams, what is it? It is basically the mass of solute. Mass of solute, which I represent with W2. If mass of solute is 10 grams, mass of solution is 100 grams. So mass of solution minus the mass of solute, that gives me the mass of solvent. So what is going to be the mass of solvent? Mass of solvent is simply going to be 90 grams. What am I supposed to calculate as per the question? I'm supposed to calculate mole fraction of solute. Mole fraction of solute. How do you calculate mole fraction of solute? Number of moles of solute divided by total moles present in the solution. So I would say, in order to calculate mole fraction of solute, I need the moles of solute as well as the moles of solvent. Right? Now people, tell me, how do we calculate number of moles of solute? Number of moles of solute will be simply mass of solute in grams divided by molar mass of solute. Similarly, number of moles of solvent will be equal to mass of solvent in grams divided by molar mass of solvent. Now tell me, what is the mass of solute? Mass of solute is 10 grams divided by, what is the molar mass of solute? Molar mass of NaOH, 23 plus 16 plus 1, comes out to be 40 grams. The value comes out to be 1 by 4. So these are the moles of solute which are there in the solution. Now similarly, calculate the moles of solvent. Mass of solvent, that is 90 grams, divided by molar mass of solvent. Molar mass of solvent. What is my solvent, people? Over here I mentioned aqueous. That means the solvent used is water. What is the molar mass of solvent? What is the molar mass of water? That is 18 grams per mole. The value comes out to be 5. So I got N1 as well as N2. Now we are done. We are sorted. So mole fraction of solute will be equal to number of moles of solute, which is 1 by 4, divided by number of moles of solvent, which is 5, plus 1 by 4. The value is 1 by 4 divided by 5 for 20 plus 1, 21 divided by 4, 4 cancelled. The value comes out to be 1 upon 21. So this is basically the mole fraction of your solute. This is basically mole fraction of your solute, which I was supposed to calculate. By chance, if they ask you to calculate mole percentage of solute as well, mole percentage of solute. What is mole percentage of solute? That will be mole fraction of solute multiplied by 100. Mole fraction of solute we have already calculated is 1 upon 21 multiplied by 100. This is going to give you the mole percentage of solute also, right? One thing which I forgot to tell you over here. What is that, people? What is that? Take a note of one statement. Take a note of one statement. For a binary solution, mole fraction of solute plus mole fraction of solvent, it's always equal to 1. For a binary solution, mole fraction of solute and plus mole fraction of solvent, it's always equal to 1. Similarly, remember one more thing. For a binary solution, mole percentage of solute plus the mole percentage of solvent, it's always equal to 100. It's always equal to 100, right? Do take a note of these two statements as well. Now, people, in the same question, if they ask you to calculate mole fraction of solvent, well, we calculated mole fraction of solute. If they ask you to calculate mole fraction of solvent, we know Chi1 plus Chi2 is nothing but 1. Therefore, Chi1 is nothing but 1 minus Chi2. So 1 minus 1 upon 21. The value comes out to be 20 by 21. This is the mole fraction of solute. This is the mole fraction of solvent, right? Similarly, if they ask you, what is the mole percentage of solvent? You will say mole percentage of solvent is nothing but mole fraction of solvent multiplied by 100. So the value will be 20 by 21 multiplied by 100. This is going to give you mole percentage of solvent as well. I believe this is clear. I believe this is super clear. Right? All clear, people? All clear? Everyone in the chats? Everyone in the chats, people? Perfect. Let's move on to one more question then. Look at this particular question, guys. See what the question is all about. Try to solve this. Yes. The question is, what mass of water should be added? What mass of water should be added to 16 grams of methanol to make its mole fraction 0.25? Right? To make its mole fraction 0.25. What does it mean? Understand. For example, this is the container. In this particular container, as per the question, we have got 16 grams of methanol. We have got 16 grams of methanol in this container. Now, people, as per the question is concerned, we have to add water in the container. And we have to add water in the container till mole fraction of methanol becomes 0.25. As per the question, my dear students, we need to keep on adding water continuously, and we'll keep on adding water till the mole fraction of methanol becomes 0.25. Let's assume X grams of water are to be added. Let's assume X grams of water are to be added to 16 grams of methanol. Then only mole fraction of methanol is becoming 0.25. Then only mole fraction of methanol is becoming 0.25. Guys, just a second. Okay. Perfect. There was an electricity cut. So I had to turn the generator on. It's done. All right. Look here now. I was saying, let's assume that X grams of water are to be added in the 16 grams of methanol, such that mole fraction of methanol is becoming 0.25. Now, guys, we are done. We are sorted. Mole fraction of methanol in this particular solution will be equal to number of moles of methanol divided by number of moles of methanol plus number of moles of water. As per the given question, this has to be equal to 0.25. Right? Right, people? Yeah? Now, my dear students, tell me just one thing. If I ask you how many moles of methanol are there in the container, moles of methanol will be simply mass of methanol divided by molar mass of methanol. The value comes out to be 1/2, which is nothing but 0.5. Similarly, just tell me how many moles of water are there in the container. It is simply going to be equal to mass of water in the container divided by molar mass of water. Perfect. So these are the moles of methanol in the container. These are the moles of water in the container, which are used to make the mole fraction of methanol as 0.25. Now put these values in this expression. We are sorted. Number of moles of methanol is nothing but 0.5 divided by. This is going to be 0.5 plus X divided by 18. And this value, as per the question, is nothing but 0.25. When you solve this equation, you'll be getting the value of X as 27 grams. I'm just asking you one thing. What is the meaning of this 27 grams? I'm just asking you one thing. What is the meaning of this 27 grams? Can I say this 27 grams, it is basically the mass of water which is to be added in the container, then only mole fraction of methanol is becoming 0.25. Yes. Perfect, people. Perfect, people. Perfect. I believe this is super clear to everyone. Now, guys, let's talk about few more concentration terms. Till now, we are done with 4 concentration terms. Let's have a look on the 5th concentration term. What is my 5th concentration term? Well, you would have heard this particular stuff as well. Strength, which is represented by capital S. You must have heard about this particular term as well. Strength. Strength. Yeah? What is strength, people? How do we define the term strength? Simple, basic. Let me tell you, strength is defined as the mass of solute in grams. The mass of solute in grams present in 1 liter solution. The mass of solute in grams which is present in 1 liter of solution. That gives you strength, basically. What does that mean? Try to understand. Let me make you understand this a bit more in detail. Imagine this is the container. Imagine this is the container. Assume that this container contains 5 liters of solution. Imagine in this container we have got 5 liters of some solution. Let's assume in 5 liters of solution. Let's assume in 5 liters of solution, there are 10 grams of solute present. There are 10 grams of solute present. Right? There are 10 grams of solute present. Now, my dear students, if you look at the given scenario, I can say 5 liters of solution. 5 liters of solution contains 10 grams of solute. I can say 5 liters of solution contains 10 grams of solute. Therefore, if I use the unitary method, I can say 1 liter of solution contains 10 divided by 5 grams of solute. Look at this particular stuff. What is it? What is it? It is basically the mass of solute. It is basically the mass of solute, which is present in 1 liter of solution. Right? It is basically the mass of solute, which is present in 1 liter of solution. And that mass of solute, which is present in 1 liter of solution, what do you call that as? You call that as strength. So I got the strength over here. The value of strength came out to be 10 divided by 5, which comes out to be 2. Or its units, I'll say it's going to be grams per liter, right? It's going to be grams per liter. Perfect. So strength over here is 2 grams per liter. What does that mean? That means 2 grams of solute are present in 1 liter of solution. 1 liter of solution. Yeah, 1 liter of solution. Perfecto. Now guys, let's try to make its formula directly so that you don't have to do all this stuff again and again. So strength, which I represent with S, it is always equal to. See, in the numerator we wrote 10. We wrote 5 in the denominator. What was this 10? 10 was the mass of solute. So in the formula, the numerator carries W2 divided by. This 5 was the volume of solution in liters. So this is the volume of solution in liters. This becomes my general formula to calculate strength over here, right? This becomes my general formula to calculate strength. If you knew this formula already, you were not supposed to follow this approach. Just use the formula. Mass of solute is 10 divided by volume of solution is 5. So 10 divided by 5 is 2 grams per liter, right? The units are here going to be grams per liter. Clear, people? Clear. So this was my one more concentration term, that was your strength. Let's move on to the 6th concentration term, that is what you call as molarity, which is represented by capital M, right? Which is represented by capital M. Now, my dear students, how do we define the term molarity? One of the super important term, right? One of the super important term. Molarity. Molarity is simply defined as the number of moles of solute, present in 1 liter of solution. Number of moles of solute present in 1 liter of solution. My dear students, imagine that. You have got 1 liter of solution. Imagine that you have got 1 liter of solution. For example, in 1 liter of solution, there are 2 moles of solute. Imagine that in 1 liter of solution, there are 2 moles of solute. As per definition, the number of moles of solute which are present in 1 liter of solution, that defines molarity, right? If in 1 liter solution, there are 2 moles of solute, that means molarity of the solution is 2. If in 1 liter solution, there are 10 moles of solute, molarity of the solution is 10. If in 1 liter solution, there are 20 moles of solute, molarity of the solution is 20. So in short, molarity is nothing but the number of moles of solute which are present in 1 liter of solution. Correct? Right, people? Now, what is the formula with the help of which we calculate molarity? The first formula, number of moles of solute divided by the volume of solution in liters. This gives me the molarity of the solution. Number 1. Number 2, number of moles of solute means mass of solute in grams divided by molar mass of solute. If I take volume of solution in ml, so over here you will have to multiply with 1000. This becomes my one more result to calculate molarity of the solution. You have to remember all the results, people. The next result to calculate molarity, one direct result I'm going to give you, which is going to ease out a lot of things in the coming future, right? In the coming questions. One more result to calculate molarity. What is that? That is 10 multiplied by weight by weight percentage of solute multiplied by density of solution in grams per ml divided by the molar mass of solute. This is one more direct result which is used to calculate molarity of the solution. Sometimes you'll be asked a question. They'll give you weight by weight percentage of solute. They'll give you the density of solution. They'll ask you to calculate molarity. Just remember the formula. You're sorted. You're done. No need to use your brain a bit, right? Use the formula. That's it. Similarly, one more result, my dear students. 10 I'm writing as such multiplied by. Do you know this term? Weight by weight of solute multiplied by density of solution. Weight by weight of solute multiplied by density of solution. What do we call that as? We call that as weight by volume percentage of solute. Divided by what? Divided by molar mass of solute. So these are few results which I would want you guys to remember from now onwards to calculate molarity of the solution. To calculate molarity of the solution. Now people, if I ask you, what are going to be the units of molarity? What do you think? Units of molarity will be moles per liter. Moles per liter, or you can call it directly as molar. You can call it directly as molar. Okay. For example, sometimes if I write like this, if I write 2 molar NaCl aqueous solution, what does it mean? As per the definition, it means that 2 moles of solute, which is my NaCl, are present in 1 liter of solution. 2 moles of solute are present in 1 liter of solution. 2 moles of solute are present in 1 liter of solution. That is the meaning of this particular stuff, right? My dear students, understand and remember one more thing. Molarity depends on, molarity of the solution depends on the volume of solution. Molarity of the solution depends on the volume of the solution. Volume of the solution depends on the temperature of the solution. Volume of the solution depends on the temperature of the solution. Molarity depends on volume. Volume depends on temperature. So I can directly say molarity is temperature dependent concentration term, right? So I can directly say your molarity, it is nothing but, it is temperature dependent. It is temperature dependent concentration term, right? And what happens generally? What happens generally? When you increase the temperature of the solution, generally what you'll observe volume of the solution will increase. And if the volume of solution increases, molarity is inversely proportional. Therefore, molarity of the solution generally decreases. This is one more important point which I would want you guys to remember from now onwards, right? So basically, remember one simple thing. Any concentration term whose formula contains volume, any concentration term whose formula contains volume, that's always going to be temperature dependent. For example, if you talk about weight by weight of solute, in the formula of weight by weight, is there volume? No. So it is temperature independent. If you talk about weight by volume, in the formula there is volume, so temperature dependent. Volume by volume, in the formula there is volume, so again temperature dependent. So any concentration term whose formula contains volume, right, either in numerator or denominator, that is going to be the temperature dependent concentration term. I believe this is clear. Right? Right, people? Now, few more things about molarity. Then we'll move ahead and solve certain questions of it. See, guys, what are those things about molarity? Understand and remember. Sometimes, just to confuse you, they might use a term semi-molar solution. Sometimes they might use a term decimolar solution. Sometimes they might use a term centimolar solution. And sometimes they might use a term millimolar solution. Now let me tell you, semimolar solution is the one whose molarity is 0.5. Decimolar solution is the one whose molarity is 0.1. Centimolar solution is the one whose molarity is 0.1. And millimolar solution is the one whose molarity is 0.001. Right? Remember this stuff as well. Semimolar solution is the one whose molarity is 0.5. What does that mean? That means 0.5 moles of solute will be present in 1 liter of solution. This means 0.001 moles of solute will be present in 1 liter of solution. I believe this is super clear to everyone. Yeah? I believe this is super clear to everyone. If this is super clear to everyone, tell me the answer of this simple question, guys. I do not want you guys to use your brain. I just want you to use the formula here, right? You're done in less than 10 seconds. The question says, calculate the weight by weight percentage of 1.5 molar CH3COH aqueous solution whose density is 0.8 molar. So my dear students, look at the question carefully. Look at the question carefully. Look at the question carefully. The question says, you've got a solution. Solution of what? CH3COH aqueous. That means the solvent used is water. The solvent used is water. So this automatically becomes my solute. And as per the question, I'm supposed to calculate weight by weight percentage of solute. I'm supposed to calculate weight by weight percentage of solute. What am I given with? What am I given with? I'm given with the molarity of the solution, which is 0.8, right? I'm given with the density of solution, which is how much? Sorry, molarity of the solution. How much that's given? Molarity of the solution, which is given to me as 1.5. Density of solution, which is given to me as 0.8 grams per ml. Guys, over here, just modify it. It is 0.8 grams per ml. Okay? Right? I wrote all the things which are given and which are to be calculated. So, do we have any formula which relates all these three things? Yes, there is one formula which I gave you a few minutes back. Molarity is nothing but 10 multiplied by weight percentage of solute multiplied by density of solution in grams per ml divided by the molar mass of solute, right? Now people, what is the molarity of the solution? As per the question, 1.5. 10 multiplied by weight percentage of solute is to be calculated. Density of solution is nothing but 0.8. Molar mass of solute. Check the molar mass of solute. Molar mass of acetic acid. Molar mass of acetic acid. How much that's going to be? I think it's going to be 60, right? Just cross multiple things and get the value of weight by weight percentage of solute. And my dear students, weight by weight percentage of solute after solving here comes out to be 11.25. Can anyone tell me the meaning of this 11.25 here? Can anyone tell me the meaning of this particular stuff? What does it mean? It means that 11.25 grams of your solute are basically present in 100 grams of your solution as per the definition of weight by weight. Correct? I believe this sort of a question you should be in a position to solve from now on easily, right? Now, people, now, look at one more question. Look at one more question. Look at one more question. All the JEE students watching me right now, this is the question which was asked long back in your JEE mains examination, right? And it's a proper NEET standard question. It's not difficult. Okay? So, look at the question carefully. Dissolving 120 grams of urea in 1000 grams of water. So, we have got 120 grams of urea and we are introducing 120 grams of urea in 1000 grams of water. What do we get at the end? We'll be getting a solution. We'll be getting a solution. As per the question, density of this solution is given to me as 1.15 grams per ml. What am I supposed to calculate? I'm supposed to calculate molarity of the solution. Is that? I'm supposed to calculate molarity of the solution. Kill it. It's a simple question. First of all, 120 grams of urea are introduced with 1000 grams of water. Which one among these two, urea or water, which one is present in lesser amount? Urea is present in lesser amount. The one that's present in lesser amount, what do we call that as? The one that's present in lesser amount, what do we call that as? Solute. So what is the mass of solute here? Mass of solute, which I'm representing by W2, it is 120 grams. What is the mass of solvent here? Mass of solvent is 1000 grams. Okay. What will be the mass of solution? What do you think? Mass of solution will be this plus this. 1120 grams, right? 1120 grams. Perfect. If I ask you, what will be the volume of solution? What will be the volume of solution? Volume of the solution will be mass of the solution in grams divided by density of solution in grams per ml. Simple, right? Density is equal to mass by volume. So volume has to be mass divided by density. So what is the mass of solution as per the question? It is 1120. What is the density of the solution? 1.15. When you solve this, the value comes out to be 973 ml. So what is this 973 ml over here? This 973 ml, it is basically the volume of solution. It is the volume of solution, right? Now people, how do we calculate molarity? Mass of solute in grams multiplied by 1000 divided by the molar mass of solute multiplied by volume of solution in ml. Just put all the values here and we are done. Mass of solute in grams, that's 120 multiplied by 1000 divided by molar mass of solute. Remember the molar mass of solute from now onwards. Molar mass of urea. Molar mass of urea is 60 grams per mole, right? The formula of urea you must be knowing, NH2CONH2, right? When you calculate its molar mass, it will be 60. So remember, 60 is the molar mass of solute, and volume of solution in ml we calculate already, that's 973 ml. When you solve this, the value comes out to be 2.05. So what is this 2.05 here? What is this 2.05 here? It is basically the molarity of the solution, people, right? It means that 2.05 moles of solute is my urea, is present in 1 liter of solution. As simple as that. Correct? Is it super clear? I believe yes. Now, before we solve some of the other questions, of the concentration terms, there is one more important concentration term which I want you guys to remember. What is that? That is your molality, which is represented by small m. So, my dear students, how do we define the term molality? You should be knowing this. Molality is defined as the number of moles of solute. The number of moles of solute. The number of moles of solute in 1 kg of solvent. 1 kg of solvent. This is how we define molality. Number of moles of solute. Nitika, you can use other formula also in the earlier question. So you can calculate weight by weight of solute first, then use the other formula, 10 multiplied by weight of solute into density of solution divided by M2, right? That can be used as well. The choice is all yours. Okay? I'm showing you one approach. You can use your brain and use different approach as well. The choice is completely all yours. Okay? Perfect. Have a look now. Number of moles of solute present in 1 kg of solvent. What do we call that as? Molality. What does that mean? Imagine in the container you have got 1 kg of solvent. Imagine in the container you have got 1 kg of solvent. In that 1 kg of solvent, for example, you are introducing 2 moles of solute. You are introducing 2 moles of solute. What does that mean? That means 2 moles of solute are present with 1 kg of solvent. As per definition, molality of the solution will be 2. If 3 moles of solute are introduced in 1 kg of solvent, so molality of the solution is 3. If 5 moles of solute are present in 1 kg of solvent, molality of the solution is 5. Right? So simple definition. Moles of solute present in 1 kg of solvent. Nothing more than that. Remember its formula. Molality, which I represent with small m, it is equal to number of moles of solute divided by mass of solvent in kg. Number of moles of solute divided by mass of solvent in kg. Now, my dear students, is there any other results which we can make over here? Yes, we can do that. Number of moles of solute is nothing but mass of solute in grams divided by molar mass of solute. Mass of solvent in kg. If I use mass of solvent in grams, I'll be multiplying here with 1000. This is one more result to calculate molality. Similarly, are there any other results? Absolutely, yes, there are some other results. Molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute multiplied by molar mass of solvent. This is one more result. Sometimes you will see a question in which mole fraction of solute will be given. They'll ask you to calculate molality. Use the result directly. Or they'll give the molality of the solution. They'll ask you to calculate mole fraction of solute. Use this result. You are done. Right? Similarly, there is one more result. Molality is equal to 1000 multiplied by molarity of the solution divided by 1000 multiplied by density of solution in grams per ml minus molarity multiplied by molar mass of solute. These are some super important results to calculate what? These are some super important results to calculate molality of the solution, people. Right? These are some important results which you are going to remember to calculate molality of the solution. Perfect. Now tell me one thing. Tell me one thing. What do you think will be the units of molality? Units. Moles per kg. Moles per kg. Or you can call it directly as molal. You can call it directly as molal. For example, if I write 5 molal NaCl aqueous solution, what does it mean? It simply means 5 moles of my solute are present in 1 kg of solvent, and the solvent used here is water. Correct? Right, people? Similarly, my dear students, understand few more things. Understand few more things. If I ask you, is molality going to be temperature dependent or independent? Look at the formula. Moles in the numerator, mass in the denominator. Do you see volume here in the formula? No, there is no volume in the formula. There is no volume in the formula. If there is no volume in the formula, what does that mean? It means molality. That is molality. Is it temperature dependent or independent? It is going to be the temperature independent concentration term. Molality is temperature independent. Why? Because molality does not depend on volume. Right? Okay? So tell me one more thing. Molality is temperature independent. Molarity is temperature dependent. So what do you think? Which concentration term? Molality or molarity? Molality or molarity? Which one is preferred? Which one is preferred? Quick. Remember, molality is preferred. It is preferred over what? It is preferred over molarity. Why is that? Molality is preferred over molarity. Why is that? Because you know, molarity is temperature dependent. Its value keeps on changing when we change the temperature of the solution, right? But molality, its temperature, its molality, its value does not change on changing the temperature. So this is one more important thing which I would want you guys to remember from now on. Let's try to solve few questions. Let's try to solve few questions. The first question which I am writing for you, give it a try. Give it a try quick. Calculate the molality of the solution containing 10% weight by weight of NaOH. Can you give it a try? Can you give it a try, people? Can you give it a try? Well, you should be in a position to solve this question. Well, as for the first question, as for this question is concerned, 10% weight by weight of NaOH. What does that mean? That means 10 grams of NaOH are present in 100 grams of solution. 10 grams of NaOH are present in 100 grams of solution, right? 10 grams of NaOH are present in 100 grams of solution. Dear students, what is this 10 grams? It is basically the mass of solute. So mass of solute here is 10 grams. Mass of solution is 100 grams. Mass of solution is 100 grams. If mass of solute is 10 grams, mass of solution is 100 grams. What do you think will be the mass of solvent? 100 minus 10 comes out to be 90 grams. So this is the mass of solvent. This is the mass of solvent, right? Now people, what am I supposed to calculate? Molality. Molality is nothing but mass of solute in grams multiplied by 1000 divided by molar mass of solute, and this is mass of solvent in grams. Few minutes back only I gave you this formula. So mass of solute is nothing but 10 multiplied by 1000 divided by, what is the molar mass of solute? Solute which I'm using here, that's NaOH, its molar mass is 40 grams Mass of solvent is nothing but 90 grams. Solve this, you'll be getting the molality of the solution. People are saying it's coming out to be 2.7. Is that? People are saying it's coming out to be 2.7. What is the meaning of this 2.7 if I ask you? It means that 2.7 moles of solute are present in 1 kg of solvent. Right? Perfect, people. Perfect, perfect, perfect. Everyone, quickly. Will you be able to solve this sort of equation on your own? You should be in a position to solve this sort of equation, people. Calculate the molality of a 2 molar NaOH solution whose density is given. Molarity is given. Molality is to be calculated. Molarity is given. Molality is to be calculated. Didn't I give you a result few minutes back? Molality is equal to 1000 multiplied by molarity divided by 1000 multiplied by density of solution minus molarity multiplied by molar mass of solute. Right? Now, people, 1000 you are writing as such. Molarity of the solution is given to me as 2 divided by 1000 I'm writing as such. Density of solution is given to me as 1.2 minus molarity of the solution is 2. Molar mass of solute, molar mass of NaOH is nothing but 40. Just the matter of calculation and get it done. Matter of calculation, get it done. Perfect. Perfect, people. It is just the matter of calculation now. No need to use your brain here. You know the formula? Use the formula. That's it. Our main motto is to solve the question. Right? And to solve the question in lesser time. Sometimes it would require to use the direct formula. Sometimes it would require to use the brain. Yeah? Perfect. Solve this one, people. Again, one simple and basic question. Calculate the mole fraction of solute in 0.1 molar aqueous solution. So we have got a solution whose molality is 0.1. The term used is aqueous. So the solvent used is water. The solvent used is water. What are we supposed to calculate? We are supposed to calculate mole fraction of solute. Do we have any result which relates mole fraction with molality? Yes. Molality is mole fraction of solute multiplied by 1000. 1 minus mole fraction of solute, molar mass of solvent. Molality is given to me as 0.1 is equal to chi2 multiplied by 1000 divided by 1 minus chi2 multiplied by, what is the molar mass of solvent? Molar mass of water, that's 18. So people, here you'll be getting one equation. That's all. One equation, one unknown. That's it. So it is 0.1 is equal to 1000 chi2 divided by, this will be 18 minus 18 chi2. Cross multiple stuff. 1.8 minus 1.8 chi2 is equal to 1000 chi2. Right? I would say 1.8 is equal to 1000 chi2 plus 1.8 chi2. So from this particular equation, can't you solve the value of chi2? Yeah? Perfect. Perfect, people. Am I clear with this? Am I clear with this? This sort of equation you should be in a position to solve. Similarly, there is one more similar sort of question. Look over here. Notes will be available on my Telegram. Wassim Bhat Chemistry Official. Okay? Look at this, people. Calculate molality of KCl aqueous solution made by dissolving 7.45 grams. Made by dissolving 7.45 grams of KCl in what? In 500 ml of solution. In 500 ml of solution. And the solution is aqueous in nature. Solution is aqueous in nature. That means solution has got solvent as water. Right? People, this you should be able to solve easily. First of all, as per the question, 7.45 grams of KCl are present in 500 ml of solution. What is the density of solution? Density of solution is this much. Okay, density of solution is this much. So what is the formula by means of which we can calculate molality? What if the formula is like this? Mass of solute in grams multiplied by 1000, molar mass of solute, and mass of solvent in grams. This is one of the results. Now, do we know the mass of solute in grams? Yes, 7.45 multiplied by 1000 divided by. Do we know the molar mass of solute? Molar mass of KCl when you solve, it is 74.5. Do we know the mass of solvent? We do not know the mass of solvent. So it is the high time to calculate mass of solvent first, right? I need to calculate mass of solvent first. How exactly am I going to calculate mass of solvent? How exactly am I going to calculate mass of solvent? See guys, density of solution is nothing but mass of solution divided by volume of solution. This is your density of solution. As per the equation, it's given to me as 1.2 grams per ml, right? Mass of solution. How much is the mass of solution? Let's try to calculate that. Mass of solution is equal to 1.2 multiplied by volume of solution. 1.2 grams per ml multiplied by volume of solution. How much is volume of solution, people, as per the question? It is 500 ml. So ml cancelled. The value comes out to be 600 grams. So if I ask you what is the 600 grams, it is the mass of solution. But do I want mass of solution here? No. I want mass of solvent. I want mass of solvent. Mass of solution I got. Mass of solute I have. Mass of solution I have. Mass of solute I have. So mass of solution minus the mass of solute. That gives me the mass of solvent, which comes out to be 592.55 grams, right? Solve this and you'll be getting the molality of the solution. Again, done and dusted. Yeah? Am I clear, people? Am I clear with this? All these results you have to remember, people. All these results you have to remember. See, look at this question. It is the revision of all the concentration terms. But before solving this particular question, we are going to cover two more concentration terms, which are very simple. Okay? Let's try to cover a few more concentration terms, which are pretty much simple. See, there is a concentration term called as parts per million. ppm. For example, ppm of solute. ppm of solute. Okay. How do we define ppm of solute? It is simply defined as that mass of solute in grams, which is present in 10 raised power 6 grams of solution. That mass of solute in grams, which is present in 10 raised power 6 grams of solution. So, if for example, in 10 raised power 6 grams of solution, there are 100 grams of solute, what does that mean? That means ppm of solute is 100. If in 10 raised power 6 grams of solution, there are 50 grams of solute, what does that mean? That means ppm of solute is 50. If in 10 raised power 6 grams of solution, there are x grams of solute, what does that mean? ppm of solute is x. In short, that mass of solute in grams which is present in 10 raised power 6 grams of solution, what do you call that as? You call that as parts per million of solute. What do you think its formula will be? Simple. Mass of solute in grams divided by the mass of solution in grams multiplied by 10 raised power 6. This is how you calculate ppm of solute. Similarly, if I ask you to calculate ppm of solvent, you should be in a position to do this as well. It is mass of solvent in grams divided by the mass of solution in grams multiplied by 10 raised power 6. Multiplied by 10 raised power 6. Now, people, this particular result you can convert in a different form as well. You can write it like this. Mass of solute in grams divided by the mass of solution in grams multiplied by. Instead of 10 raised power 6, let's write 100 in 10 raised power 4. If you wrote it as 100 in 10 raised power 4, what do we call this particular term? This particular term is called as weight by weight percentage of solute multiplied by what? Multiplied by 10 raised power 4. This is one more result of calculating ppm of solute. In some questions, they'll give you directly weight by weight of solute. Just multiply that with 10 raised power 4. Get the ppm of solute. Nothing else you have to do. Yeah? Similarly, I can convert this particular equation in a different form. I can write it as weight by weight percentage of solvent multiplied by 10 raised power 4. Yeah? Simple and basic. Simple and basic, people. Right? For example, if sometimes I write 20 ppm of solute, what does it mean? What does it mean? Try to decode this statement. 20 ppm of solute. It means that 20 grams of solute are present in 10 raised power 6 grams of solution as per the definition. Nothing else. Nothing else. Right, people? Similarly, there is one more simple concentration term which I believe you should be knowing. What is that? That is your ppb of solute, parts per billion. The last concentration term, that is your parts per billion. Let me write parts per billion of solute. Let me write parts per billion of solute, ppb of solute. How do you define it? How do you define it, people? It is similar. Instead of 10 raised power 6, you have to write 10 raised power 9. That's all. Instead of 10 raised power 6, you have to write 10 raised power 9. That's it. So I'll be writing. It is defined as the mass of solute in grams, which is present in 10 raised power 9 grams of solution. Which is present in 10 raised power 9 grams of solution. So I can use the result. Parts per billion of solute is equal to, this will be mass of solute in grams divided by the mass of solution in grams multiplied by 10 raised power 9. Multiplied by 10 raised power 9. This is ppb of solute. Similarly, if I ask you, what about ppb of solvent? ppb of solvent will be equal to mass of solvent in grams divided by the mass of solution in grams multiplied by 10 raised power 9. Well, if I ask you, can you convert these results into different form as well? Can you convert them? Can you convert them? Yes, you can convert them. You can say ppb of solute is nothing but weight by weight percentage of solute multiplied by 10 raised power 7. Similarly, here it's going to be weight by weight percentage of solute. Sorry, weight by weight percentage of solvent multiplied by 10 raised power 7. And one result at the end, and that's it. I can write ppb of solute is equal to ppm of solute multiplied by 10 raised power 3. Okay, so these were all your concentration terms, people. Normality I don't teach here. Normality I teach in redox reaction. Let me tell you that. Normality I do not teach here. Normality I'm going to teach you in the redox reaction, not here. Okay, just to keep you updated, just to let you know. All right, since we have covered all the concentration terms, people, don't you think you should be able to solve this one? Don't you think you should be able to solve this one? Look at it carefully. Look at it carefully, people. Break will be at 9 p.m. Okay, break will be at 9 p.m. As per the question, people, for a 1.5 molar NaOH aqueous solution. So we have got a solution whose molarity is given to us as 1.5. Okay. Solute is NaOH. Therefore, molar mass of solute will be 40 grams per mole. Solvent is your water. Molar mass of solvent will be 18 grams per mole. Density of solution is also given to us. Okay. Calculate all this stuff. The first thing, molality. The first thing, molality. Can you calculate molality here? Easily, guys, easily. I give you already one result. Molality is equal to 1000 multiplied by molarity divided by 1000 multiplied by density of solution minus molarity multiplied by molar mass of solute. Look here. Molarity is given. Molarity is given. Molar mass of solute, you know. Density of solution, you know. Put the values. Get the value of molality. Done. Nothing else. Nothing else. First question is done. Second question, calculate weight by weight of solute. You know, molarity is equal to 10 multiplied by weight by weight percentage of solute multiplied by density of solution divided by the molar mass of solute. As per the question, molarity is given, density of solution is given, molar mass of solute is given. Can't you calculate weight by weight of solute from here? Yes, we can do that. Just a matter of calculation, nothing else. Can be solved. Can be solved, right? Can be solved. Look at the next one. Weight by volume percentage of solute. Since we calculated weight by weight of solute here, already I've told you weight by volume percentage of solute is basically equal to 10 multiplied by weight by weight by volume percentage of solute is always equal to weight by weight percentage of solute multiplied by density of solution in grams per ml. In the beginning only I've given you this result. In the beginning only I've given you this. Weight by weight, you have to calculate from here. Multiply that with density of solution. Get the weight by volume. Done and dusted. What is the next thing? Mole fraction. Mole fraction. Already one result is given. Molality is equal to chi2 multiplied by 1000 divided by 1 minus chi2 multiplied by m1. This is given. Well, this is given. I mean given. Given means we have calculated the value of m. m1 we know. So one equation, one unknown. So chi2 easily you can calculate after solving this equation. And once you get chi2, you can easily calculate chi1 because you know chi1 plus chi2 is always equal to 1. Am I clear, people? Am I clear? Say it in the chats once. Am I clear? Everybody? Everybody in the chats, all clear? Break will be at 9 p.m, not now. 9 p.m, 9 p.m, 9 p.m. Wait, we'll complete the concentration terms then. It is not going to take a lot of time. It is not going to take a lot of time, guys. Relax. Let's have a look on molarity of dilution. Molarity of dilution. Okay. Molarity of dilution. Before discussing molarity of dilution, I told you a few minutes back, molarity of the solution is equal to number of moles of solute divided by volume of solution in liters, right? So can't I say number of moles of solute is basically equal to molarity of the solution multiplied by volume of solution in liters? I can say something like this, right? So what technically that means? If you know the molarity of the solution, if you know volume of solution in liters, so molarity of the solution multiplied by volume of the same solution in liters, what does that give me? That gives me moles of solute, right, in the solution. Similarly, in the same formula, if I use volume of solution not in liters, in milliliters, what do I get? I'll be getting number of millimoles of solute. I'll be getting number of millimoles of solute, right? I'll be getting number of millimoles of solute. What is the difference between moles and millimoles? Millimoles are nothing but, millimoles are basically moles multiplied with 1000. Moles multiplied with 1000 gives us millimoles. That's all. That's all, people. That's all, right? Try to understand now. Try to understand what exactly I'm going to say. First of all, if I ask you what is dilution, how do we define the term dilution? Dilution is nothing but, it is defined as the addition of extra solvent. The addition of extra solvent in a solution to modify its concentration. Addition of extra solvent into a solution to modify its concentration. What does that mean? See guys, imagine this is the container. For example, in this particular container, we have got, let's say, HCl aqueous solution. There is HCl aqueous solution in this container, right? Solution means there is solute as well as solvent here. Imagine that molarity of this solution is M1. Volume of this solution is V1. Imagine that molarity of this solution is M1. Volume of this solution is V1. Okay? If I ask you, how many moles of solute are there in this solution right now? Number of moles of solute. How do we calculate moles of solute? Molarity of the solution multiplied by volume of solution, right? So, how many moles of solute are here in this particular container right now? Solute is your HCl here. So, how many moles of HCl are there in the container? You'll directly say molarity multiplied by volume in liters. This term gives me the moles of solute. This term gives me the moles of HCl which are there in this solution, right? Imagine that you are adding extra solvent here. Imagine that you are adding extra solvent here. My dear students, when you will be adding extra solvent, in the same solution, what is going to happen? What's going to happen? When you will be adding extra solvent in the same solution, what is going to happen? Still the solution is going to be the same. It's going to be HCl aqueous solution only. But will the volume of the solution now be V1 or V2? I would say volume of the solution would have increased. Initially, the volume of the solution was V1. Now you're introducing extra solvent. Now the volume of the solution is, for example, V2. If the volume of solution is V2, you know, molarity depends on volume. You are increasing the volume of solution. That means you are decreasing the molarity of the solution. If the initial molarity of the solution was M1, now the molarity of the solution will be M2. Now the molarity of the solution will be M2. Right? Now the molarity of the solution will be M2. Try to understand carefully, guys. The solution which I took, right? Its molarity was M1. Its volume was V1. How many moles of solute were here in this container? M1 multiplied by V1. You are introducing extra solvent here. When you will be introducing extra solvent here, what is happening to the volume of solution? Volume of solution would have increased. Therefore, molarity of the solution would have decreased. Now the volume of the solution is V2. And imagine molarity of this solution is M2. So if I ask you, how many moles of solute are here in this container now? Number of moles of solute in this container. It is just going to be M2 multiplied by V2. Okay? Tell me whether these are the moles of solute in the container before dilution or after dilution. These are the moles of solute in the container before dilution. These are the moles of solute present in the container after dilution. These are the moles of solute in the container before dilution. These are the moles of solute in the container after dilution. After dilution. Tell me one thing. What did we do? We just added solvent. We just added extra solvent. Did we do anything with the solute? No. Did I take any solute out from here? No. Did I add some extra solute here? No. I did nothing with solute. So I can use one simple concept. The concept is going to be number of moles of solute present in the container before dilution. It has to be equal to number of moles of solute present in the container after dilution. Right? How many moles of solute we had in the beginning before dilution? It used to be M1V1 is equal to, this is going to be M2V2. This formula is something which you call as dilution formula. This is what you call as dilution formula. This is what you call as dilution formula, right? This is what you call as dilution formula. Okay. Now we will try to understand one more thing. If they ask you, calculate the volume of extra solvent which we added. Volume of extra solvent added. Calculate the volume of extra solvent added. How you guys are going to calculate the volume of extra solvent added? See, the solution which we took in the beginning, its volume was V1. Now you added extra solvent. Now the volume of the solution becomes V2. So, how much volume of extra solvent we added? It's going to be final volume of the solution minus initial volume of the solution. This is going to give you the volume of extra solvent added. Okay? This is going to give you the volume of extra solvent added. I believe this is clear to everyone. Yeah, I believe this is clear. Give this question a try. Kill it. The question is how much water should be added to 200 ml of HCl solution. So you have got a solution of HCl here. You have got a solution of HCl here whose molarity is 2. Volume of this solution is 200 ml. Now, as per the question, you are adding some extra water here. So extra solvent you are adding. Now, after the addition of extra solvent, what is happening? After the addition of extra solvent, what is happening exactly? After the addition of extra solvent, molarity of the solution now becomes, since we are doing dilution, due to dilution, molarity decreases. If the initial molarity is 2, final molarity as per the question is 0.2. Okay, let's say volume of this solution now is V2. Before the arrow part, this is the scenario before dilution. This is the scenario after dilution. So use the dilution formula. Dilution formula says that M1V1 is nothing but M2V2. Simple. What is M1? 2. What is V1? 200. M2? 0.2. Calculate V2 from here. V2 will be simply 2000 ml. Since we used volume in ml, therefore we'll get the volume in ml too. Right? So this is the final volume of the solution. But as per the question, am I supposed to calculate final volume? No. I'm supposed to calculate volume of extra solvent added. So what is the volume of extra solvent added? It is going to be equal to V2 minus V1. What is V2? 2000. What is V1? 200. 2000 minus 200 comes out to be what? 1800 ml. So what is meant by this 1800 ml? I would say 1800 ml extra solvent has been added into the container. Then only its molarity has changed from 2 to 0.2. Yes. Right, people? Is it clear? Is it clear? Is it clear? Quickly in the chats. Let's have a look on molarity of mixing. Let's have a look on molarity of mixing. It's again pretty much simple. I'll be discussing this molarity of mixing of non-reacting solutions in 2 cases. I'll be discussing this molarity of mixing of non-reacting solutions in 2 cases. Understand both the cases one by one. Understand both the cases one by one, people. Understand both the cases one by one. All right. For example, this is the container that contains your HCl aqueous solution. This is one more container. It contains HCl aqueous solution. Let's assume molarity of this solution is M1. Let's assume volume of this solution is V1 liters. For example, molarity of this solution is M2. Volume of this solution is V2 liters. If I add them, if I mix them, when I mix them in this final container, what do I get? Since this was HCl solution, this is also HCl solution, right? So you are mixing them in final container. So you are getting a final solution of HCl. You are getting a final solution, or you call it as the resulting solution of HCl. You call this as the resulting solution of HCl. Now the final solution of HCl which we get, assume its volume is VR. Assume its volume is VR, right? If this resulting solution is ideal, which I'll tell you afterwards, what is ideal, non-ideal? First of all, remember, if this resulting solution is ideal, then its volume has to be equal to sum of these 2 volumes, V1 plus V2. Let's assume molarity of this resulting solution will be MR. Okay. My dear students, tell me how many moles of solute are here in this container? You'll say M1V1. How many moles of solute are there in this container? You'll say M2V2. If I add them up, what do I get? I'll say these are the total moles of solute present in the first 2 containers before mixing. These are the number of moles of solute present in the first 2 containers before mixing. Now, after mixing, the scenario is different. After mixing, the solution which we got, its molarity is MR, volume is VR. So, MR multiplied by VR. This is going to give me the number of moles of solute in this final container before mixing or after mixing. It's going to be after mixing. Molarity multiplied by volume in liters. That gives me moles of solute. That gives me moles of solute, right? So, before mixing, these were the moles of solute present in the first 2 containers. After mixing, moles of solute in this final solution is MR multiplied by VR. Now think logically. Think logically. What did we do? We just mixed these two solutions in this container. We just mixed these two solutions into this particular container. So can I say whatever solute was there in the first container plus whatever solute was there in the second container, all that solute would have reached here? Right? Imagine there were 2 moles of solute here. Imagine there were 3 moles of solute here. Since you are mixing these two in the final container, so all those 2 plus 3, 5 moles of solute will be there in this container. Yeah? Correct, people? So I can say number of moles of solute before mixing, it has to be equal to number of moles of solute after mixing. Simple logic. Nothing else. Nothing new. Nothing difficult. Nothing new, nothing difficult. So, the number of moles of solute before mixing is what? M1V1 plus M2V2. Number of moles of solute after mixing is what? MR multiplied by VR. So, from this particular result, you can calculate the value of MR, which is nothing but M1V1 plus M2V2 divided by what? Divided by VR. VR is nothing but V1 plus V2. So, this is the expression by means of which you can calculate the molarity of this final solution. Yeah? Perfect, people. Is it clear? Let me know once the chats. This is the result here by means of which we are going to calculate molarity of the final solution here. Let me know quickly in the chats if this is super clear. Let me know quickly in the chats if this is super clear. Then only I'll go to case 2. Then only I'll go to case 2. Quick, everybody. Everybody in the chats. Now people understand what the case 2 is all about. It's again simple. Right now I'm not just taking 2 containers. Let me take 3 containers in the beginning. And let me take a bigger container here. Okay? Imagine you have got HCl aqueous solution here. Imagine again you have got HCl aqueous solution here. So are these reacting ones or non-reacting ones? These are non-reacting solutions. Imagine this container contains pure water, solvent only. Right? Okay. For example, molarity of this solution is M1. Volume of the same solution is V1. Molarity of this solution is M2. Volume of this solution is V2. Volume of this water in the container, I'm representing with VH2O. Right? Now, how many containers did I take here? I took 3 containers. In the first container, we have got solution. In the second container, we have got solution. In the third container, we have got pure solvent. There is no solution in the third container. It is just the pure solvent. There is no solute here. Right? So, if I ask you, how many moles of solute are here in this container? You will say M1 multiplied by V1. How many moles of solute are here in this container? M2 multiplied by V2. Is there any solute here? There is no solute here. So, before mixing, since I have not mixed all these 3 yet, I have not mixed them yet. So, how many moles of solute do we have in all the containers before mixing? Before mixing, these are the total moles of solute which we have. Before mixing, these are the total moles of solute which we have. Correct? Right, people? Now, I'm going to mix them up. I'm going to mix them in this container. What do I get at the end? I'll be getting the final solution, which I call as the resulting solution. This is the resulting solution of HCl here. Okay? What will be the volume of the resulting solution? VR, which is nothing but V1 plus V2 plus volume of water added. Let's assume molarity of this solution, final solution is MR. Okay? Let's assume molarity of this solution is MR. Now tell me one thing. Molarity multiplied by volume, that gives me number of moles of solute. Before arrow, this was the case of before dilution. Sorry, this was the case of before mixing. This is the case of after mixing. So after mixing, if I ask you, how many moles of solute do we have? How many moles of solute are here in this container after mixing? You'll just say MR multiplied by VR. MR multiplied by VR. That gives me the moles of solute here in this container after mixing. Right? Right, people? Now, what is the basic principle which I'll use here? Again, can I say whatever solute was here, whatever solute was here, all that solute would have finally reached here because you are mixing them up in this final container. You are mixing all these three containers into this final container. So whatever solute was here, plus whatever solute was here, here you did not have any solute. It was pure solvent. All that solute is reaching here in this final solution. So my concept here is number of moles of solute before mixing equal to number of moles of solute after mixing. I believe this is clear. Now tell me, how many moles of solute do we have before mixing? It is M1V1 plus M2V2. How many moles of solute do we have after mixing? It is Mr multiplied by Vr. Vr is nothing but V1 plus V2 plus volume of H2. Now, my dear students, from this particular equation, question is asked. You'll be asked to calculate this particular term. You'll be asked to calculate this particular term. How much volume of water you took in the beginning. Okay, that's the question which will be asked to you. Is this particular scenario clear? Is this particular scenario clear, people? Solve this simple and basic question. You should be in a position to solve this question. As per the question, this is my first container. This is my second container. And this is my third container. In the first container, we have got HCl aqueous solution is mixed with. In the second container also, we have got HCl aqueous solution. Molarity of this solution is given to me as 3. Volume of this solution is given to me as 200 ml. Okay. Molarity of this solution as per the question is given to me as 2. Volume of this solution is given to me as 300 ml. What exactly are we doing? We are mixing them up and we are making a final solution, a resulting solution of HCl aqueous. Right? We are supposed to calculate molarity of the resulting solution. We are supposed to calculate molarity of the resulting solution. Volume of the resulting solution as per the question is made up to what? Final volume of the resulting solution is made up to 1500 ml. Do you understand this? Do you understand this, people? We are mixing them up and at the end, as per the question, final volume of the solution is made up to 1500 ml. So, is this the case of mixing or dilution? This is the case of mixing right here, right? So, use the mixing formula. M1V1 plus M2V2 is equal to Mr multiplied by Vr. So, what will be Mr here? Mr will be M1V1 plus M2V2 divided by Vr. As per the question, M1 is given, V1 is given, M2 is given, V2 is given, Vr is given. All the parameters are given. Put it here, get the value of Mr. Mr is going to be the molarity of the resulting solution. And people are saying the value is coming out to be 0.8. All right. So the final molarity of the resulting solution is coming out to be what? 0.8 molar. I believe this is clear. I believe this is clear, people. Look at this one. Look at this one. Will you be able to solve this one on your own? The volume of water that must be added, a mixture of 250 ml of 0.6 molar HCl and 750 ml of 0.2 molar HCl to obtain 0.25 molar resulting solution. Is this related to case 1 or case 2? Quickly in the chat. Is this related to case 1 or case 2? I want you to tell me right now. Is it the case? Is it resembling with case 1 or case 2? Everybody. Quickly, people. Perfect. Yes, it is resembling with case 2. So what is the formula which you'll use here? What is the formula which you'll use here? So the question is like this. This is one of the containers. This is one more container. This is one more container. And this is one final container. In the first container, you have got HCl aqueous solution, whose molarity is 0.6, whose volume is 250 ml. This is again one more HCl aqueous solution, whose molarity is 0.2, whose volume is 750 ml. At the same time, in the third container, you are taking water as well. Let's say you have taken V3 ml of water here in the third container. Now you are mixing all these three into this final container. So what do you get? You get resulting solution of water. Sorry, you get resulting solution of HCl. Molarity of this resulting solution as per the question is nothing but 0.25. Volume of this resulting solution will be, volume of the resulting solution will be V1 plus V2 plus V3. V1 is 250. V2 is 750. So this plus this makes it 1000. So 1000 plus V3. 1000 plus V3. Right? So is it resembling with case 1 or case 2? Definitely it's resembling with case 2. Right? And my dear students, you know what we discussed few minutes back. M1V1 plus M2V2 has to be equal to MR multiplied by VR. Instead of VR, I'll write 1000 plus V3. Right? Look at all the things. This is given to us. This we know, this we know, this we know, this we know. We can calculate V3 from here. So V3 has to be equal to, when you solve it, it will come out to be 200 ml. It will come out to be 200 ml. So basically, 200 ml of water should be added with this mixture. Then only molarity of the final solution comes out to be 0.25. Yes? Someone is saying, sir, first one is wrong. What do you mean? First one is wrong. Approach is correct. Maybe you can check the calculation. What is the calculation? This is 600 plus 600 is 1200. 1200 divided by 1500. That is 12 by 5. 12 divided by 5. 3435. 4 by 5. 4 by 5 is 0.8. It's correct. Not wrong. It's correct. Okay. Got it, people? Look at this one. Look at this particular question. Quickly. Look at this particular question. Quickly, people. Will you be able to solve this one? 29% weight by weight solution of HCl, whose density is given, occupies 8 ml volume. Occupies 8 ml volume. Calculate the final volume of the solution whose concentration becomes 0.4 molar on dilution. Question is based on dilution. Look here. You have got a solution here. Which solution is it? It is HCl aqueous solution. What is the volume of this particular solution? As per the question, volume of the solution is 8 ml. Volume of the solution is 8 ml. Now, in this solution, weight by weight percentage of solute is given. How much? 29.2. Density of this solution is given. How much? 1.25 grams per ml. Can you let me know what will be the molarity of this solution? 10 multiplied by weight of solute, density of solution, divided by molar mass of HCl, molar mass of solute, 36.5. Can you solve it and let me know what is the value of M which comes out to be after solving this equation? What is the value of M which we get here? Tell me quickly in the chats. What is the value of M which we get here after solving? Quick, quick, quick. Quick, people. What is the value of M which we get here after solving? Quickly, quickly. People are saying it's coming out to be 10. All right. So the solution which we have, its volume is given to me as 8 ml. Its molarity I calculate as 10 molar. Right? Now, what are we doing? We are doing dilution. Dilution means we are adding extra solvent. When we shall be adding extra solvent, this is the final solution which we get after dilution. This is the final solution which we get after dilution. And as per the question, molarity of the final solution is 0.4. We have to calculate final volume of the solution. Since the question is based on dilution. Okay, if the question is based on dilution, I'll be using the dilution formula. M1 V1 has to be equal to M2 V2. So M1 multiplied by V1. So 8 multiplied by 10 comes out to be 80 is equal to M2 V2 0.4. And here you can calculate V2. V2 comes out to be 200 ml. So final volume of the solution which I was supposed to calculate, it came out to be 200 ml. DPP of solution chapter, I'll share once the chapter is complete, right? Do not spam. Do not spam. Perfect, guys. All the things clear? Now there is one more thing left here in concentration terms. What is that? That is what happens when we mix the non-ideal solutions. What are non-ideal solutions? We have to discuss that in detail after like 1-2 hours. Okay? Just one concept I would need here. Perfect. Rest of the things in detail we'll study in this chapter itself, like after 1-2 hours. Okay? This is again important. See, guys. Imagine that this is a liquid in the container. This is one more liquid. Imagine that this is liquid 1 in the container. Imagine that this is liquid 2 in the container. For example, its volume is V1. For example, its volume is V2. Let's say its mass is W1. Let's say its mass is W2. Mass of liquid 1 is W1, mass of liquid 2 is W2. Now, for example, you are mixing these two liquids. Imagine that you are mixing these two liquids. When you'll be mixing these two liquids, you'll be getting a final solution. A final solution, right? Let's assume volume of this final solution is VR, right? Now, there are two possibilities. There are two possibilities. Either VR will be equal to V1 plus V2 or VR won't be equal to V1 plus V2. This particular solution for which VR will be equal to V1 plus V2, that is the case of ideal solution. And when VR won't be equal to V1 plus V2, you'll be calling it as non-ideal solution. In detail, we'll be discussing non-ideal solutions after some time. Right now, this is the only point which I need here. Right now, this is the only point which I need here. Right? Right now, this is the only point which we need here. Okay? Now, see my point. See my point. If VR is equal to V1 plus V2, I'll be calling this ideal. If VR is not equal to V1 plus V2, that is the property of the non-ideal solutions. My dear students, irrespective of the fact whether the resulting solution is ideal or not, mass of the resulting solution will be always equal to W1 plus W2. Does not matter whether the final solution is going to be ideal or non-ideal. This is valid for ideal as well as non-ideal. Irrespective of the fact whether the resulting solution is ideal or not, its mass will be always equal to W1 plus W2. Where do I use this concept? Have a look. Look at this particular question. Look at this particular question, guys. Look at this particular question. As far as this question is concerned, see, we have got ethyl alcohol here in this container, C2H5OH. Its volume is given to me as 15 ml. Okay. Its density is given to me as 0.792 grams per ml. Perfect. Here in the second container, we are given with water at 4 degrees centigrade. Okay. Volume of this water over here, I'm taking as 15 ml as per the question. And you know, density of pure water at 4 degrees is nothing but 1 gram per ml. Now, as per the question, you are mixing these two liquids. You'll be getting a final solution, a resulting solution, right? As per the question is concerned, the density of resulting solution will be equal to. The density of the resulting solution is 0.924 grams per ml, right? In the question, they are mentioning that the resulting solution is non-ideal. If the resulting solution is non-ideal, one thing is clear. If the resulting solution is non-ideal, one thing is clear. Volume of the resulting solution won't be equal to V1 plus V2. In the question, they are mentioning that the resulting solution is non-ideal. What does that mean? That means volume of the resulting solution won't be equal to V1 plus V2. Understand one thing. I told you already one thing. I told you in case of non-ideal solutions, volume of resulting solution is not equal to V1 plus V2. volume of resulting solution is either greater than V1 plus V2 or volume of resulting solution is less than V1 plus V2, right? And people just think over it logically. If volume of the resulting solution will be greater than V1 plus V2, at that point of time, we say expansion has happened. This is the case of volume expansion. If volume of the resulting solution is less than V1 plus V2, at that point of time, we say volume contraction has happened. At that point of time, we say volume contraction has happened, right? At that point of time, we say volume contraction has happened. Now look here. They're asking us to calculate contraction in volume. That means one thing is clear, volume of a resulting solution will be less than V1 plus V2. Now, how much volume contraction has happened? Let's try to understand. Hey guys, tell me one thing. Density of liquid 1 will be equal to mass upon volume, correct? So what is the mass of this liquid? W1, D1 into V1. D1 multiplied by V1. So what is D1 multiplied by V1? Can you check it out? This multiplied by this. I think it will be 11.8 grams. This multiplied by this, it will be 11.8 grams. W2 will be equal to this multiplied by this, which will be 15 grams. So mass of liquid 1 is 11.88. Mass of liquid 2 is 15 grams. Irrespective of the fact whether the resulting solution is ideal or not, it is going to be W1 plus W2. It is going to be W1 plus W2, this plus this, which comes out to be 26.88. Correct? Now, density of resulting solution is equal to mass of resulting solution divided by volume of resulting solution. Or I can say volume of resulting solution is equal to mass of resulting solution divided by density of resulting solution. What is the mass of resulting solution? 26.88 divided by, what is the density of resulting solution? 0.924. When you solve this, the value comes out to be 29 ml. When you solve this, the volume comes out to be 29 ml. So what is this 29 ml? This is the volume of the final solution. Volume of the final solution is coming out to be 29 ml, people. Do you understand this? Volume of the final solution is coming out to be 29 ml. What should have been the volume of the resulting solution? Volume of the resulting solution VR should have been 15 plus 15, 30. But what is the volume of the resulting solution? 29 ml. Should have been 30, but it is 29. So has volume increased or decreased? From 30 to 29, it has decreased. It has decreased. So, how much volume has decreased? It should have been 30, but it's 29. So, decrease in the volume is 1 ml. So, contraction in volume, decrease in the volume, which I was supposed to calculate, is nothing but 1 ml. Am I clear with this? Am I clear with this, people? So, 1 ml is here, the decrease in the volume. Got it? All clear? All clear? Perfect. Perfect, people. Now, there is one more important stuff which is asked, that is calculation of concentration of ions. Calculation of concentration of ions. This is the last topic before the break. And with this, we'll be done with the concentration terms. Understand, this is again important. My dear students, I told you already. One thing I told you already. Molarity multiplied by volume of the solution in liters. It gives me moles of solute. Molarity multiplied by volume of solution in ml. It gives me millimoles of solute. As per the question, we have got 100 ml of 0.1 molar BaCl2. And we are introducing this BaCl2 in water. Now just tell me one thing. When BaCl2 is introduced in water, how will it undergo dissociation? Ba di positive aqueous plus 2 times Cl negative aqueous. When BaCl2 is introduced in water, it will break down into its ions. Ba di positive, 2 times Cl negative. Tell me one thing. In BaCl2 aqueous solution, which one is solute? BaCl2 is solute. The solution which we have, We know its molarity, we know its volume. And you know, molarity of the solution multiplied by volume of solution in ml. This multiplied by this. It gives me what? As per this formula. It gives me number of millimoles of solute. Solute is BaCl2. So how many millimoles of BaCl2 are we introducing in water? Molarity multiplied by this. So it comes out to be 10. So we are introducing 10 millimoles of BaCl2 into water. Right? So initially this will be 0, this will be 0. Now whatever BaCl2 you are introducing in water, assume that it got 100% dissociated into its ions. So I'll be left with nothing. 0 millimoles of BaCl2 at the end. Now 1 mole gives 1 mole. 10 millimoles will give 10 millimoles. 1 mole gives 2 moles. So 10 millimoles would have given 20 millimoles. So I got to know just one thing. I got to know one thing. Millimoles of Ba dye positive in the final solution is equal to 10. I got to know millimoles of Cl negative in the final solution, that is 20. Now think logically, guys. Millimoles divided by volume of solution in ml, that gives you molarity of ion. I would say molarity of ion is nothing but number of millimoles of ion in the solution divided by volume of solution in ml, or molarity of ion. If you want to use this result, you can say number of moles of ion in the solution divided by volume of solution in liters. These are the two ways by means of which you can calculate molarity of ion. Since you got millimoles of both ions, when we divide millimoles of ion by the total volume of the solution in ml, you get molarity of ion. Now understand. If I ask you the final solution which we got in the final solution, if I ask you what is the molarity of Ba dye positive, molarity of Ba dye positive will be equal to millimoles of Ba dye positive in the final solution divided by total volume of the solution in ml. Value comes out to be 0.1 molar. Millimoles of Cl negative in the final solution will be equal to, concentration of Cl negative in the final solution will be equal to millimoles of Cl negative divided by total volume. The value comes out to be 0.2 molar. Yes. Now look at this particular one. From here, things will be very, very, very clear. My dear students, this is the solution which we have. In this solution, this Na3PO4 is our solute. We are introducing solute into water. When you should be introducing Na3PO4 into water, assume it would have got 100% dissociated into its ions. Its ions are 3 times Na positive plus PO4 tri-negative aqueous. Right? Just tell me one thing. The solution which we have, are we given with its molarity? Yes. Are we given with its volume? Yes. Is volume of the solution given in ml? Yes. Molarity multiplied by volume in ml. That gives me the millimoles of solute. Solute is Na3PO4. So how many millimoles of Na3PO4 we have in the beginning? This multiplied by this. So 10 millimoles. Initially, this will be 0. This will be 0. Now, assume this Na3PO4 have got completely dissociated into its ions. So I'll be left with 0 millimoles of this. Now, 1 mole gives 3 moles. 10 millimoles are going to give us 30 millimoles. 1 mole gives 1 mole. So 10 millimoles are going to give us 10 millimoles. So my dear students, we got to know one important thing. We got to know the millimoles of Na positive and the millimoles of PO4 tri-negative in the final solution. That's something which I wanted. Because once I know the millimoles of ions, I divide the millimoles of ions with the total volume in ml. I get concentration of ions. Yeah? So I would say concentration of Na positive in the final solution will be equal to millimoles of Na positive divided by total volume in ml. The value is 0.3. What is the concentration of PO4 tri-negative in the final solution? It is equal to millimoles of PO4 tri-negative divided by total volume in ml. The value comes out to be 0.1 molar. Got it? Simple. Simple, people. So just let me summarize it quickly. Whenever you are supposed to calculate the concentration of ions in the solution, first get the millimoles of ions in the final solution. Once you get the millimoles of ions in the final solution, divide the millimoles of ions with the total volume of the solution in ml. You'll be getting the concentration of ion in the final solution. Am I clear? Am I clear? Tell me the answer of this question. You've got 100 ml of 0.1 molar HCl aqueous. You're mixing that with 100 ml of 0.2 molar H2O4 aqueous. So you're mixing two. You're mixing two solutions into one container, right? So the final solution which we get, we need to calculate the net H positive ion concentration in the final solution. We need to calculate molarity of H positive in the final solution. Well, you know, people, you know, in order to calculate molarity of an ion, what do we need? We need millimoles of the ion in the final solution. Once we get the millimoles of ion in the final solution, we divide it with the volume of the solution. Final volume of the solution in ml. That's all. We are done. We are sorted. Now check it out. First of all, tell me how HCl would have got dissociated. H positive plus Cl negative. Initially, if I ask you how many millimoles of HCl do we have, this multiplied with this, 10 millimoles. This would be 0, this would be 0. Now, HCl, completely dissociated, nothing left. 1 mole gives 1, 10 gives 10. 1 gives 1, 10 gives 10. So we got millimoles of H positive and Cl negative coming from HCl, right? Similarly, we have got H2SO4 as well. How H2SO4 undergoes dissociation? This is how it dissociates into its ions. How many millimoles of H2SO4 we have? This multiplied with this, 20. So initially 0, 0. Now this is 0. 1 gives 2, 20 gives 40. 1 gives 1, 20 gives 20. So now here we got the millimoles of H positive and SO4 dinegative coming from H2SO4. Now imagine you're introducing all of this. Everything is happening in the final solution. So in the final solution, which contains this as well as this, in the final solution, how many total millimoles of H positive do we have? How many total millimoles of H positive are there in final solution when you mix them both? How many millimoles of H positive are coming from HCl? 10. How many millimoles of H positive are coming from H2SO4? 40. So 40 plus 10 comes out to be 50. So in total, in the final solution, there are 50 millimoles of H positive. Since you got the millimoles of H positive in the final solution, so what is the net H positive ion concentration? Millimoles of H positive in the final solution divided by total volume. Total volume is 100 plus 100. That's 200, right? So it's 1 upon 4. 5154, right? So it is 0.25. So this is the molarity. This is the concentration of H positive in the final solution. Am I clear? Am I clear, people? Is there any full form of GOAT? GOAT means greatest of all time. Yeah. Am I clear, people? Is that clear? So here you got to know one thing. When you mix the solutions, how do you calculate the concentration of ions in the final solution? One nice question I'm going to give you. Let me see if you can solve this or not. This is one nice question. Look at the question carefully, guys. You have got a container. The container contains an aqueous solution. Aqueous solution. This aqueous solution, it contains NaCl. It contains CaCl2. It contains NH4Cl as well. The aqueous solution contains NaCl, CaCl2 and NH4Cl as well. Okay? As per the question. As per the question. Now, if you look carefully, look at this statement, 5.85% weight by volume of NaCl. What does that mean? That means 5.85 grams of NaCl are present in 100 ml of aqueous solution. Are present in 100 ml of aqueous solution. Similarly, 22.2 grams of CaCl2 are present in 100 ml of same 100 ml of aqueous solution. Similarly, 5.35 grams of NH4Cl are present in same 100 ml of aqueous solution. Right? Do you see how do I decode things? This means you're got an aqueous solution containing NaCl, CaCl2 and NH4Cl, correct? This means 5.85 grams of NaCl are present in 100 ml of the aqueous solution. Similarly, 22.2 grams of CaCl2 are present in 100 grams of aqueous solution. Similarly, 5.35 grams of NH4Cl are present in the same 100 ml of aqueous solution. Now tell me, how many moles of NaCl are present in 100 ml of aqueous solution? How do you convert mass into moles? Given mass, divide by its molar mass. Its molar mass is 58.5. So 5.85 divided by 58.5. So 0.1. Given mass, divide by its molar mass. Molar mass is 111. So 0.2 moles. 5.35 divided by its molar mass. 53.5. 0.1. So I can say 100 ml of the solution contains 0.1 moles of NaCl, 0.2 moles of CaCl2, 0.1 moles of NH4Cl. Right? Now, if I ask you, what about the moles of Cl negative coming from NaCl? What about the moles of Cl negative coming from NaCl? How NaCl would have got dissociated? Na positive plus Cl negative. So 1 mole of NaCl gives 1 mole of Cl negative. Therefore, 0.1 moles of NaCl would have given 0.1 moles of Cl negative. So, moles of Cl negative coming from NaCl are 0.1. Moles of Cl negative coming from CaCl2. How CaCl2 undergoes dissociation? CaCl2 gives Ca di positive plus 2 times Cl negative. So 1 mole of CaCl2 gives 2 moles of Cl negative. Therefore, 0.2 moles of CaCl2 gives 2 into 0.2. 0.4 moles of Cl negative. Right? Similarly, moles of Cl negative coming from NH4Cl in the final solution. 0.1 only, because NH4Cl gets dissociated as NH4 positive plus Cl negative. Correct? Now, if I ask you, how many total moles of Cl negative we have here? This plus this plus this, 0.6. So, can I say 100 ml aqueous solution? 100 ml aqueous solution contains 0.6 moles of Cl negative? Absolutely. Therefore, 1 ml aqueous solution should contain 0.6 divided by 100 moles of Cl negative. Yes. Can I say 1000 ml solution should contain 0.6 divided by 100 multiplied by 1000 moles of Cl negative? It comes out to be how much? This cancel. So it contains 6 moles of Cl negative. Just look at this carefully. I would say 6 moles of Cl negative. 6 moles of Cl negative are present in 1000 ml of solution. 6 moles of Cl negative are present in 1 liter of solution. And as per definition, moles of Cl negative present in 1 liter of solution, that gives you molarity of Cl negative. So what is the molarity of Cl negative? What is the concentration of Cl negative in the final solution? It is 6 molar. This is something I was supposed to calculate as far as the question is concerned. Say yes or no in the chats if it is clear. Say yes or no in the chats if it is super clear. Right, people? All clear? Did you understand this question? Did you understand this question? I hope this is clear. So it is the time to take a break. And after the break, we'll enter into the liquid solutions properly. Okay? Perfect. So it's 8:40 now. Let's take the dinner break. This is going to be the dinner break, by the way. 20. Break till 9:15. Okay? Perfect, people. I would want every one of you to be back exactly at 9:15. Okay? Till then, the ones who have any sort of problem in understanding any sort of concept, till then you can take the video back. You can watch it again. Perfect, guys. Have your dinner, but come back on time. I'll be waiting for everyone. Okay? I'll be waiting for everybody. Be back on time. Be back on time. I'll see you. I'll see you in some time. Have your dinner quick and come back. What's up, guys? Are you done? Are you all done? Is everyone back? All right. Perfect, perfect, perfect. So, guys, tell me now, whatever things we have discussed till now, is every single thing clear? Will you be able to solve all the types of the questions asked from concentration terms? Tell me in the chats. Tell me in the chats quick. Will you be able to solve all the questions based on concentration terms from now onwards? Because I've shown you all the types of the questions that can be asked. No, I'm not done with my dinner yet. I did not have my dinner. I just had some coffee. We'll have it afterwards. Are you guys done? Perfect, perfect. Perfect, guys. Just give me a second and we shall be starting. Yes, yes, I had coffee, not tea. This session will end at what time? I don't know exactly. Let's see. I don't know. Should we start then? Already? All ready, people? Let me know quick in the chats. Then we shall be starting. Exactly. There is no fixed time. Till the chapter is done and dusted, we are here. Till the chapter is done and dusted, we are here. Yeah? Perfect. Let's get going then. Let's get started with a new term, right? One of the most important terminology of this particular chapter, that is vapor pressure, right? My dear students, this vapor pressure term you'll hear from now onwards in the entire chapter. Your entire chapter of solution is based on this particular term, that is vapor pressure. So let's get going. What this vapor pressure exactly is all about. See, guys. As per the definition, I would say vapor pressure is the pressure exerted by the vapors of a volatile liquid. The pressure exerted by the vapors of a volatile liquid when liquid and its vapors are at equilibrium. When liquid and its vapors are at equilibrium at a particular temperature. at a particular temperature. So what exactly it means? What can we understand from this particular term? Try to understand very carefully, guys, what exactly I'm going to say. So first of all, imagine this is one closed container. And in this closed container, for example, we have kept a volatile liquid. In this particular container, we have kept a volatile liquid, for example, X. We have kept a volatile liquid X in the container. This liquid right now is at temperature T, which I have kept constant. This liquid is at a particular temperature. Which liquid do we have in the container? We have got a volatile liquid X in the container. Now, my dear students, since it's a volatile liquid, therefore, what will happen? When you put this liquid into the container, since the liquid is volatile, it can form its vapors. What is a volatile liquid, first of all? That particular liquid which can form its vapors. That particular liquid which can form its vapors. For example, water. Water can form its vapors. So it's a volatile liquid. So for example, I have kept a volatile liquid in the container, right? Since when the liquid is kept in the container, what will happen? What will happen? The first thing that's going to happen over here, I would say some of the liquid molecules will start getting converted into vapors. This is the first step. Some of the liquid molecules will start getting converted into vapors. So X liquid, first of all, will start getting converted into X gas. And you know, the process of conversion of liquid into gas, what do you call this as? This is called as evaporation. So first of all, what is going to happen? When this liquid is kept in a container, first of all, evaporation is going to start. Some of the liquid molecules will start getting converted into vapors. After some time, my dear students, after some time, when this liquid will continuously start getting converted into vapors, after some time, what you will observe? You will observe some of the liquid molecules getting converted. Some of the vapor particles getting converted into liquid. First, you'll observe evaporation. Then after some time, some of the vapors will start getting converted into liquid again. And that process of conversion of vapors into liquid, what do we call this as? We call this as condensation. So, when I kept liquid X in the container, first evaporation happened. After some time, condensation happened. Then, my dear students, a stage will come. Then a stage will come when rate of evaporation and rate of condensation becomes equal. At that point of time, we'll say your liquid and its vapors, they are at equilibrium with each other. At that point of time, we say your liquid and vapors, they are at equilibrium with each other. What does that mean? That means if one liquid particle is getting converted into vapor, at the same time, one vapor particle will get converted into liquid. If one liquid particle gets converted into vapor, at the same time, one vapor particle will get converted into liquid. So what does that mean? That means when liquid and vapors will be at equilibrium, when liquid and its vapors will be at equilibrium, at that point of time, I would say the amount of vapors generated will be fixed. The amount of vapors generated will be fixed. What does it mean? The amount of vapors generated will be fixed. Let's try to understand this a bit more in detail. My dear students, imagine that you kept a liquid X in the container. What happened in the beginning? Some of the liquid started getting converted into vapors. After some time, some of the vapors got converted into liquid. A stage came into this scenario when rate of evaporation and rate of condensation became equal. So if one liquid particle is getting converted into vapors, at the same time, one vapor particle will get converted into liquid. Imagine right now, there are 10 vapor particles over here. In this space, imagine there are 10 vapor particles. Now, I'm assuming equilibrium is established here. I'm assuming equilibrium is established between the liquid and its vapors. What does that mean? As I told you, that means if one liquid particle is getting converted into vapor, at the same time, one vapor particle will get converted into the liquid. Therefore, the amount of vapors here will be 10 only. They are not going to change now. So when equilibrium is established between the liquid and its vapors, the amount of vapors generated will become fixed now. They are not going to change. Why is that? Because if one liquid particle gets converted into vapor, at the same time, one vapor particle gets converted into liquid. Therefore, I would say when equilibrium is established between the liquid and its vapors, the amount of vapors generated are fixed. They are not going to change now. Okay? My dear students, at equilibrium, we have got a fixed amount of vapors here. We have got a fixed amount of vapors here, right? They are not going to change now. You tell me, at equilibrium, will these vapors be at rest or they'll be in motion? These vapors will be in motion, right? These vapors, they'll be in motion. They'll be in continuous random motion, due to which they'll be colliding with each other, due to which they'll be colliding with the walls of the container, right? Due to which they'll be colliding with the topmost surface of the liquid as well, right? So tell me one thing. Can I say at equilibrium, whatever vapors we have in the container, since these vapors are in continuous random motion, can I say these vapors at equilibrium will be exerting some pressure? Right? These vapors will be exerting some pressure on the walls of the container, on the topmost surface of the liquid as well. And that pressure which is exerted by the vapors when liquid and its vapors are at equilibrium at a particular temperature, that pressure exerted is what we call as vapor pressure, right? That is what we call as vapor pressure. So what is the vapor pressure? What is the definition of the vapor pressure? I would say vapor pressure is nothing but it is the pressure exerted by the vapors when liquid and its vapors are at equilibrium at a particular temperature. That pressure exerted is what we call as vapor pressure. Okay, perfect till here. Now, my dear students, the point is on what factors this vapor pressure depends upon. Factors affecting vapor pressure. Factors affecting vapor pressure. Before talking about the factors affecting vapor pressure, right? Or let's first of all talk about these factors. All right. Factors affecting vapor pressure. Number one, force of attraction between the liquid particles. Force of attraction between the liquid particles. Force of attraction between the liquid particles. Just tell me one thing. Just tell me one thing, guys. You tell me in the chats. If there is more attraction between these liquid particles, if there is more attraction between these liquid particles, what do you think will happen to the escaping tendency of liquid? More the attraction between the liquid, lesser will be the escaping tendency of the liquid. Lesser will be the escaping tendency of the liquid, right? More the force of attraction between the liquid particles, lesser will be the escaping tendency of the liquid. If lesser is the escaping tendency of the liquid, that means less amount of vapors will be generated. Less amount of vapors will be generated. If the vapors generated are less, what do you think will happen to vapor pressure? Vapor pressure will be less. So more the force of attraction between the liquid particles, lesser is going to be vapor pressure. So vapor pressure, I would say, is inversely proportional to force of attraction between the liquid particles. This is your point number one. Point number two, my dear students. Point number two. What is that? Vapor pressure depends on temperature as well. How it depends on temperature? That will be explained mathematically. That will be explained mathematically by Clausius-Clapeyron equation. That will be explained mathematically by Clausius-Clapeyron equation, right? And what this Clausius-Clapeyron equation is all about, let me write it. I'll write a log of P2 divided by P1 is equal to delta H vaporization divided by 2.303 R 1 upon T1 minus 1 upon T2. 1 upon T1 minus 1 upon T2. Just try to understand how this Clausius-Clapeyron equation is going to make us understand the relation of vapor pressure with temperature. See guys, first of all, leave the Clausius-Clapeyron equation aside. Think logically. When you increase the temperature, at higher temperatures, vapors generated, what do you think? Will be more or less? At higher temperatures, vapors generated will be more or less? Of course, more. Vapors generated more means more with the vapor pressure. So first of all, you should know it. Your vapor pressure, it is directly proportional to the temperature of the liquid. More the temperature of the liquid, more is going to be its vapor pressure. Now, this equation is going to explain this a bit more in detail. Let's have a look how. See guys, let me write the equation again. It is the log of P2 divided by P1 is equal to delta H vaporization divided by 2.303 R. This is 1 upon T1 minus 1 upon T2. This is your Clausius-Clapeyron equation, correct? Now try to understand. Imagine that I've got a container over here. In this particular container, for example, I've got a volatile liquid. This is a volatile liquid, which is present at temperature T1. Let's say when the liquid is present at temperature T1, assume that its vapor pressure is P1. Now, my dear students, imagine that you are changing the temperature of the liquid from T1 to T2. Let's assume at temperature T2, the vapor pressure of the liquid is P2. Okay? At temperature T1, vapor pressure of the liquid is P1. When the liquid is kept at temperature T2, its vapor pressure, for example, now is P2. Okay? Imagine that we have increased the temperature of the liquid. Imagine that initial temperature of the liquid is T1. Final temperature of the liquid is T2. Imagine that we have increased the temperature of the liquid. If we have increased the temperature of the liquid, I can say T2 value is greater than T1. I can say T2 will be greater than T1. My dear students, if T2 is greater than T1, so T2 minus T1, will it come out to be positive or negative? It will come out to be positive. T2 minus T1 will come out to be positive, right? Now tell me just one thing. Here you have got T2 minus T1. So right now this particular term is coming out to be positive. T2 minus T1, it's coming out to be positive. Now, delta H vaporization. Vaporization means conversion of liquid into gas, conversion of liquid into vapors. When you convert liquid into vapors, is the process endothermic or exothermic? Is energy required or energy released? During the conversion of liquid into vapors, is energy absorbed or energy released? Energy is absorbed. Energy absorbed means, what does that mean? That means the process of vaporization, is it endothermic or exothermic? It is endothermic. If it is endothermic, for endothermic processes, delta H is positive. So this term is positive as well as this term is positive. If this is positive, this is positive, I'll say the overall term will be positive. Overall term positive means I would say log of P2 divided by P1, this term will be positive as well. Okay. Now, my dear students, if I ask you, when is the log of X positive? When is log of X positive? Log of X is positive when X is greater than 1, right? Log of X is positive when X is greater than 1. So log of P2 by P1 will be positive when P2 divided by P1 will be greater than 1, which tells you simply that P2 is greater than P1. What was P2? P2 was the vapor pressure of the liquid at temperature T2. P1 was the vapor pressure of the liquid at temperature T1. And when we increase the temperature from T1 to T2, what is happening to vapor pressure? As you can see, P2 is greater than P1. So on increasing the temperature, vapor pressure of the liquid increases, which is clearly explained by your Clausius Clapeyron equation. So directly remember, vapor pressure is directly proportional to temperature. As simple as that. Right? I believe this is clear to everyone. If this is clear, let me tell you one more thing. My dear students, vapor pressure of the liquid. As I told you, vapor pressure of liquid is directly proportional to temperature. Okay? So if you want to see its graphical representation as well, you can do that. Let's say along this axis, I'm plotting vapor pressure. Along this axis, I'm plotting temperature. So on increasing the temperature of the liquid, what happens to its vapor pressure? Its vapor pressure increases. So the graph will be simply like this. Right? On increasing the temperature, vapor pressure of the liquid increases. Perfect. This is the graph, which shows you that on increasing the temperature, vapor pressure of the liquid increases. Okay. Now, vapor pressure of the liquid does not depend upon. Number one, vapor pressure of the liquid does not depend upon. Number one, amount of liquid taken. Amount of liquid taken. And anything that does not depend on amount of substance. Anything that does not depend on amount of substance. What do we call that as? Extensive property or intensive property. Any property which does not depend on amount of substance, we call that as the intensive property. So your vapor pressure, since it does not depend on the amount of liquid taken, so it is definitely going to be the intensive property. Okay. So for example, imagine you have got a glass of water. On another side, you have got a tub of water. Both kept at same temperature. Their vapor pressure will be same. So remember, from now onwards, your vapor pressure, it does not depend on the amount of liquid taken. Therefore, I would say vapor pressure is an intensive property. Point number one. Point number two, vapor pressure of the liquid does not depend on the shape of the container. In which liquid is kept. Remember this particular thing as well. Over here, the container which I've taken, it was a cubical container, I would say. Vapor pressure of the liquid, it does not depend on the shape of the container, right? Okay, it does not depend on the shape of the container as well. Perfect. So, since I've taken the liquid in the cubical flask, if the flask was spherical, its vapor pressure would have been same at the same temperature. Okay, so these are the two factors basically on which vapor pressure does not depend upon. Number one, amount of liquid taken. Number two, the shape of the container in which liquid is kept. I believe this is also clear to everyone. Okay. Perfect, guys. All clear till here? All clear till here? All clear till here? All clear till here? Quick. Now, we have got one more term, that is your boiling point. Boiling point. So first of all, how do we define the boiling point? How do we define the term boiling point? Understand, guys. Boiling point is defined basically as the temperature at which vapor pressure becomes equal to the external pressure. Vapor pressure becomes equal to the external pressure, which is generally atmospheric pressure. Generally atmospheric pressure. Let's try to understand this. It's again one simple thing, guys. Have a look. For example, over here, I'm taking a container. Imagine this is the container. For example, in this particular container, imagine that I've kept water. This is water in liquid state in this particular container. Assume that this water is at temperature 25 degrees centigrade. Assume that this water is at temperature 25 degrees centigrade. My dear students, understand. The water which I've taken in the container, it is right now at 25 degrees centigrade. So at 25 degrees centigrade, definitely this water will have some vapor pressure. Of course, there will be some vapors here at 25 degrees centigrade. Let's assume the vapor pressure of this water right now is 100 mm of Hg. Let's assume that the vapor pressure of this water is right now 100 mm of Hg. Okay, 100 mm of Hg. Now understand what exactly I'm going to say. Outside this container, what do we have? We have got atmosphere. Outside this container, what do we have? We have got atmosphere. And generally, how much is the atmospheric pressure under normal conditions? 700 mm of Hg. This is the atmospheric pressure, right? This is atmospheric pressure under normal conditions, right? This is your external pressure, or you call it as atmospheric pressure, which is 760 under normal condition. Now, my dear students, if you look at the definition carefully, the temperature at which vapor pressure of the liquid becomes equal to the atmospheric pressure. Tell me one thing. This liquid is right now at temperature 25 degrees centigrade. At 25 degrees centigrade, its vapor pressure is 100 mm of Hg. Okay? Right? Tell me one thing. If I want to increase the vapor pressure of this liquid, what do I have to do? If I want to increase the vapor pressure of this particular liquid, what do I have to do? I'll have to increase the temperature. If I keep on increasing the temperature of this liquid, what will keep on happening? Vapor pressure of the liquid will keep on increasing. Initially, it was 100. Now, on increasing the temperature, vapor pressure of the liquid will start to increase. If I continuously keep on increasing the temperature, can I say there will be a temperature at which vapor pressure of the liquid becomes equal to 760 mm of Hg? Right? If I continuously keep on increasing the temperature of the liquid, vapor pressure of the liquid will keep on increasing. I'll say there will be a temperature at which vapor pressure of the liquid becomes equal to the external pressure. Vapor pressure of the liquid becomes equal to the atmospheric pressure, and that temperature at which vapor pressure of the liquid becomes equal to the external pressure, vapor pressure of the liquid becomes equal to your atmospheric pressure. That temperature is something which we call as boiling point, right? So what you will observe in case of water? In case of water, you'll observe at 100 degrees centigrade. At 100 degrees centigrade, the vapor pressure of the water will be 760 mm of Hg. What is the 760 mm of Hg actually? This is your atmospheric pressure, which is your external pressure. And you know that temperature at which vapor pressure becomes equal to external pressure, that temperature is something which we call as boiling point, which is represented by TB. Am I clear with this? Am I clear with this, people? Am I clear with this? Well, if you want to have a look at its graph, if you want to understand it graphically as well, you can do that. For example, I'm plotting a graph between pressure versus temperature. Pressure versus temperature. Okay? Let's say I'm plotting a graph between vapor pressure versus temperature. Vapor pressure versus temperature. Okay. Now, my dear students, at this particular point, vapor pressure is 0, right? Vapor pressure is 0. When you increase the temperature of the liquid, what happens to vapor pressure? Vapor pressure increases. When you increase the temperature of the liquid, vapor pressure of the liquid increases. Let's say on going upwards, what is happening? Vapor pressure is increasing. Let's say this is the point. At which this is the point which represents, for example, 760 mm of Hg. Let's say this is the point which represents 760 mm of Hg pressure. Now, if you look carefully, guys, let me just join this particular thing and join this one. This is the graph between vapor pressure and temperature of a liquid, right? We know on increasing the temperature, vapor pressure of the liquid increases. This is it. On increase the temperature, vapor pressure of the liquid increases. Can I say, upon increasing the temperature, vapor pressure of the liquid is increasing. This is the temperature at which vapor pressure of the liquid becomes equal to 760 mm of Hg, which is your atmospheric pressure, which is your external pressure, and that temperature at which vapor pressure becomes equal to your external pressure, vapor pressure becomes equal to your atmospheric pressure, that temperature is what you call as boiling point. So this particular point over here on temperature axis represents your boiling point. Is it clear? Is it clear, people? Is it clear? Remember, when the P external is kept as 1 bar, when external pressure is kept as 1 bar, at that point of time, we use the term standard boiling point. Okay? When do we use the term standard boiling point? When external pressure is kept as 1 bar. When external pressure is kept as 1 atm, we use the term normal boiling point. Be careful with these two things as well. When external pressure is kept as 1 bar, we use the term standard boiling point. When external pressure is kept as 1 atm, we use the term as normal boiling point. Normal boiling point. Now, my dear students, few points about this boiling point. Understand very important points I'm going to tell you. Tell me, if the force of attraction between the liquid particles is more, if the force of attraction between the liquid is more, escaping tendencies, keep on telling me in the chats, escaping tendency of the liquid particles is more or less? Escaping tendency is less. If escaping tendency is less, vapor pressure of the liquid is less. If the vapor pressure of the liquid is less, that means if the vapor pressure of the liquid is less, that means we have to increase its temperature more in order to make its vapor pressure equal to atmospheric pressure. Temperature has to be increased more to make the vapor pressure equal to external pressure, which is generally your atmospheric pressure. Right? And if temperature has to be increased more to make the vapor pressure equal to atmospheric pressure, what does that mean? That eventually tells you your boiling point of the liquid is more. Is this point clear to everyone? So I would say in general, your boiling point is directly proportional to force of attraction between the liquid particles, right? More the force of attraction, lesser the vapors generated. Lesser the vapor pressure. Lesser the vapor pressure, that means more temperature has to be raised to make the vapor pressure equal to external pressure. That means more will be the boiling point. I believe this is clear. Point number 1. Point number 2, people. Point number 2. On increasing the external pressure, if I increase the external pressure, that means this pressure I'm talking about. If I increase the external pressure, what do we have to do? If I increase the external pressure, what will happen to boiling point? What do you think? Think over it. If I increase the external pressure, see, over here, external pressure was 760, and we had to increase the vapor pressure of the liquid from 100 to 760. So, the increase in the vapor pressure was 660 mm. Correct? But if the external pressure is more, we have to increase the vapor pressure more to boil the liquid. If we have to increase the vapor pressure more to boil the liquid, that means boiling point has to be less or more. Boiling point of the liquid will be more. Okay? If external pressure is more, that means simply boiling point of the liquid will be more. Boiling point of the liquid will be more. Okay? So your boiling point of the liquid, I would say, boiling point of the liquid is directly proportional to external pressure. More the external pressure, more is going to be the boiling point of the liquid. If this particular statement is clear, let me know once in the chats. If this particular statement is clear, let me know once in the chats quickly. Right? Or if you want to write it in detailed manner, so write it like this. On increase the external pressure, we need to increase the vapor pressure more. In order to increase the vapor pressure more, right? Temperature raised should be more. Temperature raised should be more. That means we have to raise the temperature more. Raise the temperature more in order to equalize vapor pressure with external pressure, right? That eventually tells you more is going to be the boiling point. That's all. Can you let me know in the chats if this is perfectly clear to everyone? Perfectly clear. Let me know once quickly. Quickly, people. Everybody. Let me know in the chats quick. Which one is going to be the next chapter? Next chapter, I'll do chemical bonding. Chemical bonding will be the next chapter. Okay? Chemical bonding will be the next chapter. Perfect. So let's have a look on the freezing point now. Hey guys, how do you define freezing point in very simple terminologies? Freezing point is defined as the temperature at which vapor pressure, if I define it in terms of vapor pressure, it's going to be defined as the temperature at which the vapor pressure of liquid becomes equal to its solid form. Or I can say, I'll say at freezing point, solid and liquid will be at equilibrium. Let's try to understand. See how I'll make you understand this in like simple words. Guys, see, whatever I'm teaching you right now, all this basically has thermodynamic explanations, right? All this, whatever I'm going to teach you here in the solution, every single thing has got thermodynamic explanation in terms of entropy, right? In terms of entropy. But I'm not discussing that here because that's of no use to us, okay? I'm giving you simple explanations so that you can remember all this stuff. Otherwise, every single thing, if I teach you relative lowering, when I'll be teaching you elevation and boiling point, depression and freezing point, every single thing has got the thermodynamic explanation. I mean, amazing explanations, everything has. But that is of no use to you, okay? So whatever things I'm telling you, just remember them so that we could solve the questions when it comes to your NEET and JEE examination, okay? Got it? So let's have a look on the freezing point first of all. My dear students, imagine that this is the container which we have. And in this container, for example, you have taken H2O liquid. This is H2O liquid right now in the container. This liquid is right now, for example, at 25 degrees centigrade. Let's assume at 25 degrees centigrade, the vapor pressure of the liquid is, for example, 100 mm of Hg. At 25 degrees centigrade, let's assume vapor pressure of the liquid is how much? 100 mm of Hg. Now, my dear students, if I solidify this liquid, When I solidify this liquid, it gets converted into ice. If I take the solid form of this liquid, that means if I take ice, okay? If I take ice, I've solidified this liquid. I've taken the solid form of this particular liquid. Now this ice will also have some of the vapors here, right? It will also have some of the vapors here. So this ice will also have here its vapor pressure. For example, this vapor pressure is 10 mm of Hg. Just to make you understand. Let's say the vapor pressure here is 10 mm of Hg. 10 mm of Hg. Now, understand one simple thing. Look at the definition. The temperature at which vapor pressure of the liquid, becomes equal to the vapor pressure of its solid form. The temperature at which vapor pressure of the liquid becomes equal to the vapor pressure of its solid form. So if I want to freeze this liquid, do I have to increase its vapor pressure or I'll have to decrease its vapor pressure? If I want to freeze this liquid, I have to decrease this vapor pressure from 100 mm to 10 mm. And how do I decrease its vapor pressure? How do I decrease the vapor pressure of the liquid? By decreasing the temperature of the liquid. If I keep on decreasing the temperature of the liquid, initially the liquid was at 25 degrees centigrade. Now, if I keep on decreasing the temperature of the liquid, vapor pressure of the liquid will keep on decreasing, The temperature will arise at which vapor pressure of the liquid would have become equal to 10 mm of Hg. That temperature at which vapor pressure of liquid and its solid form becomes equal, we call that particular temperature as the freezing point, right? And in case of water, what do you observe? At 0 degree, which is the freezing point of water, at 0 degree, the vapor pressure of liquid water would be equal to the vapor pressure of ice, would be equal to the vapor pressure of its solidified form. And that particular temperature at which vapor pressure of the liquid becomes equal to vapor pressure of its solid, you call that particular temperature as the freezing point. Yes? Right? People, if you want to have its graphical look, let's have a look. Understand? See, this is vapor pressure. This is the temperature. Okay? Vapor pressure versus temperature. See, this particular graph represents, on increase the temperature, vapor pressure of the liquid increases. This is the graph for the liquid. If you want to plot the graph for the solidified form of this liquid, it will come like this. This is the solidified form of this liquid. So, if you first of all extend this, it will meet here. Right? It will meet here. This particular part, it is for solid, right? This particular part is for liquid, right? Now guys, if you think logically, on increasing the temperature, the vapor pressure is increasing. When you are decreasing the temperature, when you are decreasing the temperature, vapor pressure of the liquid is decreasing. On decreasing the temperature, vapor pressure of the liquid is decreasing. This is the point at which vapor pressure of solid, the vapor pressure of liquid and its solid is becoming equal. That particular temperature at which the vapor pressure of liquid and its solid becomes equal, you call that particular temperature as the freezing point. So this particular point over here on the temperature axis, it represents your freezing point. Is this clear? Is it clear, people? Is it clear? Let me know once in the chats. This particular part of the graph, it is valid for liquid. This is the solidified form of the liquid, right? So on decreasing the temperature, vapor pressure of the liquid decreases. This is the point at which the vapor pressure of the liquid and its solidified form becomes equal. And that temperature at which the vapor pressure of liquid and its solid becomes equal, we call that particular temperature as the freezing point. Okay? We call that particular thing as the freezing point. I hope this is clear. So 3 terminologies I discussed with you: vapor pressure, boiling point, freezing point. Now, my dear students, we are going to enter into an amazing phase of the chapter. What is that? That is going to be your Rault's law. That's going to be your Rault's law. That is going to be your Rault's law, from which questions are frequently asked. Questions are frequently asked. Rault's law. So what this Rault's law exactly is all about? Let's understand. Someone is saying, sir, you did not teach this in the plus class. In the plus class, I would have taught this graph when I would have taught you depression in freezing point. Okay? Got it? Henry is like crying in the corner. Yes. What is there in Henry's law? Nothing. Okay, look here. Rault's law. What this Rault's law states that how this Rault's law was introduced, etc., that's of no use to you. Let's have a look on the statement. Let's see where do we use this Rault's law. Let's see what kind of questions can be asked from this Rault's law. That's our main point. Okay. Let's talk about the Rault's law now. As per the Rault's law is concerned, I will say the partial vapor pressure. The partial vapor pressure of a component. The partial vapor pressure of a component over a solution. Over a solution is directly proportional to its mole fraction, in the solution. Is directly proportional to its mole fraction in the solution. What exactly it means? What exactly it means? Let's try to understand. See, guys, imagine this is the container, one of the containers. Okay. Imagine I've got one more container here, and this is the final one. So I've taken 3 containers here. Understand what I'm going to say. I'm assuming that there is a volatile liquid A in this container. I'm assuming there is volatile liquid B in the container. Volatile liquid B in the container. Okay. First of all, since the liquid is volatile, so you will find its vapors here. Yes. The vapor pressure of liquid A when present in pure state is represented by P naught A. So what is this P naught A? It is the vapor pressure of A in pure state. It is the vapor pressure of A in pure state. Since this A is right now in pure state, there is nothing added to it. So this A is in pure state. Vapor pressure of A in pure state is something which I represent with P naught A. Similarly, vapor pressure of B in pure state, I'm representing with P naught B. Vapor pressure of liquid B in pure state. I'm representing with P naught B. My dear students, understand one thing. Simple. If I mix these 2 liquids into this container, if I mix these 2 volatile liquids into this container, what do we get? We'll be getting a solution. We'll be getting a solution of A and B. Since this A is volatile as well as B is volatile. A is volatile as well as B is volatile. Therefore, you'll find vapors of A. You'll find vapors of A as well as vapors of B here. You'll find vapors of A as well as vapors of B here. So, my dear students, can I say the vapor pressure of the solution here? The vapor pressure of the solution. Is the vapor pressure of solution only going to be due to A? Only going to be due to B? Or both would have contributed? I would say both would have contributed. Both would have contributed. both would have contributed, right? So I would say vapor pressure of the solution would be due to A as well as B. And let me tell you, contribution made by vapors of A towards the total vapor pressure of solution. That's what I call as partial vapor pressure of A. Contribution made by vapors of B. Contribution made by vapors of B towards the total vapor pressure of the solution. You call that as partial vapor pressure of B. And you know, the total vapor pressure of the solution will be the sum of partial vapor pressure. Will be the sum of partial vapor pressure. What is PA? PA is what I call as partial vapor pressure. Partial vapor pressure of A. This is partial vapor pressure of B. What is meant by partial vapor pressure of A? Partial vapor pressure of A means contribution made by vapors of A towards the total vapor pressure of the solution. Contribution made by vapors of B towards the total vapor pressure of the solution. For example, imagine the total vapor pressure of the solution is 10 bar. Imagine the total vapor pressure of the solution is 10 bar, right? That 10 bar will be due to A as well as B. Let's say towards that 10 bar, contribution made by A is 2 bar. Therefore, contribution made by B will be 8 bar. So this 2 bar and 8 bar will be the contribution made by A and B towards the total vapor pressure of the solution, which is what you call as partial vapor pressures, right? Which is what you call as partial vapor pressures. Correct, people? Which is what you call as partial vapor pressure. Now, what Rault's law says? What Rault's law says? As per Rault's law, partial vapor pressure of a component, for example, partial vapor pressure of A, that is directly proportional to mole fraction of A in the solution. That is directly proportional to mole fraction of A in the solution. Similarly, partial vapor pressure of B, that is directly proportional to mole fraction of B in the solution. What does that mean? See guys, just understand. As per Rault's law is concerned, partial vapor pressure of A is directly proportional to mole fraction of A in the solution. Anyone think? What is this mole fraction of A? Mole fraction of A means number of moles of A in the solution divided by total moles present in the solution, right? Mole fraction of A in the solution means number of moles of A in the solution divided by total moles present in the solution. Tell me one thing. More the mole fraction of A. What does that mean? That means more will be the moles of A in the solution. If more are the moles of A in the solution, there is more probability of A forming its vapors. If there is more probability of A forming its vapors, I'll say the partial vapor pressure of A will be more, right? I'll say the partial vapor pressure of A will be more. So in short, remember it directly. Partial vapor pressure of A is directly proportional to mole fraction of A in the solution. Partial vapor pressure of B is directly proportional to mole fraction of B in the solution, right? And if you remove these proportionality constants, you'll be getting a constant here, P naught A multiplied by chi A. And this PB over here will be equal to P naught B multiplied by chi B. This is your Rault's law, as simple as that. Which you have to remember. This is the Rault's law, which you have to remember. Okay? Is it clear, guys, still here? So what I'm trying to say is, the partial vapor pressure of A of a component over the solution is directly proportional to mole fraction of A in the solution. More the mole fraction of A in the solution. That means more with the moles of A in the solution. More the moles of A in the solution, more is the probability of A to form its vapors. If more is the probability to form the vapors, that means more will be its partial vapor pressure. Simple. Simple, right? Okay. Perfect, guys. Now, here comes one more thing. First of all, let me write these terminologies again so that you are not going to forget them. I told you PA is nothing but P naught A chi A. And similarly, I told you PB is nothing but P naught B chi B. P naught B chi B, right? P naught B chi B. What is PA? PA is what we call as partial vapor pressure of A. PB is what I call as partial vapor pressure of B. P naught A is basically vapor pressure of A in pure state. Vapor pressure of A in pure state. P naught B is the vapor pressure of B in pure state. Vapor pressure of B in pure state. Chi A is the mole fraction of A in solution, not in vapors, okay? Not in vapor phase, in solution. Chi B is the mole fraction of B in the solution. Now, people, if I would want to plot certain graphs, I can do that too. The first graph which I'm plotting is, for example, between PA versus Chi A. The second graph which I'm going to plot here, that is, for example, between PB versus Chi B. The third graph which I'm plotting is between PA versus Chi B. The next graph which I'll be plotting here, that will be between PB versus Chi A. These are few graphs which I'm plotting here. Okay, guys. We know when we talk about PA is nothing but P naught A Chi A. PA we are plotting along y-axis. Chi A we are plotting along x-axis. This becomes my M. Y is equal to mx, straight line passing through origin. Slope is the value of M. M is nothing but P naught A. Correct? P naught B Chi B. We know PB is equal to P naught B Chi B. Right? PB you are plotting along y-axis. Chi B you are plotting along x-axis. This becomes your M. Y is equal to mx. Again a straight line passing through origin. Its slope is nothing but P naught B. Its slope is P naught B. Right? Its slope is P naught B. Now look here. PA versus Chi B. As we know, PA is equal to P naught A Chi A. Right? So I can write PA is equal to P naught A. Instead of Chi A, I'll write 1 minus Chi B. So it's going to be PA is equal to P naught A minus P naught A Chi B. So this PA you are plotting along y-axis. Chi B you are plotting along x-axis. This becomes your M. The sign is minus and this is C. So y is equal to minus mx plus c. Y is equal to minus mx plus c. Straight line with a negative slope. Straight line with a negative slope. And slope here is minus P naught A. Similarly, this PB versus Chi B. This PB versus Chi B. Sorry, not PB versus Chi B. This is PB versus Chi A. Right? This will be also like this. Okay, when you plot it, and its slope will be minus P naught B. See, PA versus Chi B, its slope was minus P naught A. PB versus Chi A, its slope will be minus P naught B. So these are few basic graphs which can be asked too. Okay? I hope this is clear. What is happening in the chats? What is happening in the chats? Who are these nonsense people? Bro, you can go to some other channel. If you want to chit chat with girls and stuff, you can go to some other channel. I'm blocking you right now, whosoever this is nonsense. This channel is not meant for this, by the way. Banned. All clear people till here? Perfect. Let's have a look on few more things. Let's have a look on few more things. Let me first of all talk about Rault's law for a solution. Rault's law for a solution containing two volatile liquids. Rault's law for a solution containing two volatile liquids. What exactly it's all about? See guys, it's same. We have discussed it. Imagine that this is a container. And this particular container contains, for example, the solution of A and B. It contains the solution of A and B. I'm assuming A as well as B, both are volatile in nature. If both are volatile, you'll find vapors of A as well as B. You'll find vapors of A as well as B, right? And we know total vapor pressure of the solution is nothing. It is the sum of partial vapor pressures of A and B. And as per your Rault's law is concerned, PA is nothing but P naught A chi A plus P naught B chi B. This is one of the equations from which question will be asked. Number one. Number two. Since this is the solution, this yellow colored part, it is a solution containing A and B. It's a solution containing A and B, in which mole fraction of A in the solution I'm representing with chi A, mole fraction of B in the solution I'm representing with chi B. And you know, since it's a binary solution containing two components, so chi A plus chi B has to be 1. Chi A plus chi B has to be 1. Now, people, if chi A plus chi B has to be 1, I can write the same equation in a different format. I can say PS is equal to P naught A chi A plus P naught B. Instead of chi B, I'm going to write 1 minus chi A, right? So PS is nothing but P naught A chi A plus this is P naught B minus P naught B multiplied by chi A. So I'll say PS is equal to, understand, first I'm writing P naught B. Then here you have got chi A, here you have got chi A. Take chi A as common, so it becomes P naught A minus P naught B multiplied by chi A. This is one more equation from which question can be formed. Is there any other equation? Yes, we can make one more equation as well. Since over here, what did I do? Instead of chi B, I wrote 1 minus chi A. I could have replaced this chi A also with 1 minus chi B. Yes. And what happens if that is done? PS is equal to P naught A. Instead of chi A, I'm writing 1 minus chi B plus this is P naught B multiplied by chi B. So I'll be writing PS is equal. This is P naught A minus P naught A chi B plus P naught B chi B, right? So you'll finally write PS is equal to P naught A chi B take as common. So it is going to be P naught B minus P naught A multiplied by chi B. This is one more equation from which question can be framed. Okay, I believe all the three equations are clear. I believe all the three equations are clear. Now, if all these three equations are clear, right, let's have a look on the graphical representation of all this stuff. Understand, guys. I'm going to plot a graph now, which will make you explain all this stuff in detail. I'm going to plot a graph now. This graph is important, okay? You have to understand this properly. Okay. Here along y-axis, I'm plotting vapor pressure. Along x-axis, I'm plotting mole fraction. Mole fraction chi. Mole fraction of the component in the solution. Okay. I'm plotting a graph between vapor pressure and mole fraction. Now guys, for example, at this particular point, let's assume chi A is equal to 0. If chi A is 0 at this point, that means chi B will be equal to 1. because chi A plus chi B, it always has to be 1. You know, your chi A plus chi B, your chi A plus chi B, it always has to be 1. If chi A is 0, therefore chi B is 1. Let's say this is the point which is at which chi A is 1. If chi A is 1, so it says that chi B has to be 0. Perfect. Now guys, understand few things. Understand few things, few important things. Okay. At this point, chi A is 0. That means in the container there is no A. There is only B in the container. At this point, in the container there is no A. There is only B in the container. So I would say B is right now present in the pure state. So the vapor pressure right now will be only due to pure B, and vapor pressure due to pure B will be represented by P naught B. Let's say this is the point which represents your P naught B. Okay? This is the point which represents P naught B. At this point, chi A is 0. If chi A is 0, that means there is no A in the container. If there is no A in the container, vapor pressure due to A will be 0. Vapor pressure due to A will be 0. And vapor pressure due to B right now is P naught B. Okay? Now, on moving from left to right, what is happening to the mole fraction of A in the solution? You know, your PA is equal to P naught A chi A. If chi A increases, partial vapor pressure of A is increasing. If chi A increases, partial vapor pressure of A increases. Now people think logically. If you move in this direction, chi A is increasing. If chi A is increasing, as per this equation, the partial vapor pressure of A will be increasing. If you think over it logically, on moving from left to right, chi A is increasing. At this particular point, there was no A in the container. Now, chi A is increasing. If chi A is increasing, that means in the solution A is increasing. If in the solution A is increasing, that means vapors due to A will be also increasing. If vapors due to A will be increasing, that means partial vapor pressure of A will be increasing. Partial vapor pressure of A will start to increase. Right? In this direction, partial vapor pressure of A will start to increase like this. Right? Now, let me keep it till here. Look at this particular point. At this point, chi A is 1. If chi A is 1, what does that mean? That means chi B is 0. So at this point, there is no B in the container. There is only A in the container. So vapor pressure right now is only due to A. And vapor pressure due to pure A is represented by P naught A. So this graph will continuously keep on going like this, right? And we'll meet here, for example. It's a straight line, okay? I could not make it straight though. And this is the point which represents your P naught A. Or you can put the points as well. If chi A is 1 at this point, put chi A as 1, PA will be equal to P naught A. Okay? Clear, guys? Clear? All clear? So, on moving from left to right, chi A increases. Chi A increase means moles of A in the solution increases. If moles of A in the solution increases, vapors due to A will increase. Vapor pressure due to A will increase. That's what happens. Vapor pressure due to A is increasing. And this is the straight line valid for, the equation for this particular straight line will be what? It will be PA is equal to P naught A chi A. This is the equation for this straight line. Because this straight line is giving us the idea about A. Perfect. Now, if you again think logically, at this particular point, there is only B in the container. So pure B, vapor pressure due to pure B is P naught B. At this particular point, there is no B in the container. So vapor pressure due to B is 0. Vapor pressure due to B is 0. Vapor pressure due to B is 0. Now, why did I join these two? Understand. On moving from left to right, chi B is decreasing from 1 to 0. On moving from left to right, chi B is decreasing. If chi B is decreasing in the container, that means moles of B in the solution are decreasing. If moles of B in the solution are decreasing, that means vapor pressure due to B will be decreasing as well. That is the reason why this graph is going down. And this particular graph is for PB is equal to P naught B chi B. This is the equation which, correctly describes this graph. Okay? Similarly, guys, similarly, if I join this point with this particular point, this straight line will be for the total vapor pressure of the solution, which is your PA plus PB. Or, PA is nothing but P naught A chi A plus P naught B chi B. Did you understand how this graph is formed? This is an important graph which I would want you guys to remember. Did you understand, people, how this graph is formed? Quick. Quick, everybody. Everybody. Did you understand how this particular graph is formed? Quickly, people. Done? Amazing. Just give me a second, guys. Okay, amazing. Why PA is here, P not B? You're saying why this is, I mean, at the lower position, this at higher position? It is completely your choice. Yeah? Got it? Here I made P not B at the lower position. You could have made it higher. That's it. And accordingly changed all this. Okay. Now, there is one more point in the Rault's law. What is that? That is calculation of mole fraction of A and B in vapor phase. Calculation of mole fraction of A and B in the vapor phase. From this particular topic, questions are also asked. Okay, calculation of mole fraction of A and B in the vapor phase. What exactly it means? It's one simple topic. I believe it'll be clear to you in a very lesser time. See, guys, imagine that again you have taken a solution. Imagine that again you have taken a solution. This is the solution of A and B, for example, out of which A as well as B both are volatile. This is the solution of A and B. This is the solution of A and B. A as well as B both are volatile in nature. Okay. If A and B both are volatile in nature, you'll find here vapors of A as well as B. These are the vapors of A as well as B. Let me assume in this particular part of the container, in this yellow colored part of the container, number of moles of A. Let me assume number of moles of A in this solution phase. So first of all, from here to here, it is the solution phase. It is a solution phase which contains two liquids A and B. Oh, from here to here, it is basically a gaseous mixture containing gas A and gas B, vapor A and vapor B. Perfect. So let me first of all tell you, this particular part of the container contains vapors of A and B. It contains vapors of A and B. And this particular part over here, this particular part from here to here, it contains a solution of two volatile liquids A and B. This is the solution of two volatile liquids A and B. Now let me assume certain things. Let's assume first of all, Na represents moles of liquid A in the solution. Nb represents moles of this liquid in the solution. Chi A represents mole fraction of A in the solution. Chi B represents mole fraction of B in the solution. Okay. Similarly, Chi A dash, or leave Chi A dash aside, Na dash represents moles of A in this mixture containing vapors of A and B. Let's say the vapors of A in this mixture vapors of A in this mixture, its moles are Na dash. Similarly, Nb dash represents moles of vapors of B in this mixture. Similarly, chi A dash, mole fraction of A in this particular vapor mixture, mole fraction of B in this particular vapor mixture. I hope this is clear. I hope these terms are clear. I hope these terms are clear. Are they? Chi A is the mole fraction of A in the solution phase. This is the mole fraction of A in the vapor phase. That's the difference. Chi B is mole fraction of B in the solution phase. Chi B dash, that is the mole fraction of B in the, that is mole fraction of B in the vapor phase. That is mole fraction of B in the vapor phase. Yes? Correct? Now guys, understand. Since we know one thing, vapor pressure of the solution is equal to PA plus PB. What is PA and what is PB? We have discussed this too. What is PA and what is PB? PA is partial vapor pressure of A. PA is partial vapor pressure of A. As per Rault's law, partial vapor pressure of A will be equal to P naught A chi A. This is as per your Rault's law. But as per Dalton's law is concerned, how do we get the partial vapor pressure of a gas? As per Dalton's law. As per Dalton's law, it is total pressure of the mixture multiplied by mole fraction of that particular gas in the mixture. This is the Dalton's law. This is the Dalton's law. This is the Dalton's law. Partial vapor pressure of A as per Rault's law is P naught A chi A. Similarly, partial vapor pressure of A in the vapor phase as per Dalton's law is going to be equal to total vapor pressure of solution multiplied by mole fraction of A in the vapor phase. Okay? One equation is as per Rault's law, one equation is as per Dalton's law. Dalton's law says that partial pressure of a gas, partial pressure of gas is always equal to total pressure of the gaseous mixture multiplied by mole fraction of that gas in the mixture. Since we are talking about A, total pressure of the mixture multiplied by mole fraction of A in the vapor phase. Mole fraction of A in the vapor phase is how much? Chi A dash. One is your Rault's law, one is your Dalton's law. Both the equations are giving you same PA. If both the equations are giving us same PA, I can say your P naught A chi A has to be equal to PS multiplied by chi A dash. Or I would say chi A dash is nothing but P naught A chi A divided by PS. Divided by PS. This is how you calculate mole fraction of A in the vapor phase. A question is directly asked from it. Calculate the mole fraction of A in the vapor phase. In the vapor phase, what is the mole fraction of A? That means you have to calculate chi A dash. Similarly, if they ask you, how do we calculate chi B dash? Chi B dash simply will be P naught B multiplied by chi B divided by PS. PS represents the total vapor pressure of the solution. But be careful with all the things, right? Be careful with all the things. Let me write all the things here. Chi A is mole fraction of A in solution phase. In solution. Chi A dash is again the mole fraction of A, but in vapor phase. In vapor phase. In vapor phase. Is it clear? These two equations are super important. Remember them, and I'll show you its application in some time. First, I need to cover one more thing. What is that thing? It is Rault's law for a solution. Rault's law for a solution containing a non-volatile solute. Rault's law for a solution containing non-volatile solute. Rault's law for a solution containing a non-volatile solute. Now understand what exactly I'm going to say. Imagine this is the container. In this particular container, we have got a volatile liquid A. This is volatile liquid A in the container. So vapor pressure of A right now, since A is in pure state, it is going to be P naught A. It is going to be P naught A, right? It is going to be P naught A. Now in this particular container, assume that you are adding non-volatile solute B. That solute which cannot form its vapors. That solute which cannot form its vapors. That solute which cannot form its vapors. For example, I'm taking urea here. For example, I'm taking glucose here. For example, I'm taking sucrose here. These are all the examples of non-volatile solute. When you'll be adding non-volatile solute here, what will happen? What will happen, people? When you'll be adding non-volatile solute into a volatile liquid, what will you observe? You'll be getting a solution. This is going to be the solution. Solution of what? Solution of A and B. But we know among A and B, A is volatile, but B is non-volatile, right? So in this particular solution, you will have A as well as B. You will have A as well as B. In this solution, you only had A. You had pure A. And all the A particles are volatile. Here in this solution, you have got A as well as B. B is non-volatile. So tell me, when non-volatile solute is added, what do you think would happen to the vapor pressure of the solution? Well, the vapor pressure of the solution was supposed to be equal to PA plus PB, but B is non-volatile. If B is non-volatile, it cannot form its vapors. If it cannot form its vapors, contribution made by B towards the total vapor pressure will be 0. So PS is nothing but PA, and already you know PA is nothing but P naught A chi. Okay? P naught A chi. Is this clear? Think over it, guys. Think over it properly, what I said. Think over it, what I said. I, in the beginning, had a pure volatile liquid. All the particles here were volatile. All the particles here are volatile. All the particles are non-volatile. Some of the particles are volatile, some are non-volatile. So what do you think? When a non-volatile solute is added, what happens to the probability of vapor formation? Is the probability of vapor formation going to get increased or decreased? Here all the particles were what? Here all the particles were volatile in nature. Here some of the particles are volatile, some are non-volatile. Right? What do you think would be the probability of vapor formation here? Increased or decreased? Probability of vapor formation would have decreased. Right? Would have decreased. Here all the particles were volatile. With volatile, there are non-volatile particles as well. Correct? Correct? So, if you understood, there is one more explanation in terms of entropy. I'm avoiding all the thermodynamic explanation here, okay? I'm avoiding all the thermodynamic explanation here. Just remember what I'm saying, that's it. Okay, this much is sufficient for you. Okay, this much is sufficient for you. So, let me write a statement. The statement is like this. On adding a non-volatile solute in a volatile liquid, on adding a non-volatile solute in a volatile liquid, what happens to vapor pressure? Increase or decreases? Vapor pressure decreases. Full stop. This decrease in the vapor pressure, this decrease in the vapor pressure is called as lowering in vapor pressure. Lowering in vapor pressure, represented by delta P. This decrease in the vapor pressure is called as lowering in the vapor pressure, represented by delta P. Okay, so if I ask you how much vapor pressure has lowered, how much vapor pressure has decreased? Initially, the vapor pressure was P naught A. Now the vapor pressure is PS. And we already know PS will be less than that of P naught A. PS will be less than that of P naught A. Right? On adding a non-volatile solute into a volatile liquid, vapor pressure decreases. Right? Initial vapor pressure was P naught A. Now the vapor pressure has decreased. Now it is PS. So how much has vapor pressure decreased? Initially it was P naught A. Now finally the vapor pressure is PS. So take the difference between the two. This will give you the decrease in the vapor pressure. This will give you the decrease in the vapor pressure. So P naught A minus, what is PS? PS is equal to P naught A chi. Right? If you take P naught A common, 1 minus chi is nothing but chi B. So this is something which you call as lowering in vapor pressure. When a non-volatile solute is added to a volatile liquid, vapor pressure decreases, and this decrease in the vapor pressure is what you call as lowering in vapor pressure, represented by delta P, which is nothing but P naught A multiplied by chi B. Am I clear with this? Am I clear with this? Am I clear with this? Perfect. Let's try to solve different questions which can be asked from the Rault's law. Then we can take one break. Okay? Some 3 to 4 questions. 4 to 5 questions we'll be solving here, which will quickly summarize all this in detail. See guys, the vapor pressure of two pure liquids A and B. The vapor pressure of two pure liquids A and B are 100 torr and 80 torr respectively. And 80 torr respectively. Calculate the total vapor pressure of the solution. Calculate the total vapor pressure of the solution on mixing 2 moles of A and 3 moles of B. On mixing 2 moles of A and 3 moles of B. So basically you have taken two liquids A and B, right? You are mixing them up. You have taken 2 moles of liquid A and 3 moles of liquid B. You have mixed them up. We have to calculate total vapor pressure of the solution. Yeah, it's simple. So PS is nothing but it is equal to P naught A chi A plus P naught B chi B. Perfect. What is P naught A? P naught A is 100. What is chi A? Chi A means moles of A divided by total moles present in the solution. Perfect. Plus P naught B is how much? 80 multiplied by moles of B divided by total moles present in the solution. Now, this is 100. How many moles of A in the solution? 2. So 2 divided by 2 plus 3, 5 plus 80 multiplied by 3 divided by 5. Solve this, get the final answer, and you'll be getting the final answer in torr. How much it comes, RB? People are saying 88. Okay, the final answer is 88 torr. So this is the final vapor pressure of the solution, people. This is the final vapor pressure of the solution when we mix 2 moles of liquid A with 3 moles of liquid B. Clear? Simple? Simple, people? Yeah? Okay, moving ahead. Moving ahead. One more simple question this is. One more simple question this is. The vapor pressure of pure liquid A, so P naught A, is how much? 70 torr. It forms an ideal solution with another liquid B. The mole fraction of B in solution means chi B is how much? 0.2. The total vapor pressure of the solution, is 84 torr. What do I have to calculate? P naught B. Again, a simple question, guys. P naught B you have to calculate. You can easily solve this. You can easily solve this, right? Correct? Say, equation you already know. PS is nothing but P naught A chi A plus P naught B multiplied by chi B. Right? What is PS? PS is 84 is equal to what is P naught A? 70. Chi A is how much? 0.2 plus P naught B. I need to calculate. What will be chi B? Chi B will be 1 minus chi A. 1 minus chi A means 0.8 here. So one equation, one unknown. Get the P naught B value from here. Something I was supposed to calculate. Simple again. Yeah? Simple and basic question this is. Look at this one. A solution has the molar ratio of pentane and hexane. So we have got a solution. Let me make it over here so that it will be clear to you. We have got a solution of pentane and hexane. Let's say pentane I'm representing with A and hexane I'm representing with B. Okay? We have got a solution of pentane and hexane present in the molar ratio of 1:4. The ratio of their moles in the solution phase. The ratio of their moles in the solution phase is 1:4. Their P naught values, right? As per the question, their P naught values are also given. What do you have to calculate? Mole fraction of pentane in the vapor phase. Mole fraction of pentane in the vapor phase. Mole fraction of pentane in the vapor phase means, do I have to calculate chi A or chi A dash? I have to calculate chi A dash, which is nothing but P naught A chi A divided by PS. Divided by PS. Now, first of all, the molar ratio of A and B in the solution phase is 1:4. That means if the moles of A are X, moles of B are supposed to be 4X. Right? If the moles of A are X, moles of B are supposed to be 4X. Right? So what about the mole fraction then? What about the mole fraction of A? Mole fraction of A in the solution will be moles of A divided by total moles. So X divided by 5X comes out to be X divided by 5X comes out to be 1 by 5. This will come out to be 4 by 5. Right? Mole fraction of A will be moles of A divided by total moles. Similarly, mole fraction of B will be moles of B divided by total moles. So mole fraction of A and B in the solution phase we got. So this is the value of your chi A and this is the value of your chi B. If you got chi A you got. What do I need now? I need vapor pressure of the solution. Vapor pressure of the solution, you can use the Rault's law. P naught A chi A plus P naught B chi B. As per the question, what is P naught A? P naught A is 440. What is chi A? Chi A is 1 by 5. What is P naught B? P naught B is 120. What is chi B? Chi B is 4 by 5. Right? Just solve this, get the value of PS and let me know in the charts once quickly. What is the value of PS which you get here? Quick. People are saying 184. Huh? Okay. 184 mm of Hg is the total vapor pressure of the solution. Once you get PS, calculate the mole fraction of A in the vapor phase, which is P naught A, 440. Chi A, mole fraction of A in the solution phase, that is 1 by 5, divided by PS, 184. When you solve this, I think you'll get the answer as 0.47. What is 0.47 here? What is 0.47? This is the mole fraction of A in the vapor phase. If you got the mole fraction of A in the vapor phase, therefore mole fraction of B in the vapor phase is 1 minus chi A dash. 1 minus 0.47 comes out to be 0.53. Done and dusted. Look at this question. The total vapor pressure of the solution is given by this equation. Calculate P naught A and P naught B. Okay, how do you solve this? The total vapor pressure of the solution is given by this equation. Calculate P naught A and P naught B. Tell me one thing. When chi B will be equal to 1, that means at that point of time chi A will be 0. Because chi A plus chi B has to be 1. Right? Right, people? If for example, if I take chi B as 1, if chi B is 1, that means chi A is 0. So in the container, there is only pure A present. In the container, there is only pure A present right now. There is only pure A present. Since you have taken chi B as 1, if you take chi B here as 1, so it will be 220 minus 110. How much that comes out to be? That comes out to be 110 mm of Hg. 110 mm of Hg. Since right now in the container there is only A present, so vapor pressure due to pure A is represented by P naught A. So P naught A you directly got as 110 mm of Hg. Did you understand how I solved? Similarly, if chi B is equal to 0, that means chi A is equal to 1. What does that mean? That means in the container, sorry, this is not pure A, this is pure B. This was pure B since chi B is 1. Since chi B is 1, right? So this has to be, just a second. I've taken chi B as 1, that means chi A is 0. So there is in the container there is pure B present. And vapor pressure due to pure B is nothing but P naught B. This is P naught B, sorry, not P naught A. Yeah? Look here, if chi B is 0 now, chi A will be 1. So in the container there is pure A present. Vapor pressure due to pure A is P naught A. Let's check that, how much that will be. Put chi A as 1, chi B 0. Chi B 0, so it comes out to be simply 220 mm of Hg. These were the two things which we were supposed to calculate. Am I clear? Am I clear, people? Am I clear? Quick in the chats. Done? Perfect. Similar sort of question I'm giving you, which you'll be solving on your own. This is the similar type of question and is the homework question. You'll solve that after the session ends. Once the session ends, then you'll be solving this question. Once the session ends, then you'll be solving this question. Okay? Let's have a look on one more question then. Two liquids A and B forms an ideal solution. At 300 Kelvin, the vapor pressure of a solution containing 1 mole of A and 3 moles of B. Here you have a solution containing 1 mole of A and 3 moles of B. Moles of A in the solution is 1. Moles of B in the solution is 3. Right? Vapor pressure of this particular solution right now. Vapor pressure of this particular solution right now. Right now, the vapor pressure of the solution is how much? 500 mm of Hg. Okay. At the same temperature, if 1 more mole of B is added, in the container, you are adding 1 extra mole of B. You are adding 1 extra mole of B. So when you will be adding 1 extra mole of B, what would happen? Think over it. When you will be adding an extra mole of B, will anything happen to moles of A? No, moles of A will remain 1 in the solution. But now the moles of B are not just going to be 3. Initially, there were 3 moles of B in the container. Now we have added 1 more. So 3 plus 1 makes it 4. So there are 4 moles of B in the container now. As per the question, when 1 more mole of B is further added, the vapor pressure of the solution increases by 10 mm. So initial vapor pressure of the solution was 500. Now after adding 1 extra mole of B, vapor pressure of the solution has increased by 10 mm. So initially it was 500. Now it's going to be 510 mm of Hg. What do we have to calculate? We have to calculate P naught A and P naught B. We have to calculate P naught A and P naught B. Try to understand, guys. First of all, I've got 2 scenarios here. Scenario number 1 on the left side, scenario number 2 on the right side. Scenario number 1 says that PS, which is the vapor pressure of the solution, is equal to P naught A. Chi A over here, mole fraction of A in the solution will be 1 divided by 3 plus 1, 4. This is 1 by 4 plus P naught B multiplied by Chi B, mole fraction of B in the solution, will be 3 divided by 3 plus 1, 4. If I take 4 as the common in the denominator, right, it becomes 4 5s are 20. So 2000 is equal to P naught A plus 3 times P naught B. Calling this as equation number 1. Calling this as equation number 1. Similarly, can we make one more equation here in this scenario? Over here, PS is equal to 510 is equal to P naught A. What is Chi A? Chi A means moles of A divided by total moles. So 1 by 4 plus 1, 5 plus P naught B multiplied by Chi B. Chi B here means mole fraction of B in the solution, which is 4 by 5. If I take 5 as the common in the denominator, so 5 multiplied by 510 will be 2550 is equal to P naught A plus 4 times P naught B. This is my equation number 2. If I solve both the equations, equation 1 is 2550 is equal to P naught A plus 4 times P naught B. Equation number 2 is 2000 is equal to P naught A plus 3 times P naught B, right? If I subtract these two equations, this term cancels. This value will comes out to be 550 is equal to 4 P naught B minus 3 P naught B comes out to be P naught B. So P naught B I got to know as 500 mm of Hg. 500 mm of Hg. This is my P naught B. If you got P naught B, now put the value of P naught B in any of these two equations, you will be getting P naught A as well, right? If you put P naught B in this equation, for example, or this equation, right, you'll be getting P naught A. And as far as I remember, it comes out to be 350 mm of Hg. 350 or 250, something like that. All clear? All clear, people? Let me know once the chats. So with this, our Rault's law is clear. Now, let's take a break. I'll have my dinner. You also have your dinner and stuff, and be back. I would want every one of you to be back on time, okay? Because we are going to discuss something very, very, very important now. Is it a promise that all of you guys will be back? Is it a promise? See, the class will end at, what is the time? See, at 11:30 we'll be back. So 11:30 to 12:30 will be done with ideal 9 or non-ideal. So from 12:30 to the class will end at 3:30, something like that. 3:30 class will end. You will have to be with me till the end. Yeah, that's the estimated duration. 3 to 3:30. Perfect. Chalo, I'll have my dinner. Be back at 11:30 sharp. Huh? Till then, you guys carry on. Are you guys back? Yeah. Are you all back? Welcome back, people. Welcome back. What's up? What's up? So, guys, whatever stuff we discussed till now, is every single thing clear? Yes, I'm done with my dinner. I'm done with my dinner, yes. I had some chicken mutton. So tell me, all the concepts are clear till here? Perfect, perfect, perfect. Of course, full non-veg. Yes, I am. All right, then should we get going? All ready, people, then? All ready, all ready, all ready. Let's get going. Let's get going. So, people, till now we are done with the Rault's law. Now it's time to discuss the ideal, non-ideal solutions. Right? It's time to discuss the ideal, non-ideal solution. So, what are these ideal, non-ideal solutions? Let's get to know about them in detail, right? Let's see what kind of concepts can be asked from these ideal, non-ideal solutions in detail. So, have a proper eye on this particular topic. Okay? Ideal, non-ideal solutions. First of all, how do we exactly define the ideal solution? How do we exactly define the ideal solution? Let me tell you, ideal solutions are the ones which obey Rault's law under all concentrations, and temperature. Those particular solutions which obey the Rault's law under all conditions, under all concentrations and temperatures, those are what we call as ideal solution. What exactly is meant by this particular statement, you'll get the idea in some time. So, but before making you understand all this stuff in detail, you write down the definition of non-ideal as well. Then I'll make you understand one by one what these ideal, non-ideal solutions exactly are all about. Non-ideal solutions, they do not obey the Rault's law. What exactly is meant by all this? See, guys, this is something which is important. Okay, and I would want you guys understand this stuff in a proper way. Just a second. Just a second. All right, so have a look. What exactly are ideal and non-ideal solutions? Perfect. See guys, for example, imagine that over here I've taken a container, and in this particular container, imagine that I have kept a solution of A and B. Imagine that I have kept a solution of A and B, wherein A as well as B, both are, for example, volatile in nature. If both are volatile in nature, over here in this part of the container, you will find vapors of A and B, right? And you will find the vapors of A and B. Perfect. So my dear students, this particular solution will have some vapor pressure, which I denote with PS. PS is basically the total vapor pressure of the solution. Now, let me exactly tell you. Vapor pressure of the solution, we can calculate by two ways. Vapor pressure of the solution, we can calculate by two ways. Number one, vapor pressure of the solution can be calculated with the help of Rault's law. And as per Rault's law, vapor pressure of the solution should be equal to P naught A chi A plus P naught B chi B. That is one way of calculating vapor pressure of the solution. Correct? And whenever vapor pressure of solution is calculated with the help of Rault's law by doing certain calculations, that is something which you call as theoretical vapor pressure of the solution or expected vapor pressure of the solution or calculated vapor pressure of the solution. Yeah? Whenever vapor pressure of the solution is calculated with the help of Rault's law by doing certain calculations. Okay? That vapor pressure of the solution which we calculate with the help of Rault's law is something which you call as theoretical, expected or calculated vapor pressure of the solution. Now, my dear students, let me tell you. In order to calculate vapor pressure of the solution, you can go for the experimental mode as well. Whenever vapor pressure of the solution is calculated in the lab with the help of certain experiments, that vapor pressure of the solution which is calculated experimentally, you call it either experimental vapor pressure of the solution or you call it as observed vapor pressure of the solution or you call it as the actual vapor pressure of the solution. You call it as the actual vapor pressure of the solution. So my first point is vapor pressure of the solution can be calculated by two ways. Theoretically with the help of Rault's law, experimentally by carrying out certain experiments, right? This is something which I would want you guys to remember. Now, my dear students, what you will observe? You will observe certain things. For example, there will be some solutions in which observed vapor pressure, which is what you call as experimental vapor pressure, or the actual vapor pressure of the solution, will come out to be same as what you had calculated theoretically with the help of Rault's law. And those sort of solutions for which experimentally determined vapor pressure comes out to be same as what you have calculated as per Rault's law, we call those solutions as the ideal solutions. Well, there are some solutions for which observed vapor pressure the actual vapor pressure of the solution comes out to be different than that of theoretically calculated vapor pressure, which we had calculated as per Rault's law. And those solutions are what you call as non-ideal solution. Those are what you call as non-ideal solutions, right? Those are what you call as non-ideal solutions. So we have got two types of solutions, as I told you. One is your ideal solutions and one is your non-ideal solutions. In case of the ideal solutions, as I told you, in case of the ideal solutions, what you are going to observe, in case of ideal solutions, the experimentally determined vapor pressure of the solution comes out to be same as that of what you had calculated theoretically, right? In case of non-ideal solutions, I would say experimentally determined vapor pressure of the solution comes out to be different than that of what you would have calculated theoretically. Perfect. You call them as the non-ideal solution. Now, there are two ways. There are two things over here. In case of non-ideal solutions, there are two things. Number one, first case, since observed and theoretical vapor pressure of the solution comes out to be different, right? Comes out to be different. So two cases will arise over here. Either the observed vapor pressure, the actual vapor pressure, the experimentally determined vapor pressure of the solution will come out to be greater than that of theoretical, or the observed vapor pressure of the solution, experimentally determined vapor pressure of the solution, right? Actual vapor pressure of the solution comes out to be less than that of theoretical. Okay, these are the two possible cases which can arise here. Let me tell you, that sort of solution for which experimentally determined vapor pressure comes out to be greater than that of theoretically determined vapor pressure, you say that non-ideal solution shows positive deviation from the Rault's law. That non-ideal solution shows positive deviation from the Rault's law, right? Similarly, this sort of a solution we say shows negative deviation from the Rault's law. This sort of a solution shows negative deviation from the Rault's law. Okay. Now let's try to understand this ideal, non-ideal in a better way. Let's exactly see what kind of conclusions we have to remember in case of ideal, non-ideal solutions. See guys, so first of all, I'm marking the heading over here as ideal solutions. Let's have a detailed overview of the ideal solutions. Okay, let's have a detailed overview of the ideal solutions. So people, as I told you, or let me make you understand like this. For example, I'm taking few containers here so that I can make you understand all this in a better way. Okay, I've taken 3 containers over here. In the first container, what do we have? In the first container, we have got a volatile liquid A. A volatile liquid A. In this particular container, we have got a volatile liquid B. Perfect. Here you'll be having vapors of A. Here you'll find vapors of B. Now, you're adding them, you're mixing them in this final container. So over here, what do we get? We'll be getting a solution of A and B. We'll be getting a solution of A and B. Here you'll find the vapors of A as well as vapors of B. Perfect. So in order to calculate vapor pressure of this solution, how many ways do we have? 2 ways. Either I'll calculate vapor pressure of the solution with the help of Rault's law, which is what I call as theoretical vapor pressure, or I'll be calculating vapor pressure of this solution experimentally. You call that as the actual observed vapor pressure of the solution. Correct? So I've got 2 ways to calculate its vapor pressure. Now, my dear students, as I told you, in case of ideal solutions, the experimentally determined vapor pressure of this solution will come out to be same as that of the theoretically determined. That means the actually determined vapor pressure of the solution will come out to be same as that of vapor pressure of solution calculated as per Rault's law. So that means the observed vapor pressure, the actual vapor pressure will be coming out to be same as that of P naught A chi A plus P naught B chi B. It will come out to be same. It will come out to be same. Okay? It will come out to be same. When is this possible? When is this possible? When the actual vapor pressure will come out to be same as what you had calculated from the Rault's law. It will come out to be same only if observed partial vapor pressure of A, if actual partial pressure of A and actual partial pressure of B will come out to be same as what you had calculated as per Rault's law. And as per Rault's law, this was supposed to be equal to P naught A chi A. This was supposed to be equal to P naught B chi B. And experimentally, you get the partial vapor pressures of A and B the same as what you had calculated with the help of Rault's law. Did you understand this? Did you understand this? Now, my dear students, few more things in case of the ideal solutions. First of all, in case of this particular liquid, what kind of interactions do we have? We have got AA interactions in this liquid. In this liquid, we have got BB interactions. In this particular solution, we have got AB interactions. Now, my dear students, understand one simple thing. Understand one simple thing. Understand one simple thing, which I'm going to tell you now. See, first of all, I would say in this particular liquid, there are A interactions. In this liquid, there are BB interactions. In this liquid, there are AB interactions. Okay. For the liquid A and B to mix, what is meant by that? What is meant by that? I'll say it like this. For this AB interaction to get formed, I would say this AA interaction has to get broken down first. This BB interaction has to get broken down first. Then only AB interaction will get formed. So first, this A bond has to be broken down. BB bond should get broken down. Then AB bonds will get formed. Now, in case of ideal solutions, what you will observe? In case of ideal solutions, all the interactions, A interactions, BB interactions, and AB interactions, all the interactions are same. In case of ideal solutions, all the interactions are same. Okay, all the interactions are same. If all the interactions are same, in case of ideal solutions, imagine volume of this liquid as V1, imagine volume of this liquid as V2, imagine volume of this solution as VR. If all the interactions are same, that means whatever force of attraction is between A and A, same force of attraction is between, same magnitude of force of attraction is between B and B, same magnitude of force of attraction is between A and B, right? In that particular case, I would say volume of the resulting solution, volume of the final solution will be same as that of V1 plus V2. If volume of the resulting solution is same as that of V1 plus V2, can you let me know, will there be any change in the volume during mixing? Since all the interactions are same, I would say change in the volume during mixing will be 0. Change in the volume during mixing will be 0. Right? Okay. If by chance AB interactions were weaker, if AB interactions were weaker than that of AA and BB, if AB interactions were weaker, then final volume of the solution should have been more than that of V1 plus V2. If final volume of the solution was more than that of V1 plus V2, at that point of time, I would say volume expansion would have happened. Right? So change in volume should have been positive. Final volume is greater than initial volume. So final minus initial would be coming out to be positive at that time. But over here, since all the interactions are same, right? Since VR is equal to V1 plus V2, there will be no change in the volume during mixing. There will be no change in the volume during mixing. Right? There will be no change in the volume during mixing. Similarly, as I told you, for this interaction to get formed, this bond should get broken down. This should get broken down. This should get formed. Bond breakage is endothermic. So energy is absorbed here. Energy is absorbed here. Bond formation is exothermic. Energy is released here. Right? Energy is released here. Absorbed, released. Since all the interactions are same, all the force of attraction between A and A, between B and B, between A and B, since all the force of attraction is same, so I would say during mixing, net heat absorbed is equal to net heat released. I would say during mixing, heat released is equal to the heat absorbed. Is equal to heat absorbed. If heat released is equal to heat absorbed, I would say delta H, mixing. If heat released is equal to heat absorbed, therefore the overall mixing process is neither endothermic nor exothermic. Right? is neither endo, overall mixing. It is neither endo nor exo. Perfect, overall mixing process. And if it is neither endo nor exo, so no net heat released, no net heat absorbed. No net heat released, no net heat absorbed. Perfect. So delta H mixing has to be 0. Delta H mixing has to be 0. Similarly, few more points which I would want you guys to remember directly. Delta S mixing, entropy change during mixing, will be positive. Entropy change during mixing. Whenever you'll be mixing two liquids, delta S you'll be always taking as positive. Entropy always increases during mixing. Entropy always increases during mixing. Okay, delta H is positive. Delta S is positive. Now, whenever you'll be mixing the two liquids, right? Delta G mixing, you'll be always taking as negative. Delta G mixing, you'll be always taking as negative. Okay, one more important point. Anything can be asked out of these points. Okay? Entropy always increases during mixing. Perfect? Right? Perfect, guys? You can see it like this also. You know, delta G is equal delta H minus T delta S. Since delta H mixing is positive, is 0. Delta S is positive. Positive, negative makes it negative. So delta G is equal to negative here, right? Delta G is equal to negative. Delta G is equal to negative here. Now, my dear student, remember one more thing. Since experimentally determined vapor pressure and theoretically determined vapor pressure of the solution comes out to be same, what does that mean? That means observed boiling point, experimentally determined boiling point of the solution is same as that of theoretically determined boiling point of the solution, right? Is equal to theoretically determined boiling point of the solution. Perfect. So do remember all these things. They can be asked. Anything can be asked out of these points in your upcoming NEET examination. And my dear students, one more thing. You are going to remember its examples as well. Examples of ideal solutions. Here I have already mentioned. These examples, right? You are going to remember them for now. When I'll teach you chemical bonding, when I'll teach you different types of interactions, ion, dipole, etc., etc. At that point of time, after studying that, by just looking at the examples, you'll check. I mean, you'll be in a position to say whether the resulting solution is going to be ideal or not. But right now, I would want you guys to remember these. Our next chapter is chemical bonding. And after we are done with chemical bonding, automatically I'll tell you, you'll be in a position to say whether the final solution, which you are getting after mixing two liquids, whether that's going to be, your ideal or non-ideal. Okay, for now, I would want you guys to remember that. So these were your ideal solutions. Now, if I talk about non-ideal solutions, let me mark the heading as non-ideal solutions. What kind of non-ideal solutions? Showing positive deviation. Let's talk about this. Non-ideal solutions showing positive deviation. Before talking about non-ideal solutions showing positive deviation, there is one more thing which I would want to tell you over here. My dear students, if you remember the graph which we made long back, like this. I hope you remember this graph. This was vapor pressure versus mole fraction of a component in the solution. At this point, chi A is, for example, 0, chi B is equal to 1. So there is only B in the container, right? So vapor pressure due to pure B is going to be P naught B. And since there is no A, therefore vapor pressure due to A right here is 0. Over here at this particular point of time, if you remember, your chi A was 1 and chi B was 0. So at this point, pure A is there in the container. So whatever is the vapor pressure of the container, that's due to pure A, which I'm representing with P naught A, for example. And here, since there is no B in the container, so vapor pressure due to B is 0, right? If you remember, we had made a graph like this. On moving from left to right, chi A increases. That means moles of A in the solution increases. Therefore, vapor pressure due to A will increase. And the graph used to be like this. Right? its equation used to be PA is equal to P naught A chi A. Similarly, over here the graph used to be like this, and equation for this used to be PB is equal to P naught B chi B, right? And this straight line used to represent the vapor pressure of the solution, which used to be equal to P naught A chi A plus P naught B chi B. Basically, this particular curve which we already made, let me tell you, this is basically valid for the ideal solution. This is valid for the ideal solution. Okay? This is valid for the ideal solution. Perfect. Now, guys, I'm moving on to non-ideal solutions showing positive deviations. As I told you, what are non-ideal solutions showing positive deviations? In case of non-ideal solutions showing positive deviations, what happens exactly? See, guys, understand. For example, I'm taking certain containers again so that it'll be easy for you to visualize this stuff, right? Over here in this particular container, what do we have? We have got liquid A. We have got liquid A, volatile liquid A. Here you have got volatile liquid B in the container, right? And over here you have mixed them up. You have got a solution of A and B. A solution of A and B. A and B both are volatile, right? A and B both are volatile. Now here you will find only the vapors of A. Here you find only the vapors of B. Here you will find the vapors of A as well as B, right? Now, I'm assuming this particular solution right now, it is the non-ideal solution showing positive deviation. Showing positive deviation. That means right now, I can say like this. I'll say experimentally determined vapor pressure of the solution. Experimentally determined vapor pressure of the solution. Actual vapor pressure of the solution will be coming out to be greater than what we expected as per Rault's law. As per Rault's law, we expected vapor pressure of the solution to be P naught A chi A plus P naught B chi B, right? I mean, as per Rault's law, we expected the vapor pressure of the solution to be P naught A chi A plus P naught B chi B. But in reality, the actual vapor pressure of the solution will be greater than this, which is only possible if the actual partial vapor pressure of A, actual partial pressure of A will be greater than what we expected as per Rault's law. How much we expected as per Rault's law? We expected it to be this much, P naught A chi A, right? But in reality, the actual partial vapor pressure of A will be greater than this, and actual partial vapor pressure of B will be greater than P naught B chi B. Okay? Now, some very, very, very important points. So very, very, very important points. See guys, as I told you, over here in this liquid, you will find A interactions. In this liquid, you will find BB interactions. In this liquid, you will find AB interactions, right? Let's say volume of this liquid is V1, volume of this liquid is V2, volume of this solution is VR, right? Now, in case of non-ideal solutions showing positive deviation, remember, AB interactions are weaker. AB interactions are weaker than expected. AB interactions, they are weaker than expected. If these interactions are weaker than expected, that means, if these interactions are weaker than expected, that means the actual vapors generated, will they be lesser or greater than the expected vapor generated? Quickly guys, what do you think? If AB interactions are weaker than expected, so basically AB interactions are weaker than ABB. We expected all the interactions to be same as per Rault's law, but in reality, AB interactions were weaker than that of ABB. AB interactions were weaker than expected. So the actual vapors generated here will be greater than what we expected as per Rault's law. Okay? Due to which, that is the reason why actual vapor pressure of the solution comes out to be greater than the expected vapor pressure of the solution. Right? Perfect. One more thing. One more thing. I hope you got this particular point. If AB interactions are weaker than expected, so actual amount of vapor generated will be greater than expected vapors. If actual vapor generated are more, that means actual vapor pressure of the solution will be more than expected, which I wrote over here. Actual vapor pressure is more than expected. Now guys, tell me one thing. If AB interactions are weaker than expected, that means volume of the resulting solution will be greater than that of V1 plus V2. If volume of the resulting solution is greater than V1 plus V2, tell me what about delta V mixing? Is delta V mixing going to be greater than 0? Delta V mixing is going to be greater than 0, right? Similarly, delta H mixing. Delta H mixing. See, first of all, for the AB interaction to get formed, this has to be broken down. This has to be broken. At the end, this will get formed. This is endothermic. Heat is absorbed. Heat is absorbed. Heat is released. Now, this AB interaction is weaker than expected. So, I would say net heat released, net energy released will be less than that of net energy absorbed. So, overall process of mixing, during overall process of mixing, is the heat absorbed or released? Is the heat, I'll say net heat is absorbed during the process. If net heat is absorbed during the process, I would say delta H mixing will be positive. Overall process of mixing is endothermic here. Right? Perfect. Now guys, as I told you during mixing, delta S is always positive, right? Delta S is always positive. Now what about delta G? Delta G, you know, is equal to delta H minus T delta S. Correct? Delta H is positive here. Delta S is positive over here. Delta H is positive. Delta S is positive. So delta G can be only negative if magnitude of T delta S will be greater than that of magnitude of delta H. Right? Delta G mixing will be negative. Right? When T delta S will be greater than that of delta H, which is possible at higher temperatures or lower temperatures. At higher temperature. I hope this is clear. I hope this is clear. One more thing. One more thing, guys. One more thing. Since the actual vapor pressure is more, observed vapor pressure is more, that means observed boiling point. Actual boiling point. Will it be more or less? If the actual vapor pressure is more, what is boiling point? The temperature at which vapor pressure becomes equal to atmospheric pressure. Actual vapor pressure is more. Theoretical vapor pressure is less. In order to make this actual vapor pressure equal to atmospheric pressure, will be increase the temperature? Will be increase the temperature from here to here. Here you have to increase the temperature from here to here. I hope you are visualizing this properly. Right? See, actual vapor pressure here is more than expected. If actual vapor pressure is more, so you will have to make that actual vapor pressure equal to atmospheric pressure. You have to increase the temperature. Perfect. You have to increase the temperature. Now, in case of the theoretical one, the actual vapor pressure is comparatively less. You have to increase the temperature more in this case, in case of theoretical one. So, remember the actual boiling point will be less than that of theoretically determined boiling point. Right? Is it clear? Is this particular point clear? How come this actual boiling point will be less? Because actual vapor pressure is more. In order to make that vapor pressure equal to atmospheric pressure, right? No doubt, you have to increase the temperature, but not that much as compared to the theoretical one. There you have to increase the vapor pressure more. You have to increase the temperature more. Is it clear? Is it clear, people? So these are all the parameters which can be asked. Now, what about its graph? What about its graph? Let me show you the graph showing the non-ideal solutions. See, this was the graph showing the ideal solutions, right? Now, the graph showing non-ideal solutions. Understand. In case of non-ideal solution showing positive deviation, this was your expected partial vapor pressure of A, but actual partial pressure of A is more than expected. The graph will come above this. Okay, perfect. Wait just a second. Let me erase this stuff so that I can write it properly. Okay, so this was your PA was supposed to be equal to P naught A chi A, but in reality, it came out to be greater. So you'll say PA is greater than your P naught A chi A. Similarly, this was for PB. PB was supposed to be equal to P naught B chi B, but in reality, it will be greater. In reality, it will be greater. So this graph will come like this. So your PB is greater than P naught B chi B. P naught B chi B. This was supposed to be for PS, which was supposed to be equal to P naught A chi A plus P naught B chi B. But over here, it will be greater than that. So PS here will be greater than that of P naught A chi A plus P naught B chi B. This particular graph is valid for the solution. Which solution? I will say non-ideal solution showing positive deviation. Correct? Non-ideal solution showing positive deviation. Right? And guys, here I would want you guys to remember few examples of non-ideal solutions showing positive deviations. These are your examples of the solutions which form non-ideal solutions and show the positive deviation from the Rault's law. Okay? Again, I'm telling you, since I did not teach you the interactions yet, I did not teach you chemical bonding yet. Once we are done with chemical bonding, you'll be in a position to decide whether the solution is showing non-ideal with positive, non-ideal, negative, etc., etc. Right now, just remember them as such. Okay? Remember them as such. Perfect? Now, what is next? Next is non-ideal solutions showing negative deviation. I think this one you can easily interpret now. Non-ideal solutions showing negative deviation. Non-ideal solutions showing negative deviation. So tell me all the parameters now. It will be just reverse of what? It will be just reverse of what we discussed in the positive deviation. So first thing, the actual vapor pressure of the solution, experimentally determined vapor pressure of the solution, that will be less than expected, less than P naught A chi A plus P naught B chi B. Number one, the actual partial vapor pressure of A will be less than that of P naught A chi A. Similarly, the actual vapor pressure of B will be less than that of P naught B chi B. Okay, this was point number one. Point number two. Perfect. How come that is possible? How come actual vapor pressure will be less? When AB interactions are stronger than expected. In this particular case, AB interactions are stronger than expected. That is why vapors generated are less and actual vapor pressure is less than that of theoretical. Actual vapor pressure is less than that of expected vapor pressure. Are stronger than expected. Are stronger than expected. Right? Stronger than expected. Now, if AB interactions are stronger than expected, therefore, final volume of the solution will be less than that of V1 plus V2. Therefore, delta V mixing, change in volume during mixing, will be positive or negative. It will be negative, right? Similarly, if final interactions are stronger, that means net heat is released during the process. Net heat is released during the process. Therefore, delta H mixing here has to be negative, right? Similarly, delta S mixing is always positive. Now, delta G mixing is equal to delta H minus T delta S. Now, as I told you, delta H is negative, delta S is positive. Delta H is negative, delta S is positive. Right? So overall delta G will come out to be negative only, right? So you can say delta G mixing is negative. Now tell me about actual boiling point of solution and theoretical boiling point of the solution. Which boiling point will be more? Since the actual vapor pressure of the solution is less, right? Experimentally determined. Observed vapor pressure of the solution, that is less than expected. Observed vapor pressure of the solution is less than expected. So in order to make that observed vapor pressure equal to the external pressure, equal to the atmospheric pressure, you have to increase the temperature more. Here you have to increase the temperature less, right? So I would say observed boiling point will be more than that of theoretically determined boiling point. Perfect. And guys, remember its examples as well. These are the examples. All the inorganic acids, when mixed with water, they lead to the formation of non-ideal solutions showing negative deviation, right? Okay, so these are some of the common examples of non-ideal solutions showing negative deviations. Perfect. Now, one thing is left here, that is the graph. That is the graph. Let me show you the graph over here as well. Let me show you the graph which shows non-ideal solution showing negative deviation. Just wait a second. Where is it? Here is the one. So right now I need to show you non-ideal solution showing negative deviation. Correct? Guys, you should be already in a position to answer this now. This was supposed to be your partial vapor pressure of A, which used to be equal to P naught A Ka A. That was something which I was expecting, but in reality it's less than that. In reality it's less than that. So PA is less than P naught A. Was this for PA or PB? Let me check it first. This was for PB. So I would say PB is less than that of P naught B Chi B. Okay. Similarly, over here, this was for PA, but in reality now it will be less than this. So PA is less than that of P naught A Chi A, and here this is going to be PS, which will be less than that of P naught A Chi A plus P naught B Chi B. So this is for the non-ideal solution showing negative deviation. This graph is for the non-ideal solution showing negative deviation. Is it clear, guys? Are all these things clear now? Yeah? I'll just summarize all this. Whatever I've discussed in the ideal, non-ideal solutions, I'll summarize it in one single slide. Okay, so that it will be easy for you to remember this stuff. I'll summarize it in just one slide. Here I'm mentioning the ideal solution. Here I'm mentioning non-ideal solutions showing positive deviation, non-ideal solutions showing negative deviation, right? So let's summarize it in one slide so that all your questions, right, will be out of this particular slide. See, guys, the first point here, the observed vapor pressure of the solution will be same as that of P naught A Chi A plus P naught B Chi B. Correct? The actual partial pressure, the actual partial vapor pressure of A is equal to that of P naught A Chi A. Similarly, the actual partial vapor pressure of B is same as what you had expected as per Rault's law, which is P naught B Chi B. Right? Point number 3. Point number 3. AB interactions is equal to BB interactions is equal to AB interactions. All is equal to A interactions. All the interactions here are same. Okay? Delta V mixing here is 0. Delta H mixing here is 0. Okay? Delta S mixing here is positive. Delta G mixing here is negative. Observed boiling point is equal to the theoretically determined boiling point. Perfect. And the examples which I would want you guys to remember, the examples which I gave you, okay, with the example. Now go to the non-ideal solution showing negative deviation. If you talk about non-ideal solution showing negative deviation, sorry, positive deviation, first of all, the total vapor pressure, the experimentally determined vapor pressure of the solution will come out to be greater than that of, greater than the expected, greater than P naught A A plus P naught B B. This is possible only if the observed partial vapor pressure of A will be greater than that of P naught A A and this will be greater than that of P naught B B. P naught B B. Third point. A-B interactions are weaker than expected. Are weaker than expected. Delta V mixing will be positive. Delta H mixing will be positive. Delta S mixing is positive. Delta G mixing, since it is positive deviation, so observed boiling point will be less than that of theoretically determined boiling point. And after that, remember its examples. Or before the examples, write one more statement. Write it for now. Non-ideal solutions showing positive deviation, they form minimum boiling azeotrops. There is a question which can be directly asked. Which of the following shows minimum boiling azeotrops? Do you remember non-ideal solution showing positive deviation? They are going to form the minimum boiling azeotrops. Okay. Then later on, remember its examples as well. What is the next thing? Next thing is non-ideal solution showing negative deviation, right? In case of non-ideal solution showing negative deviation, observed vapor pressure will be less than that of expected, less than that of P naught A plus P naught B B. This is possible only if P observed of A is less than that of P naught A and P observed B will be less than that of P naught B B. Correct? A-B interactions are stronger than expected. Correct? Delta V mix, negative. Delta H mix, negative. Delta S mix, positive. Delta G mix, negative. Observed boiling point, the actual boiling point of the solution, will be greater than that of theoretical boiling point of the solution. And remember, non-ideal solutions showing negative deviation, they form the maximum boiling azeotrops. And at the end, remember its examples. So let me know in the chats if it is clear to everyone or not. Quick, people. I would want every one of you to let me know in the chats quickly if all these things are clear. If all these things are super clear. Yeah? Wake up, guys, wake up. It's not the time to sleep. In I believe 2-3 more hours will be done. 3 more hours will be done, okay? Perfect. Should we move on then? Should we move on? Yes, guys, 3 more hours. It's okay. What's wrong? Just 3 more hours. Okay, perfect. Great. Let's move on. Now we are going to talk about the colligative properties. Colligative properties. So, my dear students, how do we exactly define the colligative properties? How do we define them? Okay, how do we define it? First of all, let me write the definition. Let me tell you, these are the properties. These are the properties of ideal solutions. These are the properties of ideal solution, whose value depends only upon, whose value depends these are the properties of the ideal solutions whose value depends only upon the number of particles of solute. These are the properties of the ideal solutions whose value only depends on the number of particles of solute. Does not depend upon the nature of solute. So basically, there are some properties of the ideal solutions whose value only depends on number of particles of solute. So what does that mean? That means there are certain properties of the solutions whose value changes on changing the number of particles of solute. There are some properties of solute. There are some properties of ideal solutions whose value changes on changing the number of particles of solute. Does not depend on the nature of solute. You call those properties as the colligative properties. So colligative properties are the ones whose value depends only upon the number of particles of solute, does not depend on the nature of the solute. We have 4 types of the colligative properties over here which we have to study. The first one is your relative lowering in vapor pressure. Relative lowering in vapor pressure. This is the first colligative property which we have to discuss. Second is the elevation of boiling point. Third one is the depression in freezing point. Depression in freezing point. And fourth one is the osmotic pressure. These are the 4 colligative properties, my dear students, which we have to discuss over here. So first of all, these are the 4 properties. These are the 4 properties of the ideal solutions whose value only depends on the number of particles of solute, whose value changes on changing the number of particles of solute, does not depend on the nature of the solute. One on one, we have to discuss these colligative properties, right? And out of these colligative properties, the first one is going to be your, out of these colligative properties, the first one is going to be your relative lowering in vapor pressure. A relative lowering in vapor pressure. Mark the heading here as relative lowering in vapor pressure. A relative lowering in what? In vapor pressure. Okay. See guys, a relative lowering in vapor pressure, what exactly it's all about. Already we have discussed, if you remember, or let me quickly rewind all the things so that it becomes clear to you properly. Let's say this is the container. in this particular container, I'm taking a volatile liquid A, right? So you will find vapors of A here, and its vapor pressure I'm representing with P naught A. Now, people, I'm adding a non-volatile solute B here in the container. When I'll be adding a non-volatile solute B in the container, what do I get? I'm adding a non-volatile solute B in the container. What do I get? I'll be getting a solution. This is a solution of A and B. This is a solution of what? Solution of A and B, out of which A is volatile, B is non-volatile, right? So over here, you'll only find the vapors of A. So the vapor pressure of the solution, which was supposed to be equal to PA plus PB, since B is non-volatile, B is not going to form the vapors. So B is not going to contribute towards the vapor pressure. So PS is nothing but, it is equal to PA, which is equal to P naught A, chi A, right? My dear students, if you remember, we have discussed one important thing already. On adding a non-volatile solute into a volatile liquid, what happens to vapor pressure? Does it increase or decrease? Vapor pressure decreases. I would say PS will be less than that of P naught A. So let me mark that 1 point over here. On adding a non-volatile solute in a volatile liquid, what happens to vapor pressure? Vapor pressure decreases. Full stop. This decrease in the vapor pressure, is called as lowering in vapor pressure, represented by delta P. Right? This is something which we already discussed long back. Correct? So my dear students, since we know on adding a non-volatile solute into a volatile liquid, vapor pressure decreases. And this decrease in the vapor pressure is what I call as lowering in vapor pressure. Lowering in vapor pressure is represented by delta P. Now, people, if I divide delta P with P naught A, if I divide delta P with the vapor pressure of pure solvent, this complete term, lowering in vapor pressure with respect to initial vapor pressure. This is something which we call as a relative lowering in vapor pressure. Which is equal to delta P, lowering in vapor pressure. How much? It is equal to P naught A minus PS. This is the lowering in vapor pressure. With respect to what? Initial vapor pressure. P naught A is equal to. So it's going to be P naught A minus. What is PS? PS is your P naught A chi A divided by P naught A. So P naught A cancel. 1 minus chi A comes out to be chi B. So in short, let me write it over here. P naught A minus PS divided by P naught A, which is what I call as a relative lowering in vapor pressure. It is equal to mole fraction of B. Mole fraction of B means mole fraction of non-volatile solute, which is nothing but number of moles of non-volatile solute divided by total moles present in the solution, Na plus Nb. This is the first result which we have to remember. And this entire term over here is what we call as a relative lowering in vapor pressure. Right? A relative lowering in vapor pressure is always equal to mole fraction of a non-volatile solute, which is equal to this much. And what is the relative lowering in vapor pressure? It is defined as lowering in vapor pressure with respect to initial vapor pressure. So people, let's try to have little more things of it. See, as I told you, just a second. Okay, as I told you, relative lowering of vapor pressure is P naught A minus PS divided by P naught A. And I told you it is nothing but NB divided by NA plus NB. This is the general result. Now, for a very dilute solution, if the solution is dilute, Solution is dilute means number of moles of solute are far less than number of moles of solvent. At that point of time, instead of Na plus Nb, you'll be only writing Nb. Sorry, instead of Na plus Nb, you'll be only writing Na. You'll be only writing Na. So my result becomes P naught A minus Ps divided by P naught A is equal to Nb divided by Na. And this particular result is valid only for the dilute solution. This particular result is only valid for the dilute solutions. This particular result is only valid for the dilute solution. Number one. Number two. Well, my dear students, sometimes it becomes difficult, right? It becomes difficult to check whether the solution is dilute, concentrated. It takes a lot of time. So, I'm going to give you one result for the numerical purposes, which is used for concentrated as well as dilute solutions. So, I'm writing over here as for numerical purpose. For numerical purpose, I'm going to give you one result. Just remember that. Just remember that. Since this particular result is only valid for the dilute solutions. Now, one result I'll be giving you. See, we know P naught A minus Ps. If I divide this with Ps, first of all, this is not something which I'll be calling as a relative lowering in vapor pressure. No, this is one result which I'm making just to solve the questions, nothing else. So P naught A minus Ps is equal to, this is P naught A minus, Ps is your P naught A chi A divided by, Ps is again your P naught A chi A. Correct? So P naught A cancel. 1 minus chi A is chi B divided by chi A. Chi B is nothing but number of moles of B divided by Na plus Nb. Similarly, chi A is nothing but Na divided by Na plus Nb. So Na plus Nb cancel. So I got one direct result. P naught A minus Ps divided by Ps is equal to Nb divided by Na. And this particular result is valid for concentrated as well as dilute solution. For concentrated as well as dilute solution. And I would suggest you to use this particular equation always. Okay? Right? So this was one result. And now I'm going to give you one more result. Have a look. See guys, P naught A minus Ps divided by Ps is equal to Nb. Nb. What is Nb? Number of moles of solute. Divided by. What is Na? Number of moles of solvent, which is basically mass of solvent divided by molar mass of solvent. And that molar mass of solvent goes to the numerator. If I divide with 1000, multiply with 1000, what will happen? Nothing will happen because I'm dividing as well as multiplying with 1000. So we will look carefully. What about this particular term? What about this particular term? Number of moles of solute divided by mass of solvent in grams multiplied with 1000. What do we call this as? This is something which we call as molality of the solution multiplied by Ma divided by what? Divided by 1000. So one more result which is used for the numerical purposes. I'm writing it over here. P naught A minus Ps divided by Ps is equal to molality of the solution multiplied by molar mass of solvent divided by 1000. Okay, this is one more important result. So 3 results I would want you guys to remember. Yeah? Did you understand all this stuff? Did you understand all this stuff till here? Let me know in the chats quick. Right, people? So just one thing you have to remember. On adding non-volatile solute into volatile liquid, what happens? Vapor pressure decrease. Decrease in the vapor pressure is what you call as lowering in vapor pressure. And lowering in vapor pressure with respect to initial vapor pressure, that's what you call as a relative lowering in vapor pressure. Yeah, that's what you call as a relative lowering in vapor pressure. And this is your relative lowering in vapor pressure. This is not the relative lowering. A relative lowering means lowering with respect to initial. This is not lowering with respect to initial. This is lowering with respect to final. I won't be calling this as a relative lowering. Okay, remember that. Remember that. Remember that. Let's try to solve a few questions. One simple and basic question this is. You should be in a position to solve this one on your own. Calculate the relative lowering in vapor pressure. Relative lowering means P naught A minus PS divided by P naught A. This is what you call as relative lowering in vapor pressure. It is always equal to what? This is what you call as a relative lowering in vapor pressure, RLVP. As per the question, we have to calculate this. And we know this is equal to what? Mole fraction of non-volatile solute, which is number of moles of solute divided by total moles present in the solution. Now look at the question. Calculate the relative lowering in vapor pressure if 100 grams of non-volatile solute are dissolved in 432 grams of water. So it will be equal to number of moles of solute will be equal to mass of solute, which is 100 grams, divided by molar mass of solute, which is again 100, divided by number of moles of solvent. Mass of solvent divided by molar mass of solvent. Molar mass of water is 18 plus number of moles of solute is 100 divided by 100. Solve this term and get the answer. Whatever value you get from here, that's going to give you the relative lowering in vapor pressure. And let me show you the exact answer. Relative lowering in vapor pressure here will come out to be this. Okay. Perfect. All clear, people? Here you can do the neglection as well, right? Here you can do the neglection as well. All right, look at one more question then. Look at one more question. Look at this one. The vapor pressure of an aqueous solution of glucose at 373 Kelvin is found to be 750 ml of Hg. The molality of the solution at this temperature will be. See guys, they are mentioning the aqueous solution. So basically, initially in the container, you would have taken water. Imagine this is pure water in the container, right? The temperature is kept as 373 Kelvin. 373 Kelvin is basically the boiling point of water, right? The boiling point of water. At the boiling point, you know, vapor pressure of the liquid is equal to external pressure, which is basically the atmospheric pressure. And generally, atmospheric pressure is how much? 760 ml of Hg. So since this water is kept at 373 Kelvin, this water is kept at 100 degrees centigrade, which is at its boiling point. Therefore, its vapor pressure has to be equal to atmospheric pressure. So I would say its vapor pressure right now, P naught A, vapor pressure of water in pure state, right now will be 760 ml of Hg. I hope this point is clear. Now, as per the question, what you are doing, you are adding a non-volatile solute. The vapor pressure of an aqueous solution of glucose. Yes, you are adding a non-volatile solute B over here, which is glucose. When you will be adding the non-volatile solute B in the volatile liquid, what will be happening? What would be happening? I'll say I'll be getting a solution. I will be getting a solution. This is the solution of A and B. This is the solution of A and B. This is the solution of A and B. Now, as per the question, vapor pressure of this solution is equal to 750 ml of Hg. 750 ml of Hg. What do we have to calculate? Molality of the solution. We have to calculate molality of this solution. Now, people, in order to calculate molality of the solution, I already gave you one result, which was P naught A minus PS divided by PS is equal to M multiplied by MA divided by 1000. This equation I gave you a few minutes back. So P naught A is 760 minus 750, that's 10. 10 divided by 750. 10 by 750 means 1 upon 75 is equal to molality multiplied by molar mass of solvent. Molar mass of water is 18 divided by 1000. Solve this equation. Get the molality of the solution, which you were supposed to calculate. Done and dusted, right? Right, people? Is it clear? Is it clear? Is it clear? What do you think about this one? You should be in a position to solve this basic question as well. Vapor pressure of water in pure state is given. The vapor pressure of the solution containing 5.40 grams of non-volatile solute in 90 grams of water is this much. Calculate the molecular weight of solute. It's a simple question, guys. See. Imagine this is the container, and in this particular container, what do we have? We have got pure water. We have got pure water here in this container. As per the question, vapor pressure of this pure water is equal to how much? 23.76 torr. Okay. Now what exactly are we doing? We are adding a non-volatile solute B over here. How many grams of it? We are adding 5.4 grams of this non-volatile solute B over here in 90 grams of water. Over here, the mass of solvent, the mass of water is given to me as 90 grams. Now, when you'll be adding a non-volatile solute, you'll be getting a solution. You will be getting a solution, right? So this is the solution over here in the container. This is the solution. This is the solution of A and B, right? This is the solution. Now, as per the question is concerned, vapor pressure of the solution is given to me. How much? 23.32 torr. Perfect. What do we have to calculate? Molecular weight of solute. We have to calculate MB, molecular weight of solute. So which result is easier for us to use? Which result is easier for us to use? You know, P naught A minus PS divided by PS is equal to NB divided by NA. Because here you are not supposed to check whether the final solution is dilute or concentrated, because this result is valid everywhere, right? So P naught A minus PS. P naught A minus PS. 23.76 minus 23.42 comes out to be 0.44 divided by, what is PS? 23.32 is equal to number of moles of solute is equal to mass of solute divided by molar mass of solute, whole divided by number of moles of solvent, mass of solvent divided by molar mass of solvent. One equation, one unknown. So you can easily calculate molar mass of solute over here, which you were supposed to calculate as far as the question was concerned, right? Am I clear, people, with this? Am I clear with this? Look here now. This is one more good question. What weight of non-volatile solute urea needs to be dissolved in 100 grams of water? So imagine you have got 100 grams of water here. Water I'm representing with A, right? Let's say its vapor pressure right now is P naught A. And how many grams of water we have here? 100 grams of water. So WA, mass of water in the container, is 100 grams. Now, as per the question, what are we doing? We are adding non-volatile solute B, which is urea. We are adding non-volatile solute urea in the container. Now, as per the question, what's happening? When we are adding non-volatile solute, into a volatile liquid, what happens? Vapor pressure decreases. Vapor pressure decreases. As per the question, what weight of non-volatile solute urea is added in order to decrease the vapor pressure by 20%? So we have to decrease the vapor pressure by 20%. For that purpose, what mass of urea is to be added? Mass of urea added, I'm representing with WB grams. So what I'll be doing, I took water in the container. Now I'll be adding urea. Non-volatile solute. Vapor pressure of this water will keep on decreasing. It will keep on decreasing. What weight of urea should be added to decrease the vapor pressure by 20%? That means if initially the vapor pressure was P naught A, now the vapor pressure should be P naught A minus 20% of P naught A. Right? Now this has to be the final vapor pressure of the solution. We have to add urea till vapor pressure of the solution comes out to be this much, right? Which comes out to be at the end 0.8 P naught. Perfect. What weight of solute should be added to decrease the vapor pressure by 20%? So initial vapor pressure was P naught. Now we have decreased the vapor pressure by 20% by adding a non-volatile solute, urea, over here. Okay. So people, it's done. Use the result. P naught A minus PS divided by PS is equal to NB divided by NA. P naught A, I'm writing as such. PS is nothing but 0.8 P naught A divided by PS is 0.8 P naught A is equal to NB, number of moles of solute, which is mass of solute divided by molar mass of solute, mass of solvent divided by molar mass of solvent. So P naught A cancel. 1 minus 0.8 is 0.2 divided by 0.8, which comes out to be 1 by 4 is equal. Mass of solute. How much mass of solute? WB. Divided by molar mass of solute. Molar mass of urea is 60. Divided by mass of solvent was 90 grams. Molar mass of solvent, molar mass of water, 18. So from here, you can calculate the mass of urea added. You can calculate the mass of urea added, right? So this was the first question. What mass of non-volatile solute should be added? So this much mass of non-volatile solute should be added, right? So you got the mass of solute added. Now what do we have to calculate? Molality. What do we have to calculate? Molality of the solution. You know, molality of the solution will be equal to mass of solute in grams multiplied by 1000 divided by molar mass of solute, mass of solvent in grams. WB, we would have already calculated. Molar mass of solute, you know 60. Mass of solvent, you know 90. Put it here and get the molality of the solution as well. You can use the direct result as well, right? You can use the direct result as well. Or you can use the other result, which I already gave you. P naught A minus PS divided by PS is equal to M into MA by 1000. You can use that as well. So these are different types of the questions which can be asked from your relative lowering in vapor pressure. And more questions will be framed when we discuss the Vant factor. Okay, this is one more question. You can take this as the homework. It is the similar sort of question. We have to calculate molar mass of solute. It is a similar type of question, people. Okay, all clear, all clear, all clear. All clear with this? Now I'm moving on to one more colligative property, which is your elevation and boiling point. Which is your elevation and boiling point, right? Which is your elevation and boiling point. Elevation and boiling point, or you can say elevation of boiling point, it is represented by delta TB. Delta TB. Okay, let me write a statement first of all. The statement is similar. The statement is same. On adding non-volatile solute in a volatile liquid, first of all, you know, vapor pressure decreases, number one, comma, boiling point increases. And this increase in the boiling point and this increase in the boiling point is called as elevation in boiling point, represented by delta TB. Represented by delta TB. Now understand. Understand, guys, what it's all about, what it means. What it means. See, guys, first of all, I'll give you the normal interpretation of this particular scenario, which I mentioned over here, right? Let's first of all try to understand what exactly it means. Imagine this is a container which contains your volatile liquid. This is the volatile liquid A in the container, right? This is the volatile liquid A in the container. Perfect. So this is my solvent. It is my pure solvent right now. Let's say this is water. Let's say this water. I'm assuming this water is right now at 25 degrees centigrade. Okay. Let's assume the vapor pressure of this water at 25 degrees centigrade is, for example, 100 mm of Hg. Just to make you understand. External pressure, which is atmospheric pressure, that is, for example, 760 mm of Hg. Okay. Now I want to boil this water. What is the boiling point? The temperature at which vapor pressure becomes equal to atmospheric pressure. Since right now the water is at 25 degrees centigrade, its vapor pressure is 100 mm of Hg. I want to make sure its vapor pressure goes from 100 till 760. For that purpose, I'll be raising its temperature. I'll keep on raising its temperature. Due to the raise in the temperature, its vapor pressure will be increasing. There will be a temperature at which vapor pressure of this water would have exactly become 760 mm of Hg. And that temperature is what I call as boiling point. So, boiling point of solvent, boiling point of water, you know it already, it's 100 degree. So at 100 degree, the vapor pressure of water would have become equal to what? 760 mm of Hg. Right? So do you see, we increase, the water was initially at 25 degrees centigrade and we increase the vapor pressure of water from 100 till 760. By how much amount? We increase the vapor pressure of water by this much amount. by this much amount. We increase the vapor pressure of water by this much amount. Okay? Perfect. Now, people, there is one more scenario. Imagine the same container we have. Imagine the same container. Again, I'm keeping water here. Again, I'm keeping water here. Now, in this water, the same amount of water I'm taking here. In this water, for example, which is right now at 25 degrees centigrade, I'm introducing non-volatile solute B. When you introduce non-volatile solute B at 25 degrees centigrade, what do I get? I get a solution. I get a solution. This is the solution of A and B, out of which A is volatile, B is non-volatile, right? And this solution is, imagine, at 25 degrees centigrade. At 25 degrees centigrade, will its vapor pressure be 100 or less than that? Vapor pressure will be less than that. Let's say it is 50 mm of Hg. At 25 degrees centigrade, its vapor pressure will be less, because you know, on adding non-volatile solute, vapor pressure decreases. Vapor pressure decreases. So at 25 degrees centigrade, vapor pressure of this solution, it will be less than 100. It will be less than 100. Correct? External pressure, atmospheric pressure is still how much? 760 mm of Hg. Now tell me one thing, if you want to boil this solution, that means you have to increase the vapor pressure of the solution from 50 till 760. So you have to increase the vapor pressure by how much amount? By this much of amount. You have to increase the vapor pressure by this much of amount. In case of pure solvent, you were supposed to increase the vapor pressure by 660 mm of Hg. Here you have to increase the vapor pressure by 770 mm, by 700 something mg, right? By 710 mm of Hg. So can I say over here you have to increase the temperature more? Yes. So if this solution boils at 100, that means this particular solution will be boiling at temperature greater than 100. Let's say at temperature 105 degree, vapor pressure of the liquid, which was 50, became equal to how much? Became equal to 760 at temperature 105 degree. Right? So do you understand what happened? Here I had a pure solvent. Here I had the solution. I had a solution containing non-volatile solute, right? Here I was supposed to increase the vapor pressure from 100 to 760. I was supposed to increase the vapor pressure by this much of amount. Here I have to increase the vapor pressure more, right? In case of a solution. So wherever I'll have to increase the vapor pressure more, there only I have to increase the temperature more. So I would say, in short, boiling point of solution will be more than that of boiling point of pure solvent. Let me know in the chats if it's clear. Did you understand this? Did you understand this? Let me know once the chat's quick, everybody. So on adding a non-volatile solute into a volatile liquid, what happens to vapor pressure first of all? Vapor pressure decreases. Initially the vapor pressure was 100 and here the vapor pressure was 50. So vapor pressure decreases, but boiling point increases. Initially the boiling point of pure solvent was 100. Now the boiling point of the solution is 105. Guys, is it clear? You can honestly let me know. You can honestly let me know if it is clear. You can honestly let me know if it is clear. Everybody. Everybody. So in short, here you had to increase the vapor pressure by 660. Here in case of solution, you have to increase vapor pressure more. That's all. Right? That's all. So, on adding a non-volatile solute into a volatile liquid, what happens to boiling point? Boiling point increases. And that increase in the boiling point is what you call as? That increase in the boiling point is what you call as elevation in boiling point. You call that as elevation in boiling point. So, your elevation in boiling point, I'm representing with delta TB, which is equal to, if I ask you how much boiling point has elevated, initially it was 100, now it's 105. So how much it has elevated? 5 degree it has elevated, right? So elevation in boiling point is basically boiling point of solution minus the boiling point of solvent, right? Simple, higher temperature minus lower temperature. That's all. If you look at its graphical interpretation as well, have a look then. Have a look. See guys, let's say here I'm plotting vapor pressure. Here I'm plotting temperature. Here I'm plotting temperature, right? Let's say this is the point at which vapor pressure, for example, is 1 atm. 1 atm means 760 mm of Hg. Okay. So first of all, this is the graph for, this is the graph, imagine, for a solvent, for a liquid solvent, right? You know, on increasing the temperature, vapor pressure increases. On increasing the temperature, vapor pressure of the liquid increases. And this is the point. This is the point at which vapor pressure of the liquid becomes equal to atmospheric pressure. You call this as boiling point of solvent. Correct? You call this as boiling point of solvent. Now tell me one thing. Tell me one thing, right? If this is the graph for solvent, the graph for solution, would it be over this or below this? Graph for solution containing non-volatile solute. Graph for solution. Graph for solution containing non-volatile solute. Will it be over this or below this? Since vapor pressure of solution is lesser than that of pure solvent. Vapor pressure of solution is lesser than that of pure solvent, right? So this would be the graph for the solution. Because vapor pressure of solution is lesser than that of vapor pressure of pure solvent. Right? Now guys, do you see one thing? Can I say this is the temperature? Can I say this is the temperature at which vapor pressure of solution becomes equal to external pressure? And that temperature at which vapor pressure of the solution becomes equal to external pressure, you call that as boiling point of solution. So from here to here, it is boiling point of solution. From here to here, it was boiling point of solvent. Boiling point of solvent, boiling point of solution. So you can see boiling point of solution, as you can see, is greater than that of boiling point of pure solvent. Right? On adding a non-volatile solute into a volatile liquid, boiling point increases. As you can see, boiling point has increased. This was the graph for pure solvent. This is the graph for solution. Right? Why the graph came below the solvent? Because you know, vapor pressure of the solution is less than that of vapor pressure of pure solvent. Right? Perfect. And guys, this particular gap is what you call as delta TB over here, elevation in boiling point. Okay. So elevation in boiling point, delta TB is nothing. It is boiling point of solution minus boiling point of solvent. So this gap is your elevation in boiling point. Perfect. Now, there are a few things which I would want to tell you about this elevation in boiling point. Elevation in boiling point is directly proportional to molality of the solution. It is directly proportional to molality of the solution. No colligative property depends on the nature of the solute. All the colligative properties, they depend on the number of particles of solute only, not on the nature of the solute. Okay? All right. I told you elevation in boiling point. First of all, if you want to have a quick overview of the things, remember it in like this. Remember it. See guys, on adding a non-volatile solute into a volatile liquid, vapor pressure decreases. Boiling point increases. That increase in the boiling point is what we call as elevation in boiling point. Elevation in boiling point is represented by delta TB. Now, elevation in boiling point, I'm telling you, delta TB is directly proportional to molality. Right? Now, think over it. More the molality of the solution. More the molality of the solution. That means there is more solute here. If there is more solute here, that means its vapor pressure will be very less. If its vapor pressure is very less, to make that vapor pressure equal to external pressure, you have to increase the temperature more. That means its boiling point will be more. Did you understand this? Did you understand, people, what I said? So more the molality, more the molality of the solution, lesser the vapor pressure of the solution. Lesser the vapor pressure of the solution. To make that vapor pressure equal to atmospheric pressure, you have to increase the temperature more. Okay, you have to increase the temperature more. Perfect. So this particular statement, I believe, is clear. Perfect. Elevation in boiling point. Elevation in boiling point is directly proportional to molality of the solution. Now, if you remove the proportionality sign, you'll be getting a constant here, Kb multiplied by m. What is Kb here? Kb is a constant, which is what you call as molar elevation constant. molal elevation constant, or you call it as the ebullioscopic constant. And this ebullioscopic constant, it is solvent dependent. It is solvent dependent, right? Let me tell you its units. Its units are degree centigrade per molal, or you can say Kelvin kg per mole, right? You can remember these two units of it as well. And people, if you want to define this kb, I can say if m is equal to 1, your kb is equal delta tb, right? So molar elevation constant, kb, is defined as elevation in boiling point of the solution whose molarity is 1. Elevation in boiling point of the solution whose molarity is 1, right? Elevation of the boiling point of the solution whose molarity is 1. Now, if you want to write this particular result in the elaborated form, you'll be writing delta TB is equal to KB multiplied by molality, which is mass of solute in grams, multiplied by 1000 divided by molar mass of solute, multiplied by mass of solvent in grams. Correct? This delta TB further you can write as TB solution minus TB solvent is equal to this much. Mass of solute in grams multiplied by 1000 divided by molar mass of solute, and this is mass of solvent. Perfect? And in order to calculate KB is calculated with the help of these results. These are some two results with the help of which we can calculate KB for a solvent as well, right? Now, first result is R T naught square divided by 1000 lb. See guys, R is the gas constant, or you can say solution constant here, whose value can be 8.314 joules per Kelvin per mole, or you will have to take 0.0821 atm liter per Kelvin per mole. Perfect. Or you'll be taking 1.98 calories per Kelvin per mole. These are the three values of R, out of which one of the value needs to be used. Now, what is T naught here? T naught represents boiling point of the solvent. T naught represents boiling point of the solvent. What is LV here? LV represents latent heat of vaporization per gram of solvent. Latent heat of vaporization per gram of solvent. Similarly, delta H vaporization is something which we call as latent heat of vaporization per mole of solvent. Per mole of solvent. Is there any other thing? No. M1 is molar mass of solvent. And this is Kb value for water, which you will be remembering from now onwards. And this is Kb value for benzene, which you'll be remembering from now onwards. Because sometimes in the question, they won't give you these values. You'll have to remember these values and solve the questions. I hope I'm clear with this. I hope I'm clear with this. I hope I'm clear with this. Yeah? Is it clear, guys? So, let's try to solve a few questions. Look at the first question on the elevation of boiling point. Look at the first question. What weight of sucrose should be added to 100 grams of water to have the boiling point of solution equal to 100.5? It's simple, guys. See, for example, this is the container which we have. And in this particular container, what do we have kept? We have kept water in the beginning, 100 grams of water, right? So mass of solvent here is 100 grams. This is water in the container. What is the boiling point of this solvent? Water. You know, boiling point of solvent, boiling point of water, that is nothing but 100 degrees centigrade, right? Now, as per the question, what weight of non-volatile solute? Urea or sucrose? It's not mentioned. What weight of sucrose? Yes, we are adding sucrose. What weight of sucrose should be added, right? To have the boiling point of solution, how much? To have the boiling point of solution, how much? See, this is the solution. This is the solution which we are getting after adding sucrose. Since we know when we'll be adding non-volatile solute into volatile liquid, boiling point increases. So we have to increase the boiling point from 100 to 105. So boiling point of solution here has to be 100.5. So that means we have to increase the boiling point. In order to increase the boiling point, non-volatile solute is to be added. Now the point is, what mass of non-volatile solute should be added? What mass of non-volatile solute should be added? Right? Okay. So I'll be using simply delta TB is equal to KB multiplied by molality. What is delta TB? Elevation in boiling point. How much boiling point has to elevate? 100 to 100.5. That means 0.5 degree. This is the elevation in boiling point. KB is given to me as 0.52. Molality means mass of solute multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent. Right? So this term approximately gets cancelled out. So 1 is equal to mass of solute, mass of non-volatile solute multiplied by 1000 divided by molar mass of sucrose is 342 multiplied by mass of solvent, mass of water is 100. So from this particular equation, you can calculate the value of W2, which you can call as WB as well. So this W2, this is the mass of solute that has to be added to increase the boiling point from 100 degree to 105 degree, 100.5 degree. Is it clear, guys? Is it clear, everyone? Is it clear, everyone? So you're saying 32 grams, might be 32 grams. Yes, you're right. Okay. There is one more question. After that, we'll start discussing one more colligative property, that is your depression of freezing point. Look at this one, guys. Can you solve this particular question? See, on dissolving 3.4 grams of sulfur in 40 grams of benzene, elevation on a boiling point was this much. Calculate the molecular formula of sulfur. It's a simple question. Let me give the hint of solving this question. See, delta TB is nothing but KB multiplied by M. Correct? How much is the elevation in boiling point? As per the question, it's 0.81. KB value is given to us as 2.52. Molality of the solution means mass of solute, which is 3.24 multiplied by 1000 divided by molar mass of solute, molar mass of sulfur, right? Multiplied by mass of solvent. How much is mass of solvent? 40. So from here, you can calculate the molar mass of solute, molar mass of sulfur. You can calculate from here, right? And as far as I remember, how much it comes out to be? Molar mass of sulfur. Sulfur is 32. 32 into 8 is how much? 256. So when you solve this, you get the answer as 256 grams per mole, right? This is the molar mass of solute, which you got over here. This is the molar mass of sulfur. This is the molar mass of sulfur, which you got over here. Now, sulfur which you added into the solvent. We did not know the formula for that sulfur. We did not know the molecular formula of sulfur. Let the molecular formula of sulfur added is Sx, right? Let's say this is the molecular formula of sulfur. So basically, we have to calculate this X. Since we got molar mass of sulfur, molar mass of Sx we got 256. Therefore, molecular mass of sulfur will be how much? Molecular mass of sulfur will be 256U. What is molecular mass? Molecular mass is basically sum of atomic masses. Sum of atomic masses. Sulfur has got the atomic mass of 32 multiplied by X. So I got the equation 32X is equal to 256. So X value after solving comes out to be 8. Therefore, the molecular formula of sulfur which we are adding into benzene is basically S8. Is that clear? Is this clear, people, to everybody? Is it clear to everybody? Quick. Yeah? I hope it's also clear to everyone. Now we are going to enter into depression of freezing point. Okay? Do you want to break for 10-15 minutes or continue? I'll give you only the break if you all be back after 10-15 minutes. Then I'll start with this. Okay? It's 1:10 right now. I'll see you all at 1:25. $125 or 130, quickly in the chats. 125 or 130. But guys, I would want every one of you to be back. I would want every one of you to be back, okay? That should be a promise. Break till what? 125 or 130? Quick. Chalo. Be back at 130 sharp. Okay? 130. I'll also have some water. And coffee maybe. But be back. We'll have to complete this chapter, guys. Because tomorrow you won't get time to see this. We'll have to complete this at any cost. So be back on time, please. See you. Is everyone back? Yeah. Sir is 1 minute late. Yes, yes, I am 1 minute late. Now what? Huh? Now what? Guys, just few more topics and we are done, right? It is 1:32 right now, so by 3:30 will be done. By 3:30 will be done. Should we start? Should we start? Before starting, let me ask you certain questions first. Okay? Let me ask you certain questions. Tell me, on adding a non-volatile solute in a volatile liquid, what happens to vapor pressure? Increase or decreases? Quick. Quick, people. What happens to vapor pressure? All right, decreases. Okay. What happens to boiling point? What happens to boiling point? Boiling point increases. Okay. And that increase in the boiling point is what you call as elevation in boiling point. Yeah? So on adding a non-volatile solute into a volatile liquid, first of all, vapor pressure decreases. Second, boiling point increases. Okay. Similarly, I'm writing a statement over here. We have already discussed what freezing point is all about in the beginning itself. Now we'll continue after that. Okay. See guys. I'm writing on adding a non-volatile solute in a volatile liquid. In a volatile liquid. Freezing point. Freezing point decreases. Freezing point decreases. And that decrease in the freezing point, is called as the depression in freezing point, represented by delta TF. So, when we add a non-volatile solute into a volatile liquid, first of all, vapor pressure decreases, boiling point increases, freezing point decreases. Okay, and that decrease in the freezing point is what you call as depression in freezing point. For example, imagine this is the container in which you have got a pure water. There is pure water in the container, right? It's a volatile liquid, right? It's a volatile liquid. What is the freezing point of water, first of all? Freezing point of water, all of you must be knowing, that is 0 degree. Now, when you will be adding a non-volatile solute here, what you will be getting? You will be getting a solution. Remember, freezing point of the solution will be less than 0 degree. For example, the freezing point of the solution now is -1 degree. So when you basically add a non-volatile solute into a volatile liquid, freezing point decreases. And that decrease in the freezing point is what you call as depression in freezing point. Okay? All right, I'll ask you one question here. When you freeze a solution, what does exactly freeze? Solute or solvent? What do you think? When you freeze the solution, what does actually freeze? Solute or solvent? It is the solvent that freezes. Okay? Remember this particular point. When you freeze the solution, it is actually the solvent that freezes. It is actually the solvent that freezes. Okay? Remember that stuff. Now let me explain this stuff graphically over here so that it becomes clear to you. So it is basically the solvent that freezes. When you freeze the solution, solute does not freeze, solvent freezes. Okay? Now guys, understand this. Have a look at its graphical approach. Vapor pressure versus temperature. Vapor pressure versus temperature. Now, imagine this graph over here, which I'm drawing. Let's say this graph is for the liquid solvent. Imagine this graph is for the liquid solvent. Similarly, imagine this particular graph. Imagine this particular graph is for the solid solvent. It is for the solid solvent. It is for the solid solvent. When you extend this, this is the point at which vapor pressure of solid and its liquid, vapor pressure of solid and liquid becomes equal. So this point I'm calling as freezing point of solvent. This point I'm calling as freezing point of solvent. Right? Now, my dear students, tell me one thing. If this was liquid solvent, pure liquid solvent, for the liquid solution, will the graph be above this or below this? We know vapor pressure of solution is less than that of solvent, right? So the graph for liquid solution will be like this. It is the graph for liquid solution. Now, when you extend this graph, see, it will cut here. Do you see at this particular point again the vapor pressure of liquid and solid becoming equal? At this point, the vapor pressure of liquid and solid is becoming equal. And this particular point over here, I'm calling this particular point as freezing point of solution. I told you already, in the solution, it is basically the solvent that freezes. Okay? This particular point is what I call as freezing point of solution. This was the freezing point of solvent. So see, freezing point of solvent, as you can see here, freezing point of solvent is more than that of freezing point of solution. Do you see this? From here to here, it's freezing point of solvent. From here to here, it's freezing point of solution, right? So freezing point of solvent is more, freezing point of solution is less. Perfect. This particular gap over here, which you see, this gap I'm talking about. This particular gap, right? This particular gap. This particular gap is what you call as delta TF, depression in freezing point. This particular gap over here, right? This is something which we call as depression in freezing point. Okay? And that depression in freezing point is represented by delta TF. Perfect? Perfect, guys? Well, I could not make this graph clearly. Let me make it once clearly so that you won't have any sort of confusion in this graph. Okay, let me make a bigger graph over here so that it will be clear to you properly. This was your vapor pressure. This was the temperature. Imagine this was the graph for liquid solvent. Okay, liquid solvent. And similarly, this was the graph for your solid solvent. Okay. At this point, if you see, vapor pressure of solid and liquid is becoming equal. This point is what I call as freezing point of solvent. If I talk about solution, vapor pressure of solution will be less than that of solvent, you know it. So let the graph be like this. When you extend this, it will cut here. For example, okay, this particular graph is for liquid solution. And this is the point at which vapor pressure of solid and liquid is becoming equal. So I'm calling this as freezing point of solution. And this gap over here is what you call as depression in freezing point. You can erase this particular part here. Okay, I believe this is clear now, right? So one thing which you have to remember over here, when you add non-volatile solute into a volatile liquid, freezing point decreases, and that decrease in the freezing point is something which you call as depression in freezing point, represented by delta TF. So delta TF, which is basically equal to freezing point of solvent minus freezing point of solution. Freezing point of solvent minus the freezing point of solution. Minus the freezing point of solution. And let me tell you, this delta F is directly proportional to molality of the solution. If you remove the proportionality sign, you get a constant Kf, and here you get molality, right? What is Kf over here? What is Kf? Kf is something which you call as molal depression constant, or you can call it as the cryoscopic constant. You can call it as the cryoscopic constant. Again, it is solvent dependent. Again, it's solvent dependent. Again, its units are going to be degree centigrade per molal, or you can say Kelvin kg per mole, right? Now, the final expression for delta TF. The final expression for delta TF, which all of you will be remembering from now onwards, I'll say delta TF is equal to Kf, or before that, let me write delta TF is equal to freezing point of solvent minus the freezing point of solution. This is equal to Kf multiplied by molality, which is mass of solute multiplied by 1000 divided by molar mass of solute, and this is mass of solvent in grams. This is one result which you have to remember. Now, my dear students, is there any way to calculate Kf? Yes, there is a result to calculate Kf. There is a result to calculate Kf. Like I gave you the result to calculate Kb. In the similar way, you'll have to remember two results to calculate Kf. Kf is equal to RT0 square divided by 1000 LF. This T0 over here is what you call as freezing point of solvent. Okay, rest all the other things are same. LF here is what I call as latent heat of vaporization, latent heat of fusion per gram of solvent. Per gram of solvent. And similarly, delta HF is something which I call as latent heat of fusion per mole of solvent. Per mole of solvent. And two Kf values you have to remember. You have to remember Kf value for water, and you have to remember Kf value for benzene, which I've already mentioned over here. 1.86 degree centigrade per mole. Similarly, 5.12 for benzene. Okay. So my dear students, these are the two values which you have to remember for water and benzene. Sometimes they won't give you the values of Kf for water or benzene in the question. This is something which is to be remembered. This is something which is to be remembered, right? Let's have a look on few questions, some basic questions, because right now I won't be able to solve some good questions till we complete the Vant factor, right? Understand, people. Find the freezing point of the solution obtained by mixing 18 grams of glucose and 90 grams of water. Simple basic question. So, as far as this particular question is concerned, imagine this was the container, and in this particular container you had taken water. How many grams of water you have taken? You have taken 90 grams of water. So the mass of solvent here is 90 grams. Similarly, the freezing point of water, the freezing point of solvent, you know, freezing point of water is nothing but 0 degree centigrade. Now, people, in this particular water, what we are adding a non-volatile solute glucose. right? Okay. How many grams of non-volatile solute glucose we are adding? We are adding some 18 grams of non-volatile solute, right? What would be happening? What would be happening? We know on adding a non-volatile solute into a volatile liquid, what happens? The freezing point. Freezing point decreases, right? So this is the solution which we have. This is the solution which we have. Let's assume freezing point of the solution is represented by TF solution. Perfect. Now, this question is based on depression in freezing point. You could see it directly. So your delta TF has to be equal to KF multiplied by M. Delta TF is equal to freezing point of solvent, that is 0, minus freezing point of solution, which I'm supposed to calculate, is equal to KF 1.86. Molality of the solution is equal to mass of solute multiplied by 1000 divided by molar mass of solute, molar mass of glucose, which is 180, multiplied by mass of solvent, that's 90, right? Take this minus sign on this side and you'll be getting the freezing point of solution over here, right? Whose sign will be minus with certain magnitude, right? So this is going to give you the freezing point of this particular solution which I was supposed to calculate. I believe this particular question is clear. Similar sort of question I'm giving you. You can take this as the homework. It is again the same question. 2.5 grams of ethylene glycol is added to 20 grams of water, right? Find the freezing point of the solution. KF is given. Similar sort of question, similar type of question. Perfect. You just have to give it a try. That's it. Perfect, guys. You just need to give it a try. And you can take this as the homework question again because it is a similar sort. It is a similar sort of question. Now, let's talk about one last colligative property, that's your osmotic pressure. Perfect. Osmotic pressure. Before talking about the osmotic pressure, you should first of all know what osmosis is all about. You should know what osmosis is all about. Okay, what is osmosis? I would say osmosis is defined as the net moment of solvent molecules. The net moment of solvent molecules. The net moment of solvent molecules from solvent side to solution side. To solution side. Or I can say from less concentrated side to more concentrated side. To more concentrated side. Through a semi-permeable membrane. Through a semi-permeable membrane is something which we call as osmosis. Let's try to understand this in detail. See, guys. Understand. Imagine this is one big container which I've taken over here. And my dear students, I'm dividing this container into two parts with the help of a semi-permeable membrane that only allows the movement of solvent molecules. That only allows the movement of solvent molecules. Okay, that only allows the movement of solvent molecules. Now imagine on this side, I'm keeping a solution. Imagine on this particular side, I'm keeping a solution whose molarity is M, or I can say whose concentration is C, whose concentration is M or C, right? Concentration means molarity. On this particular side, what exactly am I keeping? I'm keeping pure solvent. I'm keeping pure solvent. My dear students, what you are going to observe, say, over here, I'm keeping a piston, for example. Let's say this is the piston over here. This piston can go up, it can come down. Remember, whenever you see solvent and solution in direct contact with the help of a semi-permeable membrane, which allows the movement of solvent molecules only, what you will observe? You will observe net moment of solvent molecules. You'll observe net moment. I'm using the term net moment of solvent molecules will be from solvent side to solution side. There will be moment of solvent from solution to solvent as well. But net moment of solvent will be from solvent side to solution side. And this phenomenon of net moment of solvent molecules from solvent side to solution side with the help of SPM is something which we call as osmosis. Tell me one thing. During osmosis, there is net moment, net flow of solvent from solvent side to solution side. What will happen to this piston? Will this piston go down or piston will go up? The piston will start going up, right? My dear students, in order to stop the moment of this piston, don't you think we have to apply some pressure over here? In order to stop the moment of the piston? In order to stop the moment of the piston, otherwise the piston will go up. In order to stop the moment of the piston, in order to stop the net moment of solvent molecules from solvent side to solution side, don't you think some pressure has to be applied from the top? Let me tell you that minimum excess pressure. Let me tell you the minimum excess pressure required. The minimum excess pressure required on the solvent side, on the solution side, to prevent the entry of or I can say to prevent the net flow of solvent from solvent side to the solution side is called as osmotic pressure, which is represented by pi. Okay, so did you understand what osmotic pressure is all about? So you had a solution and a solvent in contact with the help of semipermeable membrane. What you'll observe, net moment of solvent molecules will move from solvent side to solution side, due to which the piston will start going up. In order to stop the movement of piston, in order to prevent the net flow of solvent from solvent side to solution side, we have to apply some pressure over here. That minimum excess pressure which is to be applied on the solution side to stop the movement of piston, to stop the net movement of solvent from solvent side to solution side, is something which we call as osmotic pressure. Is something which we call as osmotic pressure. Okay? Is something which we call as osmotic pressure. Is something which we call as osmotic pressure, which is represented by pi. Let me tell you the mathematical expression of pi. This osmotic pressure is directly proportional to the concentration of the solution. Osmotic pressure is directly proportional to the concentration of solution. More the concentration of the solution, more will be the concentration difference. More the concentration difference between these two compartments. More the concentration difference between these two compartments. More will be the net moment of solvent from solvent side to solution side, right? More excess pressure has to be applied to stop the net moment of solvent molecules. So I would simply say more will be the osmotic pressure. So osmotic pressure is directly proportional to concentration. At the same time, osmotic pressure is directly proportional to temperature as well. So in general, I'll write pi is equal to C. This is R. This is T. Right? Pi is equal to C RT. Or you can write pi is equal to MRT. The choice is all yours. Pi is equal to MRT, where M is the molarity, or you can call it as the concentration of the solution. Now simply you can deal with it. Molarity means number of moles of solute divided by volume of solution in liters. This is R, this is T over here. So this is the result by means of which you can calculate the osmotic pressure. Number one. This is the result to calculate osmotic pressure. Okay. Now people, let me tell you one more thing. If the applied pressure is greater than the osmotic pressure, what will happen? If the applied pressure is greater than the osmotic pressure, for example, understand this particular scenario. Let's say over here, for example, minimum 5 atm pressure is required. Let's say minimum 5 atm pressure is required to stop the net moment of solvent molecules from solvent side to solution side, right? But for example, if the applied pressure is greater than 5 atm, If the applied pressure is, for example, 6 atm, what will happen? How much minimum pressure is to be applied to stop the movement of piston? 5 atm. For example, I'm putting 6 atm here. I'll say the piston will go down. When the piston goes down, there will be net moment of solvent molecules from solution side to solvent side, right? So if the applied pressure is greater than osmotic pressure, I would say there will be net moment of solvent from solution side to solvent side. And this phenomenon is what you call as reverse osmosis. This phenomenon is called as reverse osmosis. And this reverse osmosis is used for the desalination. It is used for the desalination of seawater. And do remember one more thing. When we do the desalination of seawater, at that point of time, the semi-permeable membrane used is cellulose acetate. Remember this, when we do the desalination of seawater with the help of what? With the help of SPM. The SPM which we use at that point of time, that is going to be your cellulose acetate. Right? Perfect. Right, people? Am I clear? Am I clear? Am I clear with this? Yeah? Is it clear, people? Let me know in the chats quickly. Perfect. Now, few more things. Few more things, guys. Remember, two solutions having same osmotic pressure at same temperatures. What do you call them? You call them as isotonic solutions. You call them as isotonic solutions, or you can call them as isoosmotic solutions. Isoosmotic solutions. Now, two solutions which have got same osmotic pressure. So if pi 1 is equal to pi 2, what is pi 1? Pi 1 is CrT1. Pi 2 will be C2RT2. C2RT2. Since temperature is also same, I'm writing the term at same temperature. So T1, T2 is same, RR cancel, TT cancel. So C1 has to be equal to C2. What is C1 basically? Molarity. So molarity of 1 has to be equal to molarity of 2, right? So what can we conclude from here? So whenever you'll be having two solutions which are isotonic, first of all, their osmotic pressure is same. At the same time, what did we see? We saw their concentrations, their molarities are also same. Their molarities are also same. Okay? Their molarities are also same. Perfect? Their molarities are also same. From this particular thing, a question will be asked. Okay? One more thing, guys. One more thing. Let's say we have got a solution whose osmotic pressure is more than that of some other solution. We have got two solutions, solution 1, solution 2. Let's say osmotic pressure of solution 1 is more than that of osmotic pressure of solution 2. At that point of time, we say solution 1 is hypertonic to solution 2. Or we can say solution 2 is hypotonic to solution 1. Hypotonic to solution 1. Okay? Hypotonic to solution 1. These are two more terminologies which you need to remember. Now, similarly, there are two more terminologies. I believe you would have heard them. One is called as endosmosis and one is called as exosmosis. Endosmosis, exosmosis. See, I'll tell you what endosmosis and exosmosis is all about. These are the two containers which I'll take. Let's say you have got, for example, grapes over here. You have got grapes over here. This is one grape particle over here, right? Inside the grape, you'll find a solution. So this is the liquid solution inside the grape. Over here, for example, I've kept water, pure water, which is a solvent. Inside the grapes, what do we have? We have got a solution. My dear students, do you see solution and pure solvent separated with the help of SPM? Whenever you see solution and solvent separated by SPM, there will be net movement of solvent molecules from solvent side to solution side. From solvent side to solution side. So there will be entry of solvent inside. Entry of solvent inside. Entry of solvent inside. Entry of solvent inside, due to which this grape will swell. And whenever you see entry of solvent inside, what do you call this as? Entry of solvent inside means endosmosis. Entry of solvent inside means endosmosis, due to which this grape swells. Okay. Now, what happens in exosmosis? Exosmosis, for example, this is the grape. And this is the solution which is present inside the grape. This is the solution. Now, over here, I'm not keeping a solvent now. I'm keeping one more concentrated solution here. This is a concentrated solution, right? This solution is more concentrated than the one which is inside. So inside you have got less concentrated solution. Outside you have got more concentrated solution. Do you see? Less concentrated, more concentrated solution in direct contact with the help of SPM. So there will be net movement of solvent molecules from less concentrated side to more concentrated side. Less concentrated side to more concentrated side. Net movement of solvent molecules from less concentrated side to more concentrated side. So whenever net movement of solvent is outside the membrane, right? Okay. Net movement of solvent is outside the membrane. Net movement of solvent is outside the membrane, right? We call this as exosmosis, due to which this grape particle shrinks. Due to which this grape particle shrinks. Okay, perfect. Now let's try to solve few questions. Let's try to solve few questions. Look at the first question. The first question is find the osmotic pressure at 273 Kelvin of a 5% solution. Remember, whenever it's not mentioned, whether it's weight by weight or weight by volume, we'll be considering it here as weight by volume. So it is 5% weight by volume of urea. What is meant by 5% weight by volume of urea? It means that 5 grams of urea are present in 100 ml of solution. 100 ml of solution. What do we have to calculate? Osmotic pressure pi. Pi is equal to MRT. MRT. What is M? Number of moles of solute divided by volume of solution in liters. R and T. What is N2? Number of moles of solute. It means mass of solute, which is 5 grams, divided by molar mass of solute, molar mass of urea, that's 60. Volume of solution in liters. It is in ml. 100 ml means 0.1 liters. Which value of R do I need to take? Since I have to calculate osmotic pressure in ATM, so I'll use the value of R as 0.0821 ATM liter per Kelvin per mole. Temperature is how much? 273 Kelvin. Matter of calculation. Solve it. Get the value in ATM. Right? Get the value in ATM. Done and dusted. Perfect. One simple and basic question this was. All right. Let's have a look on one more question. The question is, a 4% solution of sucrose is isotonic with 3% solution of unknown substance. So we have got a sucrose solution, and at the same time, we have got a solution of some organic substance. We have got 4% weight by volume of sucrose. Here we have got 3% weight by volume of this organic substance. What does it mean? First of all, it means that 4 grams of sucrose are present in 100 ml solution. Similarly here, 3 grams of organic substance is present in 100 ml of solution. Now, as per the question, these two solutions are isotonic, so their osmotic pressures are equal. So I would say pi 1 is equal to pi 2. Pi 1 is equal to pi 2. Since they're isotonic, that means the temperature is same. So if pi 1 is equal to pi 2, that means M1 has to be equal to M2. What is the molarity of the first solution? Molarity of the first solution means mass of solute, mass of sucrose, divided by volume of solution in liters is equal to molarity of second solution means number of moles of organic substance divided by volume of solution in liters. I think the volume of solution is same at both the places, so this term cancels. So I would say number of moles of sucrose is equal to number of moles of organic substance. Number of moles of sucrose means mass of sucrose divided by molar mass of sucrose is equal to number of moles of organic substance means mass of organic substance divided by molar mass of organic substance. I think the question is done. Mass of sucrose is how much? 4 grams divided by molar mass of sucrose is 342 is equal to mass of organic substance is 3 grams. So from here you can calculate molar mass of organic substance, right? From here you can calculate molar mass of organic substance, which I was supposed to calculate. Am I clear till here? Am I clear till here, people? Yeah. And one more thing, these 2 pointers I would want you guys to remember, they can be memory based questions. Whenever you would want to calculate molecular mass of a protein, for example, molecular mass of biomolecule, right? The best way to calculate the molecular mass of biomolecules, right? The best way to calculate the molecular mass of biomolecules like proteins and polymers is through osmotic pressure. Through osmotic pressure. Because in this particular colligative property, there is no temperature change involved, due to which the nature of biomolecule does not change. In all the other colligative properties, other than osmotic pressure, what happens? Due to the temperature change, the nature of the biomolecule changes, right? So the best way of calculating molecular mass of a protein, that means molecular mass of a biomolecule like protein, like you have got polymer, right, is through osmotic pressure method. Remember this as the important point. And this particular point is also important. 0.91% weight by volume NaCl. It is isotonic with blood, right? Do remember these values. 0.91% weight by volume NaCl is isotonic with blood. This can be again one memory based question asked in the exam. Okay? Do remember these 2 points. What is the reason for the first point? Because through osmotic pressure, there is no temperature change. Due to no temperature change, the nature of biomolecule does not change. Okay? Remember this. It can be asked. These 2 can be asked. All right, so we are done with the colligative properties. Now, the last topic of the chapter, which is very important. I would want you guys to be active here, because otherwise you are not going to remember this particular topic. Are you here? Everyone, I want you guys to open your eyes properly now. Okay, because this is something which is super important. Introduction to Vant factor. This is something which is super important. I want you guys to stay active now. For an hour. For an hour. Okay? For an hour. I would want some fire emojis in the chats so that I'll see whether you guys are here or not. Quick. This is something which is super, super important, guys. Are the eyes open? Are the eyes open? Perfect. So, introduction to Vant factor. First of all, if I ask you how many colligative properties have we studied? The first one was relative lowering in vapor pressure. The first one was relative lowering in vapor pressure. As per relative lowering in vapor pressure, P0 minus PS divided by P0 is equal to mole fraction of solute. This is the first colligative property that we discussed. Second one was elevation in boiling point. As per elevation and boiling point, delta TB has to be equal to KB multiplied by M. The third colligative property, depression in freezing point. Delta TF is equal to KF multiplied by M. Similarly, osmotic pressure, pi. Osmotic pressure, pi. Osmotic pressure, pi is equal to CRT. These are the four colligative properties which we have discussed till now. Okay? Four colligative properties which we have discussed till now. My dear students, in every colligative property, be it relative lowering, be it elevation, be it depression, be it osmotic pressure, one thing you'll observe in all the colligative properties. What is that? You will see all the colligative properties will be inversely proportional to molar mass of solute. You'll observe all the colligative properties will be inversely proportional to molar mass of solute. Take any of the colligative property. Take any colligative property. For example, take, let's say, osmotic pressure. Pi is equal to CRT. What is C? Concentration, molarity. M, number of moles of solute divided by volume. Number of moles of solute will be mass of solute divided by molar mass of solute. Right? So osmotic pressure is inversely proportional to molar mass of solute. Similarly, depression freezing point will be inversely proportional to molar mass of solute. If you take any colligative property, what you'll observe one thing. All the colligative properties, they'll be inversely proportional to molar mass of solute. Point number one. Right? Point number two, guys. See, let me tell you, in order to calculate the colligative property, any colligative property out of these, in order to calculate a colligative property of a solution, we have got two ways. First, either I'll calculate colligative property of the solution experimentally, or I'll calculate it theoretically. I can calculate colligative property of a solution, any colligative property of a solution, either experimentally or theoretically. When I'll be calculating colligative property experimentally, I'll be calling that as, either I'll be calling it as observed value of colligative property, or I'll be calling it as experimentally determined colligative property, or I'll be calling this as actual value of colligative property. When I'll be calculating colligative property, right, be it relative lowering, elevation, depression, osmotic pressure, right? If I want to calculate a colligative property experimentally, whatever value I'll be getting from the experiments, I'll be calling that either as observed colligative property, or experimental colligative property, or you'll be calling this as actual colligative property. There is one more way of calculating the colligative property. That is with the help of these formulas. I can use these formulas and get the value of any colligative property. So when I'll be using these formulas to calculate the colligative property value, that colligative property which I calculate with the help of these formulas, I'll be calling them either calculated value of colligative property, or theoretical value of colligative property, or expected colligative property, Okay. So like we discussed about vapor pressure of solution, there were two ways to calculate vapor pressure of solution, experimental and theoretical. Similarly, there are two ways to calculate the value of colligative property. First, experimentally. Second, theoretically with the help of these results. I can use this result, calculate delta TF. I'll be calling it as depression in freezing point. Which one but? Theoretical depression in freezing point. I hope you are getting what I'm trying to say. So, one thing I would want you guys to remember over here. Whenever these formulas are used to calculate the value of any colligative property, we call that colligative property which we get from these formulas as calculated colligative property, theoretical, expected. But when we calculate the value of colligative property of a solution experimentally in the lab, you'll be calling that as observed, experimental, actual, right? Now, my dear students, there are some solutions for which experimentally determined colligative property and calculated colligative property, experimental colligative property and theoretically determined colligative property as per the formulas comes out to be equal. But there are some solutions for which the observed and experimental colligative properties, they do not come out to be equal, right? They do not come out to be equal. Now, what is the logic behind that? Why for some solutions this is true? Why for some solutions this is not true? Why? What is the reason? For some solutions, experimentally determined colligative property and theoretically determined colligative property as per these formulas come out to be same. But for some solutions, they do not come out to be same. They do not come out to be same. First of all, why they don't come out to be same? That's a different debate. But before that, I'll tell you one thing. Whenever for any particular solution, the experimentally determined colligative property and the calculated colligative property with the help of these formulas, they come out to be different. At that point of time, we say the solute which is there in the solution, we say it shows abnormal behavior. Solute shows abnormal behavior. Due to the abnormal behavior of solute, these two come out to be different in case of some solutions. Now, why solute shows abnormal behavior? What is meant by that? Let's try to understand. Let's try to understand. Let's try to understand. See, guys. For example, here I'm taking two containers. Here I'm taking two containers. Let's say here you have got 100 ml water in this container. Similarly, here you have again got, for example, 100 ml water in this container. Perfect. For example, imagine that here you are introducing one particle of urea, non-volatile solute. Here you are introducing one particle of NaCl. Again, the non-volatile solute, right? For example, since I'm adding non-volatile solute into a volatile liquid, let's calculate the value of some colligative property. For example, I want to calculate elevation in boiling point here. Well, in order to calculate elevation in boiling point here for this solution, I've got two ways. Either I'll calculate elevation in boiling point experimentally, or I'll calculate elevation in boiling point theoretically with the help of formula Kb into m, which I'm calling as Cp calculated. And what you will observe in this particular solution, you'll observe these two values will come out to be same. But in this particular one, for example, here I want to calculate elevation in boiling point. First, I'll calculate elevation in boiling point experimentally. Then I'll calculate elevation in boiling point theoretically with the help of formula. And here, these two will come out to be different. First of all, why here they come out to be same? Why here they come out to be different? See, guys. Urea, when it goes into water, it neither dissociates nor associates. But when NaCl goes into water, it gets converted into Na positive plus Cl negative. When NaCl goes into water, it gets converted into Na positive plus Cl negative. You know, colligative property depends upon the number of particles of solute. Since this one particle of solute which you are introducing, it neither dissociates nor associates, right? But here, this one particle of solute gets converted into two particles, one Na positive plus one Cl negative, right? So, over here in this particular case, we had expected that the value of colligative property will come due to one particle of solute. That's something which we had expected. But in reality, this NaCl got converted into two particles, Na positive plus Cl negative. So the actual value of colligative property will come due to two particles. Right? This colligative property will come due to one particle. Because this is the value of colligative property which we get with the help of formulas. Okay? So basically, we are introducing one particle of NaCl. So we were expecting that the colligative property value will come out to be due to one particle. Right? But in reality, this NaCl got dissociated into two particles. So actual value of colligative property came out to be due to two particles. And you know, colligative property depends on number of particles of solute. Right? That's the reason why these two things, they come out to be different. But here, urea neither dissociates nor associates. So you were expecting that you are introducing one particle of solute. Right? You were expecting that colligative property value will come due to one particle. And in reality also, it came out to be due to one particle only. That's the reason why they came out to be same here, right? Did you understand why these two come out to be different here? Because in reality, this NaCl got dissociated into two particles. Okay? Perfect. Now, my dear students, since these two are coming out to be different, experimental colligative property, which is the actual value of colligative property, it comes out to be different than what you have calculated as per the formulas. Now, if you want LHS and RHS here to be equal, if you want, since they are not equal, if you want LHS and RHS to be equal, so what you'll be doing? What you'll be doing? You'll be introducing a term over here which you represent with I, which is basically a correction factor used, in order to equalize LHS and RHS. In order to equalize LHS and RHS. Okay? So, this I is the correction factor which is used to equalize LHS and RHS in case of that solution where the solute either dissociates or associates. Okay? So, I can say I is nothing but the actual value, experimental colligative property divided by calculated colligative property. Perfect. Now, people, already I told you, colligative property is inversely proportional to molar mass of solute. If colligative property is inversely proportional to molar mass of solute, so instead of Cp observed by Cp calculated, I can write observed molar mass of solute, calculated molar mass of solute divided by observed molar mass of solute, Mc divided by Mo. Is this particular point clear? Is this particular point clear? So how do you define I over here? How do you define I over here? I is simply defined as actual value of colligative property divided by the calculated value of colligative property, which can be also calculated as MC, molar mass of solute calculated divided by molar mass of solute observed. Okay? Perfect. Is it clear, people, till here? Is it clear till here? Let me know once quickly. Now tell me one thing. Whatever colligative property, whatever formulas we have here, what do you think? Do these formulas always give us right results? These formulas, they are not always going to give us right results because they do not take into consideration whether the solute dissociates or associates, right? Perfect. They do not take into consideration whether the solute dissociates or associates. Now, since these formulas, they are not always going to give us the correct results. So we are going to modify these formulas so that we always get correct results from them. Okay? In order to modify these formulas, I'll be multiplying all the results by I. Now they are going to give us the correct result always. Because I have introduced the correction factor over here, which will take care of the thing that whether the solute undergoes dissociation or association, which earlier was not the case. Now, my dear students, the first point. If you have got a solute that dissociates, at that point of time, whenever you'll be having such kind of a solute that dissociates, for example, you introduce one particle, it dissociated into three particles in the solution. One particle dissociated into three particles. So you were expecting the value of colligative property will come due to one particle, but in reality it came due to three particles. And colligative property depends on number of particles of solute. More the particles of solute, more the colligative property. So can I say at this particular point of time, the actual value of colligative property, right, which comes out to be due to three particles, will be greater than that of calculated value of colligative property, which is calculated with the help of formula. So now, if Cp observed is greater than Cp calculated, what will be the value of I? Cp observed is greater than Cp calculated. So the ratio will be greater than 1, right? It will come out to be greater than 1. So remember that particular solute that dissociates, I value for that particular solute is taken to be 1. Okay. Second point. If you have the solute that associates, if solute associates in the solvent, for example, you introduce two particles of solute. In reality, those two particles became one in the solution. So you were expecting the value of colligative property will come due to two particles, but in reality, it's coming due to one. right? And colligative property depends on number of particles of solute. So I would say at that point of time, that solute which associates, I would say at that point of time, the experimental colligative property which comes out be due to one particle, right? The experimental colligative property will come out to be less than that of what you had expected. What you had expected. Is this clear? So in this particular case, I value, will it be greater than 1 or less than 1? It will be less than 1. I value will be less than 1. Now, if you have such kind of the solute that neither dissociates nor associates, that neither dissociates nor associates, at that point of time, your experimentally determined colligative property will be equal to what you have calculated with the help of formulas. So I value for them is nothing but 1. Perfect. I value for them is nothing but 1. Right, people? Perfect. Now the point is, how do we get the value of I for the solute that dissociates or associates? Okay, tell me one thing first of all. I told you for those solutions wherein experimentally determined colligative property comes out to be different as what we had calculated, right? We say at that point of time, the solute shows abnormal behavior. Or you can say one more thing. Since Cp observed won't be equal to Cp calculated, you can say MO won't be equal to MC. In that case, molar mass, experimentally determined molar mass of solute won't be equal to calculated molar mass of solute. At that point of time, we say the solute shows abnormal molar mass. Or you can say abnormal molecular mass. When do we say that the solute shows abnormal molecular mass? When solute undergoes dissociation or association. Okay? Perfect. I hope this particular point is also clear. Now the point is, how do we calculate I for the solute that undergoes dissociation? That solute which undergoes dissociation, for that we know I value is greater than 1. Correct? We know for that I value is greater than 1. Now how do we calculate it? I'm not going to derive the result, I'll just give you the result. For example, you have got the solute AN. In the solvent, let's say it gave N times A. It got converted into N times A. Stoichiometric option here is 1. Here it is N. Imagine N value is greater than 1. What does that mean? For example, N is 2. It is greater than 1. For example, N is 2. So one particle in the solvent is giving 2 particles. Or N is 3. One particle is giving 3 particles. One particle giving 4. One particle giving 5. One particle giving 6. So this is the case of dissociation. Solute is dissociating into the solvent. How do we calculate I for it? Let's say the degree of dissociation is alpha for the solute. So I is calculated 1 plus N minus 1 into alpha. This is how you calculate I for the solute which undergoes dissociation. And for the solute which undergoes dissociation, I is directly proportional to N basically. For the solute which undergoes dissociation, I is directly proportional to N. Okay? More the dissociation, right? More the dissociation, what does that mean? More is going to be the Vant effect of that particular solute. Right? I hope this is clear. I hope this is clear. So this is the value of I. This is how you calculate the Vant factor for the solute that undergoes dissociation. Perfect, people. I hope you got to know. I is the alpha is the degree of dissociation here for the solute. Let me know one more thing. What is this N here? What is this N? For example, you have got a solute like this. Let's say I'm writing NaCl gives Na positive plus Cl negative. If I ask you what is the value of N for this, see, one particle is giving 1 plus 1, 2 particles. So N value is 2 for NaCl. Let's say you have got BaCl2. How it undergoes dissociation? Pa di positive plus 2 times Cl negative. Right? So one particle is giving 1 plus 2, 3 particles. So N value is 3. Let's say you have got something like this. 2 times A gives 3. Or let me write it. 2 times A gives 4 times B. Now see, 2 particles are giving 4 particles. Therefore, 1 particle will give 4 by 2. 4 by 2 means 2. 1 particle is giving 2 particles. So N value here is 2. So this is how you calculate N value. So this was the case of dissociation. Now, there can be one more case wherein solute undergoes association. Wherein solute undergoes association. And you know, when the solute undergoes association, what happens? When the solute undergoes association, I value, we have already discussed, it's 1, it's less than 1, right? It is 1 less than 1. Now, my dear students, for example, you have got a solute like this. N times A, this solute in the solvent got converted into AN. Perfect. Stoichiometric coefficient here is N, here it's 1. Let's assume N value is greater than 1. For example, N is 2, N is 3, N is 4. That means 2 particles are giving 1 particle, 3 particles are giving 1 particle, 4 particles in the solvent are giving 1 particle, 5 particles in the solvent are giving 1 particle. So this is the case of association. In case of association, how do we get I? I is equal to 1 plus 1 divided by N minus 1 into alpha. This is how you calculate I. And in case of association, do remember, I is inversely proportional to N. As you can see. In case of association, I is inversely proportional to N. Right? So the point is now, how do we get the N value? See, let's say you have got a solute like this, which in the solvent behaves like this. 2A gives A2. So 2 particles are combining, forming 1 particle. So N value is 2. If 3 particles are combining and forming 1 particle, N value is 3 here. If 4 particles of A are combining in the solvent and making 1 particle, N value is 4. So in case of association, N represents number of particles associating to form 1 particle. Here N represents number of particles dissociated from 1 particle of solute. Right? That is the difference. That is the difference between N here and N here. What is N here? Number of particles which are generated from 1 particle of solute. Here N represents number of particles associated to form 1 particle in the solvent. Okay? I hope this is clear. I hope this is clear. Now, let's go into the questions and see what kind of questions can be asked. See guys, this is the first question. Can you give it a try? Can you let me know in the chats? Quickly. Quickly, people. Yeah? Let's have a look. The values of observed and calculated molecular weights of AgNO3 are observed and calculated, right? So observed molecular weight of AgNO3 is 92.64 grams. Calculated molecular weight of same AgNO3 is 170 grams. What do we have to calculate? We have to calculate alpha or AgNO3. Okay. So first of all, how AgNO3 would have undergone dissociation? Tell me that. It would have gone dissociation as Ag positive plus NO3 negative in the solvent, right? What is the value of N? 1 is giving 2 particles, so N value is 2. Perfect. So first of all, how can I calculate I? I is nothing but MC divided by M naught, right? What is MC? MC is 170, M naught is 92.64. When you solve this, the value comes out to be 1.8. So I is 1.8. If you got the I value, since it's a case of dissociation, you know I is nothing but 1 plus N minus 1 into alpha. So I is 1.8 is equal to 1 plus N value is 2 minus 1 into alpha. So when you calculate alpha here, it comes out to be 0.8. This is something I was supposed to calculate. Alpha is 0.8. So if alpha is 0.8, if they ask you how much AgNO3 has dissociated, how much percentage of AgNO3 has dissociated, percentage dissociation is always equal to alpha multiplied by 100. So 0.8 multiplied by 100 is giving me basically 80%. Right? It's giving me 80%. This is the first type of question that can be asked. Number 1. Number 2. Number 2. The degree of dissociation of a weak electrolyte AXBY can be expressed in terms of I as. Okay. So you have got a weak electrolyte as AXBY. Now the point is how it will undergo dissociation. It will undergo dissociation as X times AY positive plus Y times B X negative. Right? So what is the value of N here first of all? See, one particle is giving X plus Y. One particle is giving X plus Y particles. So N value is nothing but X plus Y. This is the case of dissociation, right? This is the case of dissociation. In case of dissociation, I is equal to 1 plus N minus 1 into alpha. What do we have to calculate? We have to calculate degree of dissociation in terms of I. Okay. So I will be equal to 1 plus, what is N? N is X plus Y minus 1 into alpha. So I would say alpha is equal to I minus 1 divided by X plus Y minus 1. Right? Alpha is equal to I minus 1 divided by X plus Y minus 1. This is the value of alpha which I was supposed to calculate. Done and dusted. Look at the next question. Vant factor for Hg2Cl2 in aqueous solution, which is 80% ionized. 80% ionized means alpha is equal to 0.8. Now remember how this Hg2Cl2 undergoes dissociation. In aqueous solution, let me tell you, HgCl2 gets converted into Hg2 dye positive, right? Plus 2 times Cl negative. It's a special case. Do you remember this is how it undergoes dissociation? Perfect. What is the value of N first of all? N value is 1 particle is giving 1 plus 2. So 3 particles, so N value is 3. Now alpha we know, we have to calculate I. I is equal to 1 plus N minus 1 into alpha. So I is going to be 1 plus N value is 3 minus 1, alpha value is 0.8. So 3 minus 1 is 2. 2 8s are 16, 1.6. 1.6 plus 1 is basically 2.6. So I is 2.6 here. Right? I is 2.6 here. Have a look on this particular question. Have a look on this particular question. Calculate I when 0.1 molar solution of NH4Cl is dissolved in 1 liter water. Alpha for NH4Cl is given. Its degree of hydrolysis is also given. See guys, all these things are of no use to us. This is just to confuse you. This is just to confuse you. So basically, we have got NH4Cl. And one thing you know about NH4Cl, how it undergoes dissociation. NH4 positive plus Cl negative. So N value here is 2. So in case of dissociation, I is nothing but 1 plus N minus 1 into alpha. Right? So I will be equal to 1 plus N value is 2 minus 1. What is alpha? It is how much percentage dissociated? Calculate I alpha for NH4Cl is 0.8. Okay, it is 0.8. So I value will be simply coming out to be 1.8. Simple. Nothing to think here. Right? Perfect. Similarly, let's try to solve this question. We have got 3-4 questions only and we are done. See guys, a millimolar solution of K3FeCN6. Millimolar means you have got a solution whose molarity is 10 raised power minus 3. Of what? We are taking K3FeCN6. Tell me how it undergoes dissociation first of all. It undergoes dissociation as 3 times K positive plus FeCN6 tri-negative. This is how it undergoes dissociation. Now, 1 particle is giving 3 plus 1, 4 particles, so N value is 4. N value is 4 first of all, right? What do we have to calculate? Vant factor? Sorry, osmotic pressure. How do we calculate osmotic pressure? The actual formula now is going to be ICRT. So first of all, I have to calculate I. How do you calculate I? Since the case of dissociation, I is equal to 1 plus N minus 1 into alpha. So I will be equal to 1 plus N values 4 minus 1. Alpha. What is the alpha value? 70%. So 0.7. So I will be equal to 3, 7, 21. It comes out to be 3.1. I is 3.1. So calculate pi here. I is 3.1. Concentration is 10 raised power minus 3 molar. We have to calculate pi in ATM. If we have to calculate pi in ATM, use the value 0.0821. And temperature is given to me as how much? 27 degrees centigrade means 300 Kelvin. Just it's a matter of calculation. Solve it. Get the answer in ATM. This is the value of osmotic pressure pi. Right? Perfect. Done. Perfect, guys. All right. Look at this particular question. 0.001 molar solution of this in water has a freezing point of this much. If Kf is this, correct formula of the compound is. Correct formula of the compound is. What you will be doing? as a freezing point. It's based on freezing point depression. So you know your delta TF is basically equal to I multiplied by KF multiplied by M, right? My dear students, every single thing is given. Delta TF is given to us. Just you do some calculation, guys, here. Do some calculation for me because I don't want to do any calculation now. KF is given to us as 0.8. Molality of the solution is how much? 0.001, right? So this will be 0.0054 divided by 0.0008 is equal to I. Can you let me know the value of I which you get from here? Is it 0.0054 or it should be 0.0024? How much it comes? I think this should be 0.0024. Then only I value will come out to be 3, right? Just a second. Yes, this is 0.0024 here, okay? Just modify the calculation. When you modify the calculation, I value will come out to be 3. If I is coming out to be 3, what has to be the formula? What has to be the formula now? What has to be the formula here? First one or second one? If first one is the formula, then you'll be getting only 2 ions. If second one is the formula, then you'll be getting 2 plus 1, 3 ions, right? I values 3 means 3 ions are generated in the solution. 3 ions, in order to generate 3 ions in the solution, this has to be the formula. In order to generate 3 ions in the solution, this has to be the formula. So that it dissociates as, it gives you 2 Cl negatives and 1 cation of this, right? It is not solubility and Henry's law. Henry's law is solubility only. Okay, so one topic is left, that is Henry's law. Okay. Can you give this question a try? Can you give this question a try? Can you give this question a try, quick? And Henry's law, I think you will study on your own. Or tomorrow or day after tomorrow, I'll post one small recording on Henry's law. That will be for half an hour. Okay, don't worry. This is the last topic which we are doing for tonight. Okay, acetic acid dimerizes. So acetic acid is dimerizing. So that means 2 particles of acetic acid in the benzene are making 1 particle, right? So 2 acetic acid particles are dimerizing in benzene and forming 1 particle. So N value here is 2. 2 particles are assembling to form 1. N is 2 here. Perfect. The boiling point raised. So this question is based on elevation and boiling point. Elevation and boiling point means delta TB is equal to I multiplied by KB multiplied by M. How much boiling point has elevated? 0.36 degree. This is the elevation and boiling point. I value we need to calculate. KB is given. How much? How much KB is given? KB for benzene used to be how much? Can you let me know in the chats? I already gave you the value. Is it 0.5 to 1.86? What was that? For benzene. What was the value of KB for benzene? Or 2.52? What was it? Can you let me know? Can you let me know in the chats? What was the KB for benzene? Was it 2.52? Okay. 2.52. Molality of the solution will be mass of solute multiplied by 1000 divided by molar mass of solute, molar mass of acetic acid. Molar mass of acetic acid will be, I think, 62. Mass of solvent is 100 here. So you can calculate I. So how much is the value of I which you get from here? Can you give it a try? I think it will come out to be, how much I comes out to be from here? I think 0.9 something it will come. Solve it quickly. What is the value of I? What is the value of I from here? I'm asking you, quick. Zero point 0.5, huh? So people are saying I value is coming out to be 0.5. If I is 0.5, what do we have to calculate? I and alpha. Since it's the case of association, so I is equal to, in case of association, 1 plus 1 by n minus 1 into alpha. So I is 0.5 is equal to 1 plus 1 divided by 2 minus 1 into alpha. So I would say alpha value over here comes out to be 0.5 only. Right? It comes out to be 0.5 only. Can you give this question a try? Can you give this question a try? You have got Ki and sucrose solution with 0.1 concentration each. So their concentration is same. Osmotic pressure of both of them is given. Calculate I and alpha for Ki. So first solution is your Ki solution. Then you have got sucrose solution. Okay. Sucrose neither dissociates nor associates. Ki would have dissociated as K positive plus I negative. Right? N value here is 2. Perfect. N value here is 2. Now, first of all, K and sucrose solution with 0.1 molar concentration. So their concentration is same. And let me tell you, their temperature is also same. It's not mentioned though, but their temperature will be same. Calculate I and alpha. Modify the equation, temperature is same. Huh? All right. So osmotic pressure for Ki. I for Ki will be equal to I for Ki multiplied by C R T. Similarly, pi for sucrose is equal to I for sucrose multiplied by C R T multiplied by C R T. Perfect. So if I divide these two equations, it becomes pi for Ki divided by pi for sucrose is equal to CRT gets cancelled. It is I for Ki divided by I for sucrose is 1. I for sucrose is 1 because sucrose neither dissociates nor associates. Right? So pi for Ki is given to me as per the equation. How much? 0.46. So it is 0.46 divided by 0.245. Can you let me know this value after solving? I for Ki here. Solve this, let me know quickly. What is the value of I? It's coming out to be 2.53. Huh? I is coming out to be 2.53 for Ki. Okay. I is coming out to be 2.53 for Ki. Since you got I. Now, you know, for dissociation in case of Ki, I is equal to 1 plus n minus 1 into alpha. So I is equal to 2.53 since you said it, right? Is equal to 1 plus n value is 2 minus 1 into alpha. So alpha here will be 1.53 there. But no, how come alpha will be 1.53, guys? That means you have done some mistake here. What is the mistake? Quick. Alpha cannot be greater than 1. So what is the value of I here? Just solve it once. 1.8. I is 1.8. So if it is 1.8, so alpha will be equal to how much? 0.8. Okay, alpha is equal to 0.8. 0.8 or 0.9, depending on whether this is getting as 1.8 or 1.9. Perfect. Now, guys, there is one more topic, that is calculation of colligative properties when concentrations are same. When concentrations are same. Okay. See, guys, so one thing I'm going to tell you. Point by point, we'll discuss this. You know, whenever the solute undergoes dissociation. So The first case which I'm discussing is for the solute that undergoes dissociation. You know your relative lowering in vapor pressure, which is basically P naught minus PS divided by P naught. It is directly proportional to I. It is I into chi B, right? It's I into chi B. Similarly, your elevation and boiling point, that is your delta TB, which is nothing but boiling point of solution minus boiling point of solvent. It is also directly proportional to I. Similarly, depression in freezing point, delta TF, which is equal to freezing point of solvent minus freezing point of solution. It is also directly proportional to I, because delta TB is equal to I kBRT, right? All the formulas. Osmotic pressure pi. Osmotic pressure pi is equal to pi is also equal to I CRT, right? So pi is directly proportional to I as well. Okay. Now people, in case of dissociation, already I have told you, when solute undergoes dissociation, I value is directly proportional to N. When the solute undergoes dissociation, I value is directly proportional to N. Perfect. So see all the conclusions. Since I is directly proportional to N, so more the ions generated into the solution from the solute, so more the value of N, tells you that more is going to be the value of I. If more is the value of I, more is going to be the value of colligative property, which is RLVP, right? More is going to be the value of RLVP, relative lowering in vapor pressure. If more is the relative lowering in vapor pressure, that means if more is this value, that means more is the difference between these two. When can be difference between these two more? If PS is less, that means lesser is the vapor pressure of the solution. So anything can be asked from this particular statement. Number one. Number two. Delta TB is directly proportional to I. I is directly proportional to N, right? So more the value of N, when the solute undergoes dissociation, more will be the value of I. If more is the value of I, more is the value of delta TB. More is the value of delta TB. If more is the value of delta TB, more is the difference between these two. When can be difference between these two more? If boiling point of the solution is more. So more is going to be the boiling point of solution. Right? Any question you can solve from this. Now similarly, talk about freezing point. More the value of N, more the value of I. More the value of I, more is going to be the depression in freezing point. More the depression in freezing point, this is delta TF. More the depression in freezing point, more delta TF means more is the difference between these two. When can be difference between these two more? And freezing point is less. So freezing point of solution here is less. One more question. Okay. Similarly, osmotic pressure. So more the value of N in case of solute which undergoes dissociation, more is the value of I, hence more is the osmotic pressure. Hence more is the osmotic pressure. So you must be thinking, where do we use all this stuff, right? Where do we use all this stuff? Where do we use all this stuff? See guys, let me give you one question by means of which you'll understand where do we use all this stuff. See, for example, I've got a question like this. 0.1 molar urea solution, 0.1 molar NaCl aqueous solution, 0.1 molar BaCl2 aqueous solution, 0.1 molar, for example, Al2SO4 whole thrice solution. These are four options. Option A, option B, option C, option D. First of all, urea neither dissociates nor associates, so its N value is 1. NaCl dissociates into two particles, N value is 2, N value is 3, N value is 3 plus 2, 5 here. So you already got the N values. Now based on N values, you can calculate anything. Based on n values, you can calculate anything. Now, how? The first question which I'm asking you, give me the order of relative lowering in vapor pressure. Give me the order of relative lowering in vapor pressure. See, more the value of n, as I told you already. Look at this particular statement. More the value of n, more the value of I, more the RLVP. So n and RLVP directly proportional. Right? N and RLVP directly proportional. So D will have maximum relative lowering in vapor pressure, followed by C, followed by B, followed by A. Give the order of vapor pressure of the solution. Vapor pressure of solution. See guys, vapor pressure of solution. More the I, lesser the vapor pressure of the solution. More the I, lesser the vapor pressure of the solution. More the I, lesser the vapor pressure of the solution. So this is the order. Give me the order of elevation and boiling point. Elevation and boiling point is directly proportional to I is directly proportional to N. So D, C, B, A. Give me the order of boiling point of solution order. Boiling point of solution. Boiling point of solution. So I told you a few minutes back, more the value of I, more the value of I, more the boiling point of solution. So directly proportional, right? So it's again going to be D, C, B, A. Next question. For example, give me the order of delta TF, depression and freezing point, is directly proportional to I is directly proportional to N. So again, D, C, B, A, right? For example, if they ask you about freezing point of solution, it will be D, C, B, A, because freezing point of solution is inversely proportional to I. We saw it 5 minutes back. Next question. Osmotic pressure. Order of osmotic pressure. Pi is directly proportional to what? I. So D, C, B, right? So this is how you solve all these different types of questions which can be asked. Okay? Perfect. So this is not just one question. This is 1, 2, 3, 4, 5, 6, 7. These are 7 questions which can be asked over here. And this is the concept which is used when concentration is same. When concentration is same. Concentration here means molarity, molality, mole fraction. Okay? You'll take concentration. If concentration is same, concentration can be your molarity here, right? It can be your mole fraction, whatever. Anything. If molarities are given, mole fractions are given, molarities are given, same concept you'll be using. Provided only the concentration is same. Provided when the concentration is same. That's great, Ujjwal. Glad to hear that. Amazing. Amazing. God bless you. Okay, one more concept, guys. So this particular question was when the concentrations will be same, right? When concentrations will be same. Now, if the concentrations are different, at that point of time, you will see the value of I multiplied by C. You'll get the value of I multiplied by concentration. You'll get the value of I multiplied by C. Okay? Rest everything is same. Over here, you'll be getting the value of I multiplied by C when the concentrations are different. For example, I'm giving you a question. 0.1 molar urea. For example, 0.2 molar NaCl. 0.3 molar BaCl2. 0.4 molar, let's say, your Na3PO4. First of all, I for urea, take it as 1. I for NaCl, take it as 2. I for BaCl2, take it as 3. I for this, take it as 4, right? So N and I am taking same here. I'm assuming 100% dissociation. And whenever solute undergoes 100% dissociation, its I and N will be always same. Now guys, over here concentration is different. So I multiplied by C, 1 multiplied by 0.1 is 0.1. I multiplied by C, 0.4. I multiplied by C, 0.9. I multiplied by C, 1.6. This is the value of I multiplied by C. Now here you have to see I multiplied by C value. Accordingly, you will be answering the question, right? See guys, the first question which I'm asking you, give me the order of relative lowering in vapor pressure. Earlier I told you relative lowering in vapor pressure is directly proportional to I. Here I'm telling you relative lowering in vapor pressure. It's directly proportional to IC. So where is IC maximum? It is D followed by C followed by B followed by A. Give me the order of the vapor pressure of the solution. Vapor pressure of the solution. You know, earlier I used to be inversely proportional to vapor pressure of solution. Here IC will be inversely proportional. It will be D, C, B, A. Okay, next. Delta TB is directly proportional to IC. Okay. Delta TF, elevation, depression in freezing point. Again, directly proportional to I. So directly proportional to IC. Boiling point of solution. Boiling point of solution. Right? It will be again DCBA. Because boiling point of solution used to be directly proportional to I. That means it's directly proportional to IC. Freezing point of solution used to be inversely proportional to IC. Okay. Osmotic pressure was directly proportional to IC. So this is the order of all these questions. All right, people. All right. All clear? So, Ujjwal, which college you are getting? Which college you are getting? Sir, in previous, how did you compare between delta TF? See, delta TF is directly proportional to I. If I is more, delta TF is more. If delta TF is more, that means freezing point of solution has to be less. So I is inversely proportional to freezing point of solution when the solute undergoes dissociation. This is all valid, people, for those solutes which undergo dissociation. And by chance, if they give you about those solutes which undergo association, at that point, you know, I is inversely proportional to N. Accordingly, you will answer. Right? I will be inversely proportional to N. Perfect? I will be inversely proportional to N. So more the N, lesser I. Lesser I means lesser relative lowering, lesser delta TF, lesser delta TB, lesser osmotic pressure. Accordingly, you can give all the answers as per, okay, as per the things which I told you. All clear? All clear, guys? KGMC Lucknow, that's great. That's great, that's great. Congrats once again. Kill it. Guys, again, I'm repeating, this is something which is valid for that solute which undergoes association. That solute which undergoes association. Okay. Let's say you have got 0.1 molar solute that dimerizes. Let's say you have got 0.1 molar solute that trimerizes. Okay. Can you give me the order of all these things in these two? By the way, dimerize means two particles are associating to form one. Trimerizing means three particles are associating to form one. Okay. So N value here will be 2. N value here will be 3. Now, accordingly, I believe you can easily give the answer. Right? So first of all, see, more the N, lesser I. So I for this will be less, I for this will be more. Now you can give all the answers accordingly. First of all, relative lowering in vapor pressure. Relative lowering in vapor pressure order will be? Relative lowering in vapor pressure is directly proportional to I. Right? So more the I, more the RLVP. So I would say A is greater than B. Perfect. Vapor pressure of solution. If RLVP of A is more, when RLVP is more, that means P0 minus PS is more. That means PS has to be less. Right? So A will be less than B. Perfect. So RLVP means P0 minus PS divided by P0, right? If this term is more, that means difference between them is more. When can be difference between them is more? When PS will be less. PS will be less. So I more, PS less. I more, PS less, yes. Third, delta TB is directly proportional to I. Okay. Which one has got more I? A. So A is greater than B. Delta TF is directly proportional to I. Which one has more I? First. A is greater than B. TB solution. TB solution. I value more. Boiling point of solution more. Right? Freezing point of solution is inversely proportional to I. B is greater than A. Osmotic pressure is directly proportional to I. I more means I more. A will be greater than B. Anything can be asked here. Is it live at 3 a.m.? Yes, it's live at 3 a.m. Yes, it's live at 3 a.m. Perfect, guys. I believe all the things are clear. Now, one topic is left. That is your Henry's law. I'll post its recording day after tomorrow, not tomorrow. Okay, because tomorrow means today. Today I have got some more sessions. Okay, day after tomorrow I'll post one short recording of Henry's law. So with this, solution chapter is done and dusted. Our next chapter will be on Monday 5 p.m. and that is going to be your chemical bonding. Which will be completed in 10 hours. Perfect, people. Now, after this particular session, I'll be sharing the session PDF on my Telegram. The name of Telegram channel is Wassim Bhat Chemistry Official. Okay. On this, I'll be sharing the Telegram, and on this particular Telegram channel, I'll be sharing the DPP also of this chapter. Please and please solve that the morning itself. Okay. Right. And one thing I would want in the comment section of this particular video right after the video ends, that is solution done and dusted. Hashtag solution done and dusted. Okay. This is something which I want in the comments. Solution done and dusted. This is something which I do not want not in the chats. This is something which I want in the comments. So are you guys getting that sense of accomplishment a bit? I'm just asking you. Are you getting any sense of accomplishment that you have done something effective? That the day was productive? Just tell me. Are you getting that feeling or not? And do let me know honestly. I want the honest answer. Tell me honestly. So Friday, Ambika ma'am, she is telling that she'll take the session on Friday. I mean, one more session. So this week she'll be taking 2 sessions. Because biology you have more syllabus, right? So it's okay if she takes more. Okay. So finally, we are done with this chapter. DV was literally awesome. Solved every equation and forced my friend through to. That's great. That's great. Keep on doing things. Henry's law, that's a small topic of 15-20 minutes. I'll post one recording of it. You don't worry. You don't worry. Perfect, guys. Chalo. With this, I'm taking a leave. Perfect. So next chapter is going to be chemical bonding, and one thing which I want in the comment section of this particular video, what is that? That is solution chapter done and dusted. Chalo, tada. See you. Bye-bye. Take care. God bless you all.